it's a lot of commitment, you know. Okay, we're now.
Yes, yes. And finally, I don't really need it, so.
Yeah. I think I'm getting close to that realization now. But all when I was younger and during my master's, also I was really determined to maybe chase for the next 5 years doing a PhD. But
yeah,
we've got time.
Exactly.
See what happens.
Exactly. And we have so many things to do to clean that word. That we have no time
exactly. Exactly. Where are you based?
In Paris.
Okay. Great, I love Paris. I'm in Abuja, Nigeria at the moment. So
yeah. Okay, I've never been to Nigeria. I've been in various places in Africa, Morocco many times, South Africa many times, but Nigeria never. I don't know why.
Not yet.
Not yet, exactly. But I'm not traveling much in the last 2 years, as you can imagine.
Of course, I don't think anybody has been.
Yeah. But, now we're all working with Zoom and others. Well, that's nice. We still meet people.
Absolutely, I agree.
Good morning.
If ever you have a PDF of your presentation.
Sorry, Yusuf.
Yes, sorry. I'm still rounding up on it, but absolutely share that once I have it. Once it's done tomorrow.
I'll send you my.
Yes, just this conference is broadcasted also via YouTube. Now your conference is already on YouTube live.
Thank you.
Okay, Professor Jamal join us.
Good morning.
Good morning.
Good morning, everyone.
Assalamu alaikum.
Welcome, salam.
I think we will we'll open the webinar to attendees. Start. We are waiting for Dr. Sonia Kalman. We are waiting for the moderator of this session, Dr. Sonia Karnan. Professor Dieter, you are promoted as panelist.
Thank you very much. Good
Welcome.
morning.
Good morning. We're always waiting for Dr. Sonia Karnan. Mr. Yassin Nasiri from Mazen will moderate this session because so far Dr. Sonia Karnan doesn't join us.
Hello, everyone. Good morning. I think Dr. Sonia cannot make it this morning, so I'll be the moderator of this workshop. I would like first to thank all the our keynote speakers that accepted to be in our workshop, which will be about the perspective of green hydrogen development for the case of Morocco, particular, and for the case of Africa. So I would like to thank Professor Jamal Shawqi for his acceptance to be with us in this workshop. He will be presenting his perspective and his insights about green hydrogen technology here in Morocco. And we will be pitching the presentation about where he will be answering the question, is large-scale green hydrogen ammonia production sustainable for Morocco? The second presentation will be presented by Professor Arek Shafek from Faculty of Sciences and Techniques of Tangier, Morocco, about low-cost catalysts for hydrogen production through dry autothermal reforming of methane. And our last invited speaker is Mr. Cédric Philibert. He will be pitching his presentation about hydrogen-rich feedstocks and fuels Africa's strength. So, Professor Jamal Shawqi, the floor is yours.
Okay, thank you very much. Do you hear me?
Yes, very good.
Dr. Sonia Karnan has joined us now.
Can you allow me to
Yes.
share my screen, please?
Yes.
Good morning, Dr. Sonia.
Sorry, good morning. Let me get in after the talk. Thank you.
Yes, I just finished the presentation of overall speakers, so I think you can follow on. So Professor Jamal Shawqi will be the first speakers to present his presentation, and then we'll be following on the other presentations. Okay.
Yes, I will take over. Thanks for thanks for covering. Thank you.
Okay, thank you very much. Thank you for inviting me to this very interesting conference. And as the chairman was saying, my presentation will be try to answer, is large-scale green hydrogen ammonia production sustainable for Morocco? Let's clarify two things first. The first one is I'm talking here as professor from École Polytechnique Montreal, not from anybody else. This is first. The second is that I will try to answer this question relatively to large scale. I'm not talking about production, local production by industrial people who have some needs and so on, okay? And therefore, let's clarify first, what are my personal applications on hydrogen, okay? I am involved in hydrogen in many consideration or many directions. First of all, I'm a member of a roadmap of Quebec. I'm also involved in hydrogen production from biomass, waste, and natural gas through gasification, pyrolysis, and so on. I'm also involved in hydrogen storage, especially in liquid form, ammonia and the combination between methyl cyclohexane and toluene. I'm also involved in many reactions with hydrogen, since I have a chair. I have a chair with Total. I am also involved in ammonia production through microwave, and also we just built a pilot plant for methanol production through CO2 and hydrogen, and also I'm involved in many hydrogenation in multi-phase reactors. Okay, we know that hydrogen economy will be anyway the future, and this is show clearly what could be in the future. Like the core will be the hydrogen production from many sources. I will be talking about that later on. And from that, of course, we can attack at the same time industrial and urban and transportation and so on. And everything can be involved in this hydrogen economy. Okay, the challenge when we're talking about hydrogen is it can be divided in three phases. The first one, of course, it must be produced. I will go through that, and I will be also introducing some study regarding the CapEx and the OpEx, what will be the investment and what will be the cost production. It must be second, store and transport if it's not used in the same place. I will also be talking about different ways of storage, and also I will be tackling what could be the CapEx and OpEx. And the third one, we have to do something with it. Of course, this now involves how this hydrogen can be used as it is, or source of fuel, or source of chemicals. Right now, hydrogen consumption around the world is around 65 million tons per year, which heavily produced from fossil fuel, heavily. This is why this technology, it emits a lot of CO2. We are talking about around 830 million tons of CO2. And this is what we call gray hydrogen. When this process, we separate and store the CO2, in this case, this gray hydrogen became blue hydrogen, which is exactly the same as gray, except that CO2 emissions coming from this process is captured, stored, or reused. This is what we call blue energy. And now the utilization of this hydrogen could be, of course, from solar, wind, algae, biomass, and so on. And it could be also, and this is what the most important production right now is from natural gas, oil, and coal. And from that, of course, we can produce electricity, we can do chemicals, and so on and so forth in order to do that hydrogen. And the use of hydrogen, if this is use of hydrogen, it's mainly used for refining in order to decrease the sulfur in refineries, and also for the production of ammonia, mainly. And the others, it's methanol and so on. This is the main utilization for hydrogen right now. Okay, I was talking about a gray hydrogen, as I said, is the production from fossil fuel without any CCS regarding CO2. I was talking about blue hydrogen, which is also usually it uses fossil fuel, but specifically natural gas. And with natural gas, we can separate, store CO2. This is what we call blue. And now we are talking about green hydrogen, which is usually it doesn't use any fossil fuel. It uses usually electrolysis, and the energy of electrolysis is coming from renewable energy. This is very, very important. We are now developing new kind of hydrogen because it's located between the blue hydrogen and green hydrogen, and the idea is to the feedstock is natural gas, but rather than heating up conventionally with natural gas or with a few fossil fuel, is to heat up this natural gas in order to produce hydrogen, is electrically heated. And this is, we are still using fossil fuel, which is methane, but rather than adding source of energy which emits CO2, we are doing the reaction with electricity, and this belongs to process electrification. Okay, now with this, when we say capturing CO2, a lot of people, they think that is the ideal technology, but it has a lot of disadvantage. Here is an overview of a big disadvantage of post-combustion CO2 capture, which is CCS. And this is the technology which is an industrially available, but it has a lot of issues. I will talk just here you have summarized the disadvantage. I will talk specifically to energy intensive process. We're talking about 3.3 gigajoule per ton of CO2, which is a huge, especially during the desorption. And also it emits a lot of pollutant. And this is the technology is really, I mean, even if it's at industrial scale, it still has a lot of disadvantage. Okay, now when we are talking about green energy, of course, we are talking about electrolyzer, and you have alkaline electrolysis cells, you have proton exchange membrane and solid oxide, which is, I think, that will be the future. And you have here table which summarize what is the electrolyte, what is the pressure, temperature, and so on and so forth. And the last line, which is extremely interesting, please take note of this, that the largest capacity in 2019, I mean, 2 years ago, it's only 10 megawatt for alkaline electrolysis, and proton, it's 20 megawatt. This is extremely important because in the future, we are going to talk about gigawatt. That means that we have to multiply this largest capacity that we're having right now by something like 100 or even 1,000. Okay, here you have a table which shows, I will not go through it completely, but you have for each of this electrolysis technology, you have advantage and disadvantage, and we still have a lot of work on any kind of this technology, and it's still room of improvement, of course, as research is going on. And here it shows, this slide shows what, how much CO2 emissions through the technologies, of course, when the hydrogen is produced through what we call green CO2, it's a green hydrogen, sorry, the emissions are very low. And if it's for example, natural gas, you see that the comparison between 600 and 6, you have something like 100 more CO2 emissions. That's why we call this hydrogen when it produces from electrolysis through electricity coming from renewable energy, wind or nuclear or hydroelectricity, that we call it, green hydrogen. And you see that even solar is considered as a clean source. You see that it's still a little bit higher than the wind, for example, in terms of CO2 emissions. Okay, now I talked about how we can produce hydrogen. Now let's move to the CapEx, how much it costs to produce this electricity. And here I was talking about alkaline and PEM, and you see alkaline and PEM. You see this is this study is done in US, and you see that the capital cost, we are talking about the capex, and this is in terms of euros per kilowatt. And you will see also the estimation in 2030. This is, of course, assumptions and what could happen in 10 years from now. And you will see, by taking this into account, we will estimate how much we can produce. What is the investment if we wanted to go for to build a huge capacity of hydrogen in terms of capex? And of course, my first answer to the question that I have been asking is large-scale green hydrogen ammonia production sustainable for Morocco? This is the first answer. Let's have an idea about what is large scale. And large scale could be whatever. And my estimation here is coming from the fact that I have to produce something like 140,000 tons per year. It could be whatever, but I have to bring some number here. And this corresponds to production of 750,000 tons of ammonia, which correspond to 1 million tons of fertilizer. This is just we have to start from something. How large is the scale that I'm talking about? I mean, if you are talking about 100,000, it will be 100,000. If it's 200,000, it will be 200,000. But this is an estimation, an assumption on what is large scale. And if we go from 140,000 tons per year, let's calculate what is the capex, what is the consumption, different consumption, and what is the OPEX. And here are the numbers that I am coming with. Is the for PEM electrolyzer, we are talking about the 8 terawatt. It's huge. And if we are going for electricity at 70% efficiency, which is what we are talking about here, we are talking about the power that we have to install is 1.5 gigawatt. And remember that the highest capacity that we are talking is around 20-30 megawatt. Here we are talking about 1.5 gigawatt. And of course, when we are talking about electrolysis, we are talking about water, and the consumption of water to produce this amount of hydrogen is 2.3 million meter cubic per year, which correspond roughly to 200 to a small city with 200,000 inhabitants, or if you wanted to have another clear image, 600 Olympic swimming pools. It's huge, and we have to ask ourselves where this water will be coming from, and especially with a country like Morocco, when we have a lot of issues regarding the water, and you know everything about that, and I will not go through that. And how we can produce this electricity, and how we are going to what will be the capital cost. If you look at what happened for Noor, in 3,000 hectares with Noor 1, Noor 2, and Noor 3, and Noor 4, you have here the capacity, the power, and the cost. And we're talking about 4 solar power plants, which around 600 megawatt electric. I think it's electric, but I'm not sure. But let's put it electric. And the total cost is 2.5 billion US dollar. And if you are wanted to produce the same quantity, we are talking about the equivalent or 2.5 equivalent of Noor. With its surface, therefore, it could be something like 7,000 hectares. And of course, the capex will be around 1.5 to 2 billion US dollar. This is the first answer to my question. Now, what is the OPEX of this hydrogen? And this figure, it gives some comparison of cost of produced hydrogen for natural gas, from natural gas. Please don't forget, this is from natural gas. And you will see that the more or less, we're talking about 1 to 1.5, depending on the cost of natural gas, of course, mainly. And if you take different countries and so on, these values are for each of these countries. And you have 2 figures, one with no sequestration of sequestration of CO2, and one with it. And therefore, here we are talking about gray hydrogen and blue hydrogen, and you will see that the cost is between 1 and 1.5 to US dollar per kilogram of hydrogen. This is very important because we have to compare it with hydrogen that it can be produced from electrolysis, for example. And this is what the comparison gives. And I will be talking a little bit with the following slide. What is the cost of this water electrolysis? We are talking roughly that when the people they are talking about what is the cost of the electrolysis compared to steam methane reforming, which is what we call SMR, we are talking roughly about 2 to 3. Here I'm keeping 3. This is the ratio between right now between the hydrogen that's produced from electrolysis compared to the hydrogen coming from gray hydrogen. This is gray hydrogen. Okay, now what is the cost? What hydrogen costs from electrolysis? It's very, very sensitive to at least 2 parameters, and we don't have to forget this, which is extremely important. The first one, which is obvious, which is the cost of electricity. Obviously, the cost of electricity will impact directly the cost of hydrogen. This is first. And the second, the capacity of how you are working with your electrolysis, which collect the load. The load is extremely important, and you see that you have the decrease, radical decrease when we are increasing the load. And we know that depending on the electricity is coming from the sun and so on, the number of hours that your electrolysis is going to work it's extremely important in terms of the cost of hydrogen. And therefore, when we are talking about hydrogen coming from green hydrogen, when we are giving costs, we have to make sure on two assumptions: what is the cost of the electricity and what is the load related to this cost. This is extremely important. And this also give very, very important issue. Here, what you have, the number that you have in this rectangular are the cost of this hydrogen, green hydrogen. And what you have here is in the left side, what you have is the cost of the electricity. And the bottom in the vertical line, in the bottom, the load factor, 10%, 20%, up to 50%, for example. And what you have here, it's clear that if you look at the rectangle at the middle, that if you go from the top to the bottom, you have an increase, a radical increase. The first line in terms of cost of electricity is 0, and after it's 10, 20, 30, and so on, US dollar by megawatt hour. And what you have, you see that depending on the load, of course, and depending on the cost of electricity, the cost of hydrogen will be extremely high or low, depending on these two parameters, which are very, very sensitive parameters. And therefore, if you wanted to compare in an overall view, what is the cost of hydrogen coming from SMR with CCS, which is a blue hydrogen, we are talking roughly about, if you look at a different here figure, we're talking, as I said, between 2.5 and 3, if we are talking, I was talking about 3 is for SMR without CCS. Here we are talking about SMR with CCS, which is around 2.5 or 2.3, 2.4. And I mean, at least double the cost of this hydrogen. Now let's talk about, we are producing hydrogen. We see how much it will cost in terms of CapEx, in terms of OpEx. Let's move on to the storage of his hydrogen. And storage of hydrogen can be in different ways, physical or material based. I'm not going into that, I don't have time, but roughly here you have some volumetric and gravimetric weight of hydrogen with different storage densities and so on, different technologies. Ammonia, transform hydrogen to ammonia. Ammonia is very interesting chemical product as storage of hydrogen, liquid hydrogen and gas hydrogen and other technologies. I will be not talking about this, but you see that I mean, for ammonia, it's very, very high in terms of volumetric and gravimetric. And we did the study for Total. If we are producing at the center of France hydrogen, transportation at certain in the red line by train, and after transportation by truck, what is the best technology in terms of CapEx and OpEx? I'm not going through that, but the idea is to go, we have different scenarios. What's really very interesting that the best scenario is to go for ammonia to transport. In this case, specific case is ammonia transportation, and therefore in the rest of my presentation I will be talking specifically to ammonia or at high pressure. Okay, now let's talk about the answer. This is my second answer to my question. First question is ammonia production. And if wanted to produce ammonia in the large scale, I mean, which correspond to 150,000 tons of hydrogen, the CapEx related to Haber-Bosch process is around 100 million tons that has to be added. And knowing that Haber-Bosch process works typically between 200 and 400 atmosphere and between 400 and 650 degrees C. And if wanted to build it close to where we're producing hydrogen, that means it has to be produced in terms, for example, for Morocco, close to Ouarzazate, for example, when we have this Noor, it has to be built in the middle of nowhere, and where this know-how will be coming from. And of course, hydrogen cost will around is 3 times what 2 times and 2.5 or 3 times what compared to SMR, and we are estimating that green ammonia will be at least double cost of conventional ammonia coming from this. Okay, now the transportation, I will go brief, I'm looking for my time here. If we want it now to where we are now producing hydrogen, we know how much the cost will be in terms of grain of ammonia. Now, if we wanted to transport it as high pressure, let's estimate how much it will have. If we are talking about 400 kilometers, which correspond to certain distance in Morocco, and comparing what the capacity of the truck that it has to transport this hydrogen, it takes something like 100,000 round trip annually to transport this hydrogen, which again correspond to 140,000 ton per year. And if this it makes by a truck, we need something like 500 trucks. This is another investment which is around 150 million US dollar just for this truck. And of course, this truck is doing 160,000 kilometers per year. And the question is, which fuel is going to be used in that case? Of course, here it's the comparison. I think everybody knows this graph, which is extremely interesting. Hydrogen used as fuel for transportation. And this very showed clearly that if, depending on the distance and the mass that you are transporting, if it's very low, you cannot beat the electricity and the batteries. But if you are going to long distance with big mass to be transported, the weight of the batteries will be extremely huge, and therefore that's where hydrogen will be very interesting. And in this case, in the truck that are transporting hydrogen, that could be, of course, they can use hydrogen, and we have to estimate how much hydrogen will be used in that case, or it can be done in other ways. Okay, now the transportation, the cost of this transportation of hydrogen, we are talking about something like we are more or less doubling the cost of the hydrogen that we are producing. And this is studied and done by many people, that the transportation, depending on the distance and so on, at the end, the cost of this is Canadian dollar, which is not US dollar, which correspond to the numbers that has been showing, and the cost at the end will be quite high compared to by including here. It includes, of course, the production and the transportation of this hydrogen. Okay, now I think that this is my third answer for this is large scale green hydrogen ammonia production sustainable for Morocco. This is my third answer. I think that Morocco is leading the production of this clean energy, which is extremely good. I'm proud that Morocco is one of the leaders to do this, but we have to think what is the best uses for this clean energy. Is it to produce hydrogen ammonia at a large scale, or is it to do something else, which is here some ideas that to use it for residential industrial consumption. We know that some industrial people, they are stopping their process because of the high cost of electricity. If we are giving them electricity which is cheap, that perhaps they can produce high added value product, new product. We can produce, of course, Morocco has a lot of problem related to water. This has to be, this energy can be used to produce drinking water, and this is what Morocco is doing already. You have a huge plant is built already in many cities, and the last one I think is in Agadir. And of course, as I said right at the beginning, this electricity can be, this clean electricity can be used to electrify processes and reduce CO2 emissions at the source, rather than having producing CO2 and after trying to capture it. And we know that the technology right now, it's not adequate for that. And of course, we can have new ideas, and researchers can have can bring new ideas and innovate how to use this green energy to produce something different than just large-scale hydrogen. And this is my conclusion. And I will be answering, is large-scale green hydrogen ammonia production sustainable for Morocco? My answer, personal answer, is no, especially for now, when we are using a lot of water. And of course, the second idea is Morocco must continue to produce renewable energy. And this is what Morocco is planning to do anyway, which is extremely good for Moroccan industry and for people, for all Morocco. And this renewable energy must be used for improve the needs of citizens. Moroccan can produce, as I said, drinking water, can improve the competitiveness of industrials, and especially by giving them cheap energy that they can really produce new products. They can also use this electricity to electrify their processes, and we can show that it will be beneficial in terms of energy consumption. It will be beneficial to introduce new processes, and it will be extremely good to reduce CO2 emissions at the source. And also, we can find new original uses for that. And we have many examples. And personally, I'm involved in many new original uses of this electricity in order to do a lot of very important and very original stuff. Please note that for industrial hydrogen, I'm not answering this question, because the industrial people, they are able to analyze their situation in terms of CapEx, OpEx, competitiveness, and they will go for it or not, depending on their process. If they need, of course, hydrogen to do some specific reaction, they will do, I mean, they have all capability to see if it's worth it to go in that direction or not. My answer here is specifically for large-scale green hydrogen ammonia production, as it is for Morocco, not for the industrials. And thank you very much for your, for your attention.
Thank you, Professor Shouki, for your talk. I think it was a very nice overview, and actually provide some sort of introduction to the next talks. I see some questions in the chat and also in the Q&A, but I think some of these questions are a bit generalized, and to save time, if I ask the people who asked them to be patient, so that we have them answered in the discussion. I think they're somehow related, and maybe it takes a bit of time to cover all of them, so that we can move to the next talk.
Now, I will answer, but I saw some answers.
Yeah, there's some that you could
the chat.
answer.
I will answer them in the chat.
Okay, and then there's some which maybe I will ask again in the discussions to invigorate the panel discussion.
Excuse me, you can divide the discussion between keynote speakers. You can answer a question relating to his talk before starting the next presentation.
Okay, there's some questions which maybe which can be answered directly.
Yes,
okay.
Excuse me, Dr. Sonia, you can read the question to all participants, because we can
Okay.
other participants don't see the
Okay.
Q&A box.
Okay, so I go to the Q&A, and there's one by Erhali Ben Said, and he asks, are there any insights regarding the round trip efficiency of using green hydrogen for electrical energy storage? And to which extent does it make economic sense for long-term storage?
I'm sorry, I had some problem with my internet. Can you repeat the question? I'm really sorry.
Yeah, no problem. This person who asks if there are if you have any insights regarding the round trip efficiency of using green hydrogen for electrical energy storage, and to what extent it makes economic sense for long time storage.
I'm sorry, I don't understand exactly the question. Is a long-term storage for?
Yeah. Okay, the person is asking if you have any ideas or any values or figures for the round trip efficiency of using green hydrogen for electrical energy storage. I think this is from the electrical energy that's used to prepare the hydrogen, store it, and then reuse it again. And then he wants to find out if this makes economic sense already for long time storage or seasonal storage of energy.
If you wanted to have a long-term storage, that means your storage tank has to be huge, and this has to be estimated for the time that you are going to. What is your scale in terms of time, and this can be estimated, of course, depending on the quantity and the time that you are having. And therefore, I cannot specifically answer the answer depending on the time that you are having, depending on the quantity of hydrogen, but this can be estimated easily right now.
Dr. Kalnan, just for your information, this will be part of my presentation, so I will have...
Exactly. This is why I had wanted to push all the questions to the discussion, because I have a feeling that some of them might be answered in some of the following. I looked at the questions and they look somewhat generalized, and I had a feeling that they could be answered in the discussion part after everybody's heard what the other speakers are talking about. So I don't know, Professor Zaz, what's your...
Yes, I think we switch to the next...
that was the original idea I had.
Yes.
Because I saw the questions were quite generalized, yes, and could lead to a lot of discussion and time.
Professor Tarek, please.
Thank you very much.
Thank you very much.
So to everybody who's asking questions, it would be nice if you write the name of the speaker that you originally addressing the question to, and then afterwards we can sort it out. Okay. If you can bear with us. So we have a next speaker, Professor Tariq Shafiq from the Faculty of Sciences and Techniques of Tangier in Morocco, and he's talking about low catalyst cost for hydrogen production through dry autothermal reforming of methane. You're welcome.
Yeah, thank you. Thank you, my friend Yusuf, Zaz, for the invitation. Are you hearing me?
Yes, we can hear you.
And okay.
And we can see the slides.
Yeah, very good. So I'm very happy here to participate to this important meeting regarding this issue of green hydrogen, and also I'm very happy to give my talk after the very interesting conference of Professor Jamal Shawki, from whom we are learning a lot every time. So my presentation is going to be rather focusing on some with respect of the, but first of all, if you allow me, I can introduce a little bit myself. So now I am a full professor here at the Faculty of Science and Technique in Tangier, and I graduate from the University of Lyon. I was doing catalysis at Institute of Catalysis and the School of Chemistry at the Laboratory of Catalysis at that time, directed by Professor Teschner, and my supervisor was Professor Daniel Bianchi. So during my PhD thesis, I managed to produce, I mean, to develop a system for studying the reactivity of catalytic species involved in CO2 hydrogenation for producing methanol. So at that time, we were studying this with the O-prime spectroscopy using FTIR. And then afterwards, after graduating, I use also this technology in the laboratory of Professor Verikius in Greece and also in Japan for studying, for example, the NOx system, diesel engine. And since my appointment at the Faculty of Science and Technique in Tangier, I'm trying to develop, because I start the lab here from the scratch, because the faculty was newly built and they give me a room that was my laboratory, and I start building the lab. So from that time, we decided to have this strategy to give some added value to local resources in order to use them in some development technology, sustainable development technology. So this is basically, I'm going to take you to a journey through several PhD thesis results that were devoted to the study of the use of clay as adsorbent first, then as a catalyst for reforming of biogas in order to produce syngas. So this has been presented before. So this is the main processes for producing hydrogen through syngas. So there is several aspect technology using local, I mean, renewable resources. In this case, we are talking about the power to X. But the one I am going to talk about is basically the one involving biogas as a feedstock. And of course, we were inspired from these processes, steam methane reform and partial oxidation of methane and so on to produce the syngas. So this is the picture, for example, regarding the process at large scale. So this has been presented before by Professor Jamal, and what is the idea is here, and that means we can associate for the heating of the reactor, we can associate the renewable energy. So this was pointed out by the work of Augusto Bianchini, who in order to gain in the yield of and the performances of the process. And also there is also another picture regarding this process using the biogas as a feedstock in order to, through the CO2 and the hydrogen, we can also produce the methanol. So with this in hand, we were thinking that biogas could be very interesting, for example, for bringing electricity and energy to some remote area, for example, in developing countries like our countries. And of course, this is a sustainable and a renewable resources as it is explained in this slide. So this is basically the composition of the biogas we can get through several feedstocks. And here, for example, this is an example of a system that can be used in order to produce biogas in some remote area. And of course, this is what we can obtain using different substrate to produce methane. So we can see, for example, sometimes in our local areas, we have some problems with the waste management, especially for these places where we are producing meat, and we are producing also some chicken waste. So it is very interesting to make use of these resources in order to get the biogas, and later on, why not hydrogen and electricity for example, through fuel cells. So this is the involved reactions. So this, for example, considering the composition of the biogas. So this is very interesting with respect to the greenhouse gases, because we are actually converting two major components, which are CO2 and methane. And of course, this is an endothermic process, but it is possible to add some oxygen in order to make use of this the exothermicity of these reactions. And of course, we can use the three processes to make the so-called autothermal reforming. But these processes, they require very efficient catalyst in order to solve the problem of cooking, and which is usually used by using the noble metals. But noble metals could be very sensitive to the problem of poisoning. And also we need to have this catalyst very, very selective if we want to activate in a very efficient way CO2 and methane, because of the stability, the higher stability of the CH bonding and the oxidation state of CO2. So mainly the engineering of the catalyst, and my talk is going to focus on this, mainly on lab scale studies. So we have to think about the cost, of course, of the trying to replace these noble metals, and also to add some very appropriate promoters and the dopants, and also to think also about the support. And this is not the only issue, because if we need to develop the catalyst that can also successfully achieve the application at a larger scale, we have to follow a lot of studies, and particularly the studies regarding the investigation at lab scales in order to develop the appropriate formulation. But we have also to do a lot of engineering studies with respect to mass and heat transfer, with respect to the engineering of the reactor and the process design and things like this. So for example, and here I will show the example, for example, this system for trying to, why not to reduce the size of the fuel cell. Let's see, this is the study from a German team. They choose this shape as a honeycomb monolith because of mainly because of the problem of the heat exchange optimization and dissipation. And so this is mainly the idea of my talk is inspired from these people using the clays, local clay, to be extruded to make this this object for the kitchen. And we say, okay, we can use the same material to produce the so-called honeycomb monolith. So this is what we try to do during this the journey of several PhD theses regarding the application of this kind of local resources. Of course, we got also inspired from the most popular application regarding the three-way catalyst using cordiorite as a support for for solving mainly this the problem also of the pressure drop. But this support, they need some wash coating with an appropriate support, and also to fix the active phase. So I will show you later on in my talk that we, based on through our research activity, we managed also to introduce the active phases and the dopant in a very innovative way. But let me first give you the most points that will be treated in my talk. So first, I will talk about the extrusion of this the clay, and then investigating the absorptive and the catalytic properties. And the final point is regarding the tuning of the catalyst properties with respect to biogas, model biogas reforming. So for this, we started the research around, something like 20 years ago. And at the beginning, we wanted to use this clay as a sorbent for volatile organic compounds. For some local companies, they are making some parts for automobile equipment. And so we wanted to use this system as a sorbent for volatile organic compound for xylene. So we built this setup for measuring the catalytic and the absorption properties. So this is basically the setup. It has mainly the system for controlling the gases, and then the reactor and the analytical system. So all this is homemade. So I'm pointing out this result for the student, so as they can get inspired for some experiment. So this is the equipment in the lab. Basically, all the equipment are homemade, but that was at that time, 20 years ago. We didn't have a lot of money. We didn't have the project, but we managed to build this, and also why not to do some research with the valuable equipment. So this is for the calibration of the FTIR, because we were using the FTIR for studying the orthoxylene concentration. So, and what is interesting here that I show you, so through the breakthrough curve, we can get some absorption capacity that was used for this kind of experiment to study the absorption capacity during saturation with the orthoxylene, and then after saturation, we performed the isothermal desorption and then the TPD. And by playing with this data, we could explain the absorptive behavior of this clay material that was mainly mesoporous, as we can see here, and it was mainly associated with the porosity of the material. So we could also, by using this data, get the information regarding the weak absorption energy, and although it was not chemisorption because it was the orthoxylene that was fixed in the very narrow pores. And from here, we can, using this thermodynamic, we could get these values for the isothermal absorption and the TPD. So this is the result. This is the isotherm we measure, and of course you can imagine this 1.1 day experiment. So from this result, we could get values of the isosteric heat of absorption. So I'm going very fast, but if students are interested, I can come back to the slide and answer in details. So this is the weak absorption value, and by measuring the TPD, also the temperature programmed desorption, we can measure the value of the species that is strongly adsorbed with the clay. So here, for example, by measuring the maximum temperature at different heating rates, we could apply this Sivantovich equation, you can get the value of the more strongly adsorbed species. So this result was published, and then one of them, we got more than 150 citations. Now, we will move to the catalytic behavior, and by looking at the chemical analysis and XRD diffraction, we could find very interesting point that this clay basically contains silica and alumina, contain also some iron, potassium, magnesium. So this is basically is what is needed for a catalytic support. And of course, this could be also used as an active phase. And these species, usually they are used also as a dopant and promoter. So here we have naturally available material that can apparently work as a catalyst. And this is what we try to show during the one of the PhD thesis. Why not? Because this chemical composition, the structure was also very stable, although we increased the temperature. So this is also another argument that allow us to use this material as a catalyst. And we use it as a catalyst for combustion of several species. And here, so by following as I explained before, the higher band of the several species studied, so we could examine the behavior of this clay as with respect to the catalytic combustion of the different species. So this is what we obtained, for example, in the case of the CO, so we can follow and we can monitor the catalytic combustion of conversion of CO to CO2. And what is interesting here, by measuring the light off curve, so this is in the absence of the clay, and with the presence of the clay. So we can see that here the effect, the catalytic effect, lowering the conversion temperature, and significantly. So this we try to investigate, say, okay, so this clay behave as a catalyst. What is because this is the issue when we are working with this natural product minerals. That means we have to identify and to link the catalytic performances with the very appropriate active phase and so on. So this is what we try to explain here by trying to compare the clay with several other material that were coated by CVD to several for example, with, for example, using the iron oxide deposited on this support, a quartz support, cobalt oxide, etc., etc. And we show here that our clay, for example, here is still the best performances with respect to this material. That means this is what we said before, especially when we study this with the cobalt supported on the clay and the neutral cordiorite, so that there is, for example, here the particle size are having there is a kind of interaction between the metal and support, reducing the size of particles, and this is why we assume that this was the origin of this significant catalytic properties. So with this in mind, we say, okay, so this is the summary for this. So we said, okay, this is the result. That means we could add some species, like, for example, nickel or others, dopant, to try to tune the catalytic behavior of this clay material with respect to the autothermal reforming of methane. So this is what we try to do. Yes, we try to use the nickel because this is the most transition metal used in this case to replace the noble metal, and also because of the prices, because you can see the prices here of the nickel, nothing to do with the prices of platinum and etc. And also we decided also to add some basic site needed for the CO2 fixation contained in the biogas and involved in the dry reforming. So this is the strategy for developing this material. So first we have to adjust, because here we were mixing we have to find first the formulation with the catalytic appropriate formulation, and then try to extrude it, and to extrude it without wash coating, because wash coating sometimes is having some challenging issues to be solved, like the thickness of this wash coat that should be controlled exactly. So this is why we started to optimize the loading of nickel, and what is the appropriate additives we should use. The dopant, cerium, lanthanum, etc., etc. And then afterward, once we defined the catalyst formulation, we tried also to start to study the extrusion. So this is the study with respect to mixing to finding the loading of nickel and the ceria needed to achieve the syngas production. And we say, okay, so the best loading was obtained here with the 10% nickel and 15% of ceria. But yes, we got a deactivation of a catalyst after 24 hours. And this was attributed mainly after the 24 hours to the formation of these species, nickel, iron nickel, if in E3. So this was at the formation of these species that caused the deactivation of the catalyst. So this result was published, and then we had to in order to solve this problem, we changed the ceria with the lanthanum. So here we solved the problem because there is no deactivation even after 24 hours, and this was due to because we had no iron in E3 formation even after 24 hours, and of course you can see here the size of particles involved is significantly reduced with respect to the previous case. But the problem is the result was published, but the problem here is when we try to extrude the system with the ceria, it doesn't work. With the lanthanum, it doesn't work. So we change another promoter, the lanthanum with magnesium. And here we follow the same approach, and we found the right appropriate composition, and we managed to extrude this monolith, honeycomb monolith, with this appropriate composition containing 8% of nickel, 3% of magnesium deposit on the monolith. So this is the result. This part of the result, this was one of my students, last one, I think we did it with the University of Poitiers because we were having a project together. So this is the extrudable paste we obtained, and this is the process that was used to give to this monolith with the appropriate mechanical properties. So this is the mechanical properties here. The test was acceptable mechanical properties. And we explain this behavior here with this clay as the formation of a solid solution based on magnesium in nickel oxide. And of course, this is the species, the active species we formed with this mixture. we can see here, we managed to reduce the particle size, and this was explaining the high catalytic performances of this system with respect to the syngas formation. Another issue is also regarding the basic involved sites. So we can see here with this composition, 8%, 3% magnesium, we obtained the highest volume of CO2 adsorbed, because we did the CO2 absorption desorption in order to study and to make a quantification of the basic site involved in the CO2 adsorption. So this is also explain, give another argument with respect to the catalytic performances regarding the increase of the dispersion of this site, and that means we have more available site for the catalytic act. So this is the summary of this result. Yes, so we can see here with this catalytic performances obtained with respect to the CO hydrogen yield and the amount of available basic site involved in this process. So the result will be published in this paper, and this is the summary, giving the most, the most significant result obtained in, during this talk. So at the end, I have to acknowledge the participation of several colleagues from different universities. First from France, starting from the project I got with my former laboratory, year 2000, and then with also some colleagues from Spain, with whom mainly we succeed this extrusion of clays, and last also with some colleagues from University of Bielefeld, Germany, with whom we also have some collaboration regarding this project. Thank you very much for your attention.
Thank you very much, Professor Shafiq, for your talk. I looked in the questions, and I see that there is one which is directly relevant to your talk. And this is the one from someone asking if you, may I know, I think he wants to know the silica and alumina ratio in one of your slides. I'm not sure which particular one.
Yeah, so we can get this information from the, yes.
But maybe you answered by the time.
Yeah, but
anyway, you could show it again. Thanks.
Yeah, so because I have here the result regarding this. Yes, the ratio. I don't remember because that. Yes. So we can have here the data regarding the weight percentage of silica and alumina contained in this clay.
Okay, I don't see any other directly relevant questions. The others are of a general nature, and so we'll push them to the discussion and perhaps move on to the next speaker. Thanks very much again for your talk.
Yeah, thank you.
So the next speaker is Mr. Cedric Filbert, an energy and climate analyst from France, and he will talk about hydrogen-rich feedstocks and fuels in Africa. You're welcome.
Thank you, Madam Chair. Good morning, everybody. Bonjour tout le monde. Salam alaikum. I will start my presentation with one slide on climate change, just to remind us that we are not looking at how could, to what purpose could we what can we do with hydrogen? We're looking at a problem, which is global warming, and we're seeking solutions. And I also show a couple of slides from the IEA net zero emission report that was published in May. It shows the very large expansion of renewables that is at the heart of a net zero emission pathways to 2050 as the most important dimension of a trajectory to put us to as close as possible to limiting global warming to 1.5 Celsius degrees, which is the aim of the convention and the mankind through the convention since the Paris Agreement in 2015. You see here the big expansion of solar and wind in the electricity mix. And by 2050, you see that basically you have 10% nuclear and all the rest is renewables, basically notably solar, wind, hydro, bioenergy, but basically it's wind and solar because the potential is unlimited compared to our needs globally, at least. And therefore, this is the one big aspect of the solution. Now, if you move from the energy mix of the electricity sector to the global energy mix that counts on all fuels of all sorts and all energy needs, heating houses, industry, cement making, steel making, and the like. You see three pillars, not only two. You see biomass, which is very versatile with solid bioenergy, liquid bioenergy, gaseous bioenergy, and then solar and hydro as the main part in the electricity mix. You see still in this net zero emission, not a gross zero emissions, you see still some uses of natural gas and oil where they are very difficult to completely eliminate by 2050, but this is a so low level, about the 6 of current energy related CO2 emissions, that this is compensated by natural mechanisms that removes the CO2, and this is why it's compatible with net zero. Two important things to be seen on this graph as well. The first is that the total energy supply reduces a little bit and then kept constant in a world that sees an increase in the global population and basically a doubling of the gross world product. So it's not degrowth of the economy, it's possibly relatively, it's not an extremely rapid growth, but it's growth and growth of the world population and growth of wealth. But this is compatible with that. And one important aspect that explain this, of course, you have energy savings, you have sobriety, you have an effort by many to avoid some aspects of consumptions, but electricity share in this mix goes up from 20% today in the final energy mix to 50% or more. And that's very important. Electrification in itself brings about a lot of energy savings, and that's very important. You cut losses in the internal combustion engines, and you cut the losses in the power plants, and that's very important. And you also multiply the effectiveness of using energy to warm your houses or for low temperature industrial heat, thanks to heat pumps, where you spend 1 kilowatt hours to get 3 or 4 kilowatt hour in return of low temperature heat. So these two aspects are quite important. And you see here that for the first time, the IEA has mentioned behavioral changes that are on purpose and material efficiency. This requires willingness to act by millions of people. You also see that while technology is very important, technological change is very important, yes, but it's not only the companies, it's also the consumers. It's you and me that need to make the right choices. At various levels. So if we have to buy a new car, it has to be electric. If you have to decide if this morning we cycle or we drive to work, if cycling is possible, it should be cycling, etc., etc. So all this matters. It's not just markets and technologies that do the change by themselves. It requires mobilization of everyone and incentive policies by all type of authorities at all levels, governments, municipalities, regional authorities, etc. Now, hydrogen in this scenario has its importance, but it's second to electrification. It's where basically electrification, direct electrification, is really hard and doesn't work. Shipping is where the IEA has seen the biggest use of hydrogen as ammonia in the future. Some in road transport, I think this is way too high in my taste. Aviation, of course, because aviation is very difficult. Chemicals, of course, and iron and steel. And for chemicals and iron and steel, I'd say this is possibly too low. And in particular for chemicals, we can really use a lot of hydrogen. For this, the production of hydrogen would jump sixfold by 2050 compared to today, the 120 million tons that is being produced both in pure as 70 million tons, but also in mix in steel making and other activities. And to make methanol, for example, it's mixed. So you have in total 120 million tons today. It should be multiplied by 6, and this will involve both blue hydrogen and green hydrogen, and I'll come back to that in a moment. We'll need both by all means. Still, the rise of green hydrogen is very important, and it's been due to the decline in the cost of renewables, which brought electrolysis to the brink of competitiveness, which we showed at the IEA in 2017 in a paper I wrote, Renewable Energy for Industry. And there we see that the cost, here is the load factor of electrolyzers in full load hour equivalent. And we showed that the cost of electrolyzers matters, but when you have 30% capacity factor, then it's the cost of electricity that matters most. And precisely the reduction in the cost of electricity with PV cost being divided by 10 in 10 years is what brings the electrolytic hydrogen closer to competitiveness. Here you have the line that corresponds to electricity at $70 per megawatt hour. That's basically what you have now, where there is a big potential in the north of Europe for offshore wind, where there is no real limit in the potential, but there is a limit in the cost. It won't go much down than this $70 per megawatt hour, unless we make a mistake in projection, which is always possible. And here is a cost we had in recent years in north of Africa, and now also in the south of Europe, extreme south of Europe, the Iberian Peninsula. $30 per megawatt hour, right? That was the cost for wind in Morocco already years ago. Solar is in that range. PV, of course, not CSP, which is more costly. And this I compared to the cost of gray hydrogen and blue hydrogen, but that was a cost in 2017 and 2019. Now the cost of gray hydrogen has jumped together with the cost of natural gas, and I'll be back to that. But the cards are being completely changed nowadays. This is what you do if you have little amounts of zero electricity, zero cost green electricity. The surpluses which are in limited amount, but it's part, of course, of the game, and you can have some hydrogen from that. Where are we going to use green hydrogen? Of course, we want to green ammonia and methanol for their current industrial uses first. And then, of course, in refineries, as long as we have refineries with oil products, to upgrade and clean fuels. Next, probably direct iron reduction in steel making with hydrogen, although there is an alternative with direct electrowinning, which will eventually be more efficient. But still, this is quite under development. We have now a plant in Sweden, but in fact, we already had a plant years ago in Trinidad that used pure hydrogen to make to the reduction of iron ores. It is important to get that in steelmaking you have two sources of emissions, like in making hydrogen, by the way, with fossil fuel. You use the coal here, both as a reductant of iron ores, the way to extract the oxygen to the iron ores, and then you produce CO2, and then you have it as a source of energy. If you go to direct reduction, which is now done in many places of the world, but with natural gas and syngas, you use both the carbon of the syngas and the hydrogen to reduce the iron ores, and then you use electricity as a source of energy to melt the metal iron and then make steel. If you replace this syngas here with pure hydrogen, you can then make steel. And if you have green electricity to run your electric arc furnaces, then you can make steel basically without CO2 emissions. Next use will likely be ammonia as fuels in industrial furnaces, in power plants, but mostly in shipping, because the ocean-going vessels cannot be electrified, and there is no need in that case to use a carbonous fuel. The density of ammonia is lower than that of hydrocarbon, but it's good enough for ships, if not for aircrafts. And then we're going to do methanol and synthetic hydrocarbon as electrofuels or feedstock for the chemical industry, methanol, but maybe also naphtha and others, and aviation. Electric kerosene could be used by the current aircraft. We don't need to wait for completely reshaping of the aviation with pure hydrogen, because this will take decades if it ever happens. But we can make sustainable fuels with hydrogen and sustainable carbon. What is sustainable carbon? It's carbon that is taken out from the air. It could be by mechanical means, but that's expensive and will probably remain too expensive. But we can do with biomass. And that's a very important thing, because if we combine the production of biofuels and that of electrofuels, we can make full use of the carbon that is in the biomass. In the biomass, you have much more carbon over hydrogen. You have a higher carbon to hydrogen ratio than you have in a liquid fuel. So a biomass plant that produces, for example, ethanol, is a source, is a powerful source of CO2 emissions. You can, and it's very concentrated. It's very easy to capture. And in fact, you add hydrogen to that, and you can produce 2 times, 3 times, maybe up to 4 times more sustainable fuels with the same biomass amount. That's very important, because you know there might be conflict between energy production and food production or biodiversity. So we don't want, it's not possible to do everything with biomass. Biofuels today produce less than 1 per mil of the aviation fuels. We can expand this to a few percent maybe, but not to 100%. So, but if we add hydrogen, green hydrogen into that, we can do much more. And finally, there is a use that has been mentioned already in this conference, which is to use hydrogen or sometimes ammonia as storable or shippable fuels within the power systems. But I'll be back to that I have a specialized slide. Now, you may notice I have not mentioned hydrogen or power to X fuels for delivering heat. And that's because it's not efficient. We should not do that. I heard that some hype or fans want to do that, but it's just crazy. From green power to heat via hydrogen, the range will be 50 to 60% at best. Now, if you use an electric heat pump, you will get 300% apparent efficiency. That is, for each kilowatt hour of electricity spent, you will have 3 kilowatt hour of heat inside your house. And if you do mechanical vapor recompression in industry, you will have up to 10 kilowatt hour per kilowatt hour of electricity. And then for high temperature industrial heat, you have very efficient processes now, electromagnetic technologies, electric arc heating, induction heating, dielectric heating like microwaves, direct resistance heating, electron beam heatings, and others. They are quite efficient. The trouble for some is that it's stressed on viable renewable energy sources. You may have a problem for some continuous processes, but then you can have innovative heat storage coming from the concentrating solar power plants in the spirit, but maybe with different materials and different technologies that will be able to turn viable renewable electricity into continued superheated air or steam at very high temperature. So we can electrify basically all electric processes. In transports, in ground transports, well, we might find a few niche markets with for hydrogen or power to X fuel, because the Lion batteries and new chemistries are making very rapid progress and cost reductions. So my take is that about more than 95% of ground transport job can be made with battery, and in some cases with electric road systems that can be overhead catenaries or rail, and could be made in some very highly, some portion of highways with very heavy traffic and help speed the recharging. The main point is that exactly like for heating, almost like for heating, the full electric traction chain is 3 to 5 times more effective than hydrogen or PTX fuel. And you have this in this graph from the Royal Society, where you look, you have renewable power at the beginning, and you look at all the losses to go to a battery electric vehicle. So you have losses, transmission, charging, motor, mechanical losses. You end up with basically 70% efficiency. If you do the same with fuel cell vehicle, you have transmission losses, electrolysis losses, very important, logistics and filling losses, not negligible at all. And then you have the fuel cell losses at the end, and the motor and mechanical losses, and you end up with 25% efficiency, basically almost 3 times less. And if you do power to X fuels, it's even worse. The losses multiply. You have the synthesis losses, etc., and you have the engine losses, like in any internal combustion engine system. So you end up at 15% best. Nevertheless, because you can do this and transport the fuel very easily from Morocco to Paris, just an example, maybe it's on a total cost of ownership basis, maybe it makes sense, but for very small portion of my consumption, range extender, the day where I want to cross France in a car, which is crazy because it's so much easier with a high-speed train, but if ever I have to do it for once, I need a range extender. I cannot wait to refill my battery. Okay, this happens from time to time. It's very small part of consumption. And then maybe it's just much less expensive to do that with an old internal combustion engine and a little e-gasoline that will not be very effective, but that will help from time to time. In shipping, now the consensus on ammonia in shipping is growing by the day because the marine internal combustion engines are very efficient, exactly as efficient as fuel cells, and they can be adapted to burn ammonia, so you don't need to replace all the traction chain in the big vessels, big container ships, bulk carriers, tankers, etc. And the first ammonia fuel ships are coming by 2025 or even earlier, I heard recently. But here you have a number of naval architects, shipbuilders, etc., that are doing this, and with the support of the company that manufacture the engines, such as MAN Energy Solution or Wärtsilä. The IEA thinks ammonia will provide half the maritime fuel by 2050. I think it's maybe a low estimate, and my personal vision in shares here is that basically green ammonia will produce the bulk by 2050. Blue ammonia is important in the meantime. Again, I'll come back to that, and LNG will not increase really much, and heavy fuel oil and very low sulfur fuel oil will almost disappear by this time in a net zero emission perspective. So the fuel use, the energy uses of ammonia will overcome its current feedstock uses. First, the use of nitrogen fertilizers may still increase, but it should decline over time as we move, because most of it is wasted in the fields. I know it's very important as a fertilizer. I know maybe some good colleagues from the OCP group are listening, but the fact is we need to use the nitrogen fertilizers more wisely and to reduce the waste that are not wasted for everybody and are not wasted for the ecosystems. We have a lot of issues with excess nitrogen from agriculture and cattle in the ecosystem. So we need to make this better. While the use of ammonia fuel will emerge as a main market in the future, driven by deep sea shipping decarbonization, but also other energy uses, mainly in the power sector. In those countries or smaller systems that are remote and that need to be delivered with a liquid fuel. And for that, ammonia will be the way to have a carbon-less and low carbon in the production liquid fuel. Also, maybe we'll use it for energy storage where we don't have geological options for pressurized hydrogen storage, and it's probably the best option for green energy seaborne trade. I'll be back to that. Note, please, that the cost of internationally traded conventional ammonia, natural gas based, has tripled since 2015. 19, sorry. In just 2 years, it went from $235 per ton to $746, and that's a major shift. So there are two options here, where it's a short-term things due to the post-pandemia recovery, etc. It will soon disappear. That's one possibility. Or it's a technical shift because now oil and gas companies have been said you should stop investing in new oil and gas field. It's time to go to renewables, and therefore the price of natural gas may remain high for 5 to 10 years before its uses really diminishes, and then the price will go down. But that means that in these 5 or 10 years, we may have very high costs for gray hydrogen and gray ammonia. And then that means that green or blue well, blue no, but green will be competitive much earlier than we thought just last year or 2 years ago. Hydrogen in power systems, that's an important point. Compressed hydrogen can be stored at length in saline cavities where available, and that's a cheap option. All other options are very expensive. And there is not so many other means of seasonal storage of green electricity. We have other means for weekly storage, daily storage, but seasonal storage. The way to go through what the German call the Dunkelflaute, the dark doldrums, the week with very low wind and sun in Northern Europe. There is not so many other ways. But if we don't have the saline cavity, then we would probably go to ammonia despite the conversion losses. And if we need to ship green hydrogen from Australia to Japan, from Morocco or Mauritania or Namibia to Northern Europe, we'll probably turn it into ammonia. Well, unless we have pipelines, which can transport hydrogen affordably, we'll have to turn it to ammonia if we want to put it on ocean-going vessels. Combustion of hydrogen or ammonia in thermal power plants will be required at the end of the decarbonization process of electricity production based on solar and wind. Just for these 10% of global of energy that is needed in times where you have little solar and wind. And this is not necessary in the European interconnected power system before 2035. So this need will happen, will emerge, but at the end of the decarbonization process, which of course is different in small grids, isolated grids, islands, landlocked mining areas, and Japan. Japan is an isolated grid, and they're already seeking to massively import green or blue hydrogen for its power system. And here is a need that has been expressed in the Japanese strategy, mostly as ammonia, because they come to the conclusion that it's the easy way.
Excuse me, Mr. Philpott. We would like to request you to wrap up soon because we're running out of time for the discussion.
Sure.
Thank you.
So, okay. I'll skip the aviation. I'll skip this. It's just to say, I won't go through it, but just to show there is a ladder of uses of hydrogen where you have competitors, electricity in most cases, biomass in few cases, and then you have a few uses where you have no competitors, so you have to go to hydrogen. One important aspect is that green hydrogen should really be made from water electrolysis with very low carbon electricity. That means if you're on grid, that means low carbon marginal kilowatt hour, not the average one. Because if ever you do produce hydrogen with electricity that is where the marginal kilowatt hours come from a CCGT fueled with natural gas, you have more gas than natural gas reforming, twice as much CO2 emissions than gray hydrogen. In that case, that's why blue hydrogen is a good option for the next 20 years probably, because it can bring in lots of relatively good hydrogen at a time where we don't have enough green hydrogen, at least in Europe, for example. If we import it from areas like Morocco, Namibia, Mauritania, Algeria, North Africa in general, or Africa in general, then provided it's countries that have already or that have decarbonized their own electricity production, then it makes sense to export if you have surplus. But in Europe, it doesn't make sense to produce green hydrogen with electricity before 2035, as shown. Green electricity should be directed first where it is most effective, and that's displacing coal in power is the most important thing, and then making hydrogen comes at the low end. of course, hydrogen would fare better if imported from better places. And as I said, that will be most likely, unless you can have, of course, pipes here, or using the existing pipes and filling them with hydrogen, that's fine. But if you have to go from other places, you will probably import hydrogen as in the form of their final use. Hydrogen will be, in most of the cases, being used to make ammonia, methanol, synthetic hydrocarbons, or metal iron. And you can transport ammonia, methanol, synthetic hydrocarbons, or even hot briquetted iron much more easily than you transport hydrogen. So you have to make this first transformation of hydrogen next to the hydrogen production places, and then you have a higher added value, and so it's better from all viewpoints to do this like this. I will stop here because I cannot, well, because I'm short of time now. Thank you very much for your attention.
Thank you very much for your talk, and I think because of the time, we will skip the direct questions to this talk and maybe handle them within the discussion. So I invite the panelists to join and ask their impressions and views on the talks made, and if they have some questions and opinions. And then within this, we'll also ask some of the questions, some of the general questions that were asked within this part of the session. Thank you. So okay, let's follow the order that's in the program. So Ms. Ogosa Erhanon, if you can give some opinions on some of the topics discussed this morning. I asked the panelists to maybe use maximum 4 minutes.
Okay, thank you so much, Dr. Sonia. Can you hear me okay? Yes, okay, great. Good morning, everyone, again, and thank you so much to the 3 other panelists that gave very insightful presentations. I don't really have much questions right now. I think maybe the first one I would have is to, I think, Dr. Chapik, and it was around the production of ammonia, and mentioned how the cost would necessarily reduce over time. And I wanted to know if that was subsequent to the price of green hydrogen actually reducing over time. Because I don't know, I think someone dropped in the chat and mentioned how obviously ammonia is going to feed into a lot of the agricultural practices, and obviously there's a food security, there's a security for infestation going on. How does that tally into the price of green ammonia in the future? I think would be my first question. I don't know how you want to work around this. Should I maybe raise everything up now, or wait till everyone takes a turn?
Maybe, I mean, if you don't really specifically have a question, if you don't specifically have a question, then you don't have to, but it's just maybe to mention, to have an opinion. I see some hands of other panelists raised. Yeah. So
I'll give the floor to them then.
So maybe they're the ones, they want to answer your question, or they have some opinion in this direction. Okay. So there's Mr. Meissner.
Yeah, thank you very much. As I pointed out in the chat already, I think one of the most important points of this morning discussion is the question, what could be the role of Morocco? And I must admit that I'm quite disappointed with the first, the conclusion of the first talk, that there is no perspective for hydrogen, green hydrogen, or whatever for Morocco. Because also the question was asked was whether this could be sustainable. And the answer, as I understood it at least, was mainly it's too big for Morocco. Morocco should concentrate on solving its own problems before the market. This cannot be the answer, of course. The world will change, and this is a big issue, as has been pointed out also by the other talks, actually, and especially the last talk. I think Professor Philippe nicely explained how big the perspective of green ammonia is. And also in the other talks, it turned out that the main cost factor actually is the cost of electricity. And looking at the world now, really from the other side of the perspective, Morocco is one of the places in the world where the cheapest green electricity can be produced, and thereby, of course, also the cheapest green ammonia. And it's really needed for transportation sector, especially for shipping. And my idea of the future would really be that Morocco may become the fuel station for ships of Europe. We will have a lot of sea transport in the future also between Europe and Asia and America and wherever. And these ships have to be fueled. And the cheapest fueling station could be Morocco. So I think there can be a very, very big opportunity for Morocco. And of course, it's sustainable because this will for a long time be the source of transportation energy, in my opinion. And therefore, every investment in this direction in Morocco should turn out to be very useful. Thank you very much.
I can answer if you allowed me to do so. Hello?
Yes.
Yeah.
Sorry, yes, please. I muted myself.
Thank you very much for your question. And I understand absolutely your position from European view, that German people, they are looking for cheap energy and especially hydrogen, and they are looking to receive it from other countries. And I understand it really very well.
The world.
Yes, but my perspective is Moroccan. And I will ask you one stupid question. Do you know the position of Morocco regarding the water situation?
Of water and clean water is a problem of energy. So of course you can, by desalinization.
If you know the problem regarding the water situation in Morocco and the dump right now, and the last report that has been written 1 month ago, the dump they need more, the situation right now is 35% of water only. And the situation, especially in, for example, in Agadir, that the groundwater is decreasing every year by 15 meters. And the situation is dramatic regarding water. When we will have opportunity to develop technology which uses salty water coming from ocean directly, not by transforming it to drinking water, because if you do it like green water and after you produce hydrogen, this is absolutely nonsense with the need of Moroccan people that they need water.
Yeah, thank you. If I may,
very critical and very important issue.
Thank you very much. I must intervene in order also to give also another Moroccan voice about this. It's not about having contradictions, etc., but it's also about explaining or expressing opinions. Okay, so my name is Samir Rashidi. I'm from IRSEC'21. And I also would like to have some to thank also our esteemed panelists and speakers, Professor Shawki our friend of Morocco, Cedric, and Tariq, Professor Tariq, who is also known in the research area here in Morocco. To be really quick, and also to have also another position that is somehow different from the position of Professor Shawki on this, and to answer first of all for the question of water. What we defend, or what we are orienting our recommendations for Morocco is to not to use, for example, sites like Ouarzazate or sites like that are inland, because there is a problem of water, of course. And the idea is to all the PTX, where we are also doing some Atlas, PTX Atlas, where those large scale, I mean, power plants will happen, will be on the seaside, mainly. For the water, for the power to X, I mean, application, the water desalinated will be produced at a really low cost, at a marginal cost. The cost of the liter of water is less than 2% of the cost of kilogram of hydrogen, of green hydrogen. So this is really low, and those large power plants will help, on the contrary, to afford desalinated water at a cheap price for the communities. So this is the first one. Second one, and also as a Moroccan citizen, I would give the example of the automobile industry and the aircraft industry. Morocco doesn't use all the cars that is producing. He exports. So by exporting, it's not like okay, we give service to other countries, but this is what economy is about. It's about exchanging. I sell you something, you sell me something, and this is life. So when Morocco will have an industry to export green molecules, it will add on to his GDP. He can grow. He can solve problems of education, of health, of poverty, and this is also sustainable development. So this is the second point. Third point is also, beside the export thing, this opportunity, as we see it as a research institute, will help to create even more value in the country. How? Because we won't only use the green electron, we will integrate vertically the value within our economy. We will use the electron, we will have electrolyzers that produce hydrogen, we will have Haber-Bosch reactors, we will have hydrogenation reactors for LOHC, for example, we will have methanol reactor, etc. So we will have industry, green industry, sustainable jobs, sustainable development. And last but not least, to also to moderate my purpose here, or my statement. It's not for tomorrow, and with this I am also okay with Professor Shawki. It's not for tomorrow, but we need to start now. And how we start now, I will speak about it later in my presentation, around 1:20 probably. But we started to prepare the ground in terms of studies, logistics, infrastructure, regulation, but also R&D and innovation. And with this, I would like to finish my statement and giving you an appointment or a rendezvous in few hours to discuss, to present you the view of IRSEC about innovation for green hydrogen. Thank you very much.
Thank you very much for this comprehensive view regarding the issue of water, because this has also been quite a big, quite a big topic of interest in the questions about whether it's possible to use seawater or wastewater for electrolysis, and how to minimize the consumption of water by electrolysis. I think also for those who are doing research and development, this is something to have at the back of their minds, that these are really the technologies to be looked at in the near future, so that also the general populace in Morocco has a positive effect, perspective towards hydrogen, that they're not competing for water with exports, water for livelihood versus water for exports. This is not a scenario that I think is wanted.
I'm sorry, it always be competition with water right now, since we are not using seawater directly. I'm still convinced on that. first. Second, to increase the GDP, if you look at, they have very nice relationship between GDP and use of direct electricity around the world, direct correlation. And if we wanted to increase the GDP, we should allow people to use that electricity, which is cheap, to other uses than having hydrogen and export it to other countries. Is better to use it locally for the citizen to improve their lives.
If I may say a word on this, there is largely enough for doing both. Why oppose the two things? I mean, you have
because it's very huge. We're talking about huge investment. I understand the European situation. The European situation, they need absolutely to decrease their CO2 emissions. And they don't do it on behalf or in Moroccan countries or African countries. They have to look at themselves how to decrease independently and to produce energy somehow without, exporting the emissions to Africa. This is what I'm talking about.
You will not export emissions if you do green electricity and green hydrogen and green ammonia in Africa. Even
but you wanted to do it in your place. This is the problem.
Sorry?
You have European countries or developing countries, you wanted to do this producing hydrogen in our countries rather than producing on site.
This because of cost. Because of cost.
We want to buy green products, green ammonia, green iron, green methanol, green hydrocarbons, instead of buying, as we do, gray ammonia, gray natural gas, gray oil, gray coal. Well, we have some gray coal from other countries. And as always, there is room for making this profitable for both parties, like all kind of trade based on the different competitive advantage of the nations. So you can have spoliations, that's true. You can have colonialism, that's true. And you can also make it sound and clear and helpful for both parts. And that's what we should do together. Thank you.
Okay, thanks. I saw some other hands. Maybe
probably just
wants to say something.
Yeah,
yes,
one last thing, and I will leave. For sorry, I don't want to be a dialogue but just to because we have been involved in the studies that were carried in Morocco about that, and they will just correct something. When we speak about and I joined Cedric for this point, when we speak about capacity green electricity for green hydrogen, this should be understood as independent from the local grid. As Cedric Philibert said, and you can all consult the roadmap, the green hydrogen roadmap that was published last week by the Ministry of Energy, and you see the data. We have an outstanding, I would say, outstanding again, third time, a renewable potential, both for wind and for solar. Solar gives you the lowest cost of electricity, and wind give you the load factor that Mr. Professor Shawki was speaking about. So we really have enough for us and for the industry. Second thing, and the green hydrogen should not, be involved in the local grid. This is our recommendation from the studies we put. So this is because it will be costly if we involve the grid. It will be also not green if we involve the grid. And for certification and guarantees of origin, this is something that is difficult. Last but not least, the point of investment. This is something that also was really clear when we were establishing the roadmap for hydrogen in Morocco, and we were talking with the stakeholders. All of them were saying Morocco should not be, the government of Morocco should not be involved in investing in this for the moment. The government need to prepare the ground, infrastructure, regulation, training, etc. And the private sector will do it when it is beneficial. Of course, we need some encouragement at higher level, but this is where I join Professor Shawki. Europeans should play their role because they are the ones that need hydrogen. So they need to find some carbon taxes, some premium prices, some quotas for green hydrogen that is coming from Morocco, but this is a win-win, win-win. Morocco, just to recall you, exported around 10 billion of euros worth of car industry. We don't need car industry, but those exports adds to GDP. So when you will have green hydrogen, you will have added GDP for industry for renewables, industry for electrolyzers, industry for green chemistry, and you will have jobs. So you will just have your cake bigger, and the cost of electricity will drop because we will have economy of scale. Just to give you a feedback, we have the 2 million tons of OCP needs around 6 gigawatt of electricity, of renewable electricity, of electrolysis capacity, sorry. So this is a huge market, and it will be even more than what we have in renewables in our grid. So this is not something that is competing with local electricity. This is something complementing that should be developed. But we need to start at a small scale and to acquire data. And I will be speaking about this later in this morning. Thank you very much.
Thanks, Mr. Dabi. I see your hand's been up for some time.
Yeah, thank you, thank you. I'm not hydrogen, but I'm associate professor in Mohammed Sis Polytechnic University, working on the lithium-ion batteries, energy storage. So I have two questions. One is addressed to Professor Shawki, and the second question will be addressed to Dr. Samir and Professor Cedric. So the first question, in order to assume the huge needs of OCP, especially for the ammonia production, can we use the seawater in electrolysis? This is my first question to Professor Shawki. The second question, in order to answer to the needs for hydrogen to Europe, so I have my question, why not to export the electricity? Because we have the desert, we have the sun, so we can export the electricity to Europe because you compare Japan to Australia, they are so far. But Europe and Morocco on MENA region is too close, so we can export the electricity and then you have the water and you can do the hydrogen by yourself. Thank you.
Yeah, I will try to answer your first question. Thank you very much, Moad. It's very, very hot topic right now, and this is where the research has to be involved heavily, and especially in Morocco, for example, by trying to produce this hydrogen by using directly the seawater. This is very, very open question, and this will be the future. In that case, that will be, of course, one of the greatest opportunity for Morocco to develop its energy field sector. Sorry, it's very, very critical and very, very important issue. Yes.
Okay, so I saw Miss
Ahon's
hand up, and then afterwards we'll have Mr. Rashidi, and I think then we have to end the session.
Thank you so much. So I think maybe just joining together everything that has been said, I would maybe just like to say that there is an opportunity cost to everything, you know, and I think one thing that's been mentioned is green hydrogen isn't happening now. What we're doing now is preparing the grounds. And as Mr. Surma has actually mentioned, this is the time for governments, which Moroccan government has been doing an amazing job with, is to create regulations, create an enabling environment. And this enabling environment involves the process of clean water, involves mitigating between countries in Africa on who has the best water, who has the best technologies. And I think that's the kind of conversations that we should be going around now. Admittedly, some developed nations in Europe, in Americans, in Asia do require green hydrogen for their decarbonization processes. Africa has the potential to match this demand. We just have to work a bit more collectively. In Nigeria at the moment, we're actually developing roadmap similar to what Morocco published last week, which was fantastic, by the way. And something that, like, I always feel the misconception that we get is that we don't need green hydrogen, we need power. But this is the shocker. To actually meet the exportation and the requirements for the global market for green hydrogen, Africa is going to get more electrified. It's going to involve powering up industries, powering up homes, powering up African communities, because we would have to invest in renewable energy. And I think the idea that I'm trying to avoid people making is jumping the gun, right? So the first thing we have to do right now in this coming years before 2030, when decarbonization has really met its mark, is investing in renewable energies, investing in our water capacity, resolving or getting resolutions to the water wars across Africa. And those are just really the first conversation. So I think maybe out of everything that was said today, the grand total, and before I share more about my own thoughts on the energy transition in Africa through green hydrogen tomorrow, is that this is an opportunity that Africa has to increase the global, their domestic, gross domestic product, the GDPs, the economic structure, while going through a sustainable development. So thank you so much for all the questions that have been raised. It's very insightful because things are coming from a very scientific view as well. So thanks, hope that was helpful.
Okay, thanks very much to the panelists for this lively debate. And I think it's quite interesting. So maybe let's immediately move on to the next discussion, because the next sessions and talks, and then I think there'll still be more.
You can add 5 or 10 to 10 minutes discussion before
the next session. Is that okay?
Next session. The first presentation will be the president of Professor Dieter.
Sorry, we cannot hear you.
We can continue 5 to 10 minutes discussion.
Okay, I had a different information.
The hot topic, I think, need more discussion from panelists and attendees.
Okay, thanks to the organizers for giving us some more time. I think I saw Mr. Rashidi's hand up, and then maybe he put it down because he thought we were running out of time, but maybe he's changed his mind. And
no, I just forgot to lower my hand. Thank you very much. I think I have pointed out all what I had to say. Thank you very much. Thank you.
Okay, thank you. So then there is Mr. Philbert. Do you have something to say, or that's a forgotten hand?
No, I wanted to respond to Mr. Dabi about electricity interconnection. I think that's fine as well. But if you have important amount of energy transfer, then pipelines, because it's all, I mean, you also have pipelines between North Africa and Europe, and pipelines can transport more energy at a lower cost as hydrogen or as ammonia than electric wires. So we need both. We need to develop the interconnection to get green electricity and to provide North Africa with more capacity, maybe because it's an exchange, in fact, of energy versus capacity to avoid blackouts, etc. But we can have both, and we should not oppose them. I also wanted to make a small comment to my friend Samir. I agree that the dynamics behind the development of green hydrogen and in Africa, in Morocco, is different than the decarbonization of the own own grid, and has to be supported by the beneficiaries of this green hydrogen, of course. And it should not be linked in the sense that these electrolyzers should not take electricity from the grid, because there is a high risk that they take marginal electricity that will be from coal or oil in Morocco, not so much gas, but coal, which is even worse. And we would have much more emissions than if we just take gray hydrogen from the market. So that would be a terrible mistake indeed. On the other hand, I think the renewable capacities that should be developed to produce this green hydrogen should still be linked to the grid and serve in times of relatively low wind or very high demand, because the hydrogen production is flexible in the electrolyzers. And when you have too little, if you have 6 gigawatt capacities additional, you still have more energy, and so you can reduce your use of fossil fuels. So I think this issue of linking the capacities mostly built for exports and the capacities of the country itself should be thought more precisely, because there is a way to make it help your decarbonization agenda, speed it up, and making it better. Thank you very much for the opportunity to add some views. Thank you.
Okay, thanks very much to all the panelists and all the presenters of the previous sessions, as well as to the audience and participants.
I have a comment, if you allow me, if we still have some minutes.
Okay, very quick, please.
Yeah, very quickly. So since I think it is about the story of South Africa with respect to the apartheid issue, when they were not allowed to get fuel from outside, so they make use of their coal at that time, and they make use basically with the process of Fischer Tropsch. And I am thinking also about this example for Morocco as a safe example for making use of this hydrogen, green hydrogen, why not? And also with the CO2 released from different industry, to try produce and to develop locally infrastructure for producing kerosene for planes and things like this. And I think the market is there, and the storage is more safer, and also the transportation also is more appropriate. So this is, of course, as the Professor Shawki mentioned, also with respect to ammonia, I think OCP will have the capacity and the competencies needed to develop ammonia production if they seek convenient solution regarding this issue. So that was my comment regarding this as a catalyst process, because this solution, both of these solutions, they involve very much catalysis. And also I'm thinking about photocatalysis, because with photocatalysis we can also make use of this, solve the problem of the used water, and the used water also could be used as a feedstock for also producing hydrogen. So these are some solutions that we have to establish priorities with respect to the available state of art with respect to these different technologies. So that was my comment. Thank you.
Okay.
I want to just add very quickly one thing regarding what Tariq was saying. Thank you very much, Tariq. It's very interesting what you have said. But I just wanted to mention that what I was trying to answer is regarding Morocco. It's not regarding any companies, including, of course, OCP. And my presentation was clear. If OCP wanted to go to produce ammonia and things like that, they are able to look at what's the capex, opex, and everything, and they will go for it or not. This is their, business. But my question was absolutely relative to Morocco rather than specific company.
Okay, I think we have to move on to the next discussions. And
excuse me, Professor Dieter, I think raising his hand to give his.
Yes, he's the next speaker.
Okay. Yes, talk is
so he's probably asking when he will start. I don't know.
The talk is scheduled for 10:20. So I think we still have 7 minutes to go. I just would like to make another comment from the outside concerning the role of Morocco. I think Africa should not make the same mistake as it did, or it was not really the mistake of Africa, but of the colonial states, actually, to use Africa as a source for resource and basic materials only. The profit is later in the value chain, and the more Africa can produce final products, the more the profit will stay in Africa, of course. This is why I was talking about Morocco as the fueling station. So if you can sell fuel, it will, of course, bring much more profit than just exporting green hydrogen or even green electricity. And as we discussed in Samir's excellent introductory lecture already, there are other final products like green concrete and green steel, which I think Morocco can think about having already heavy industry and having all the potential with good education and so on to develop more industry. So produce final products rather than raw materials is just my comment. Thank you very much.
Especially true as the bulk of the forthcoming steel demand is in Africa rather than in Europe. So our responsibility is to help establish a green steel making industry in Africa. And then you don't have issues of transporting hydrogen over long distance.
Thank you very much. Yeah.
Okay. Thanks. It looks like that discussion has come to not a permanent end, but a temporary end, so that we get some more insights from the next few talks. And I see there are also some that are including techno-economic analysis. So maybe this brings us forward. So the next talk is by Professor Dieter Meissner from Estonia, I think. And yes, Tallinn University. I knew it was Tallinn, but I wasn't sure of the country. And he will talk about some work on membranes for solar water splitting. And the floor is yours. Thank you.
Thank you very much. The talk has been recorded, and I think the recording should be played here.
Okay,
actually,
thanks.
I'm a German living in Austria and having a university position in Tallinn, Estonia. So I'm European, probably. The paper is dedicated to 4 excellent. Dear colleagues, ladies and gentlemen, this paper is dedicated to 4 excellent scientists, 2 of them also co-authoring the paper, who had to leave us forever. Elham Kouhi Isfahani, probably the most gifted PhD student I ever was lucky to supervise. Professor Renate Hiesken, for 30 years a close collaborator and very close friend. My dear friend academician N. Melikov, the father of our monograin growth technology. And my former supervisor and boss for 10 years, Professor Rüdiger Memming, together with Professor Heinz Gehrischer, father of photoelectrochemistry, the investigation of charge transfer at the semiconductor electrolyte interface. The paper reports our latest results from a field which accompanied me now for already 40 years, the direct solar hydrogen generation using monograin membranes. Monograin membranes allow the combination of ultra-low-cost printing technologies to produce photovoltaic modules with the use of highest quality and very stable single crystalline semiconductor grains of a few 10 micrometer in size, deposited as monolayers. This technology is currently used in crystal sol.
a spin-out company I founded in 2008 to print endless stripes of photovoltaic modules. As I have demonstrated already in my diploma thesis 40 years ago, these monograin membranes can be produced so that every little single crystal sticks out on both sides of the membrane. Thereby, they can be modified or contacted differently on both sides by coating techniques. So they can be used as photocathodes or anodes on the illuminated front side, and as anodes or cathodes respectively on the back side. Between two electrolyte compartments, they allow the spatially separated evolution of hydrogen and oxygen. To allow current flow between these electrolytes and use one side for the production of hydrogen while at the opposite side producing oxygen, ion flux is needed between these electrolytes. In our biological model, the photosynthetic thylakoid membranes, ion channels are embedded to close the electric circuits. To mimic this structure, Elham mixed the glue polyurethane, prepared from the biocomponents desmodur and desmophane, with droplets of the very common proton exchange polymer Aquivion, a perfluorinated sulfonic acid. However, when using these membranes to separate two metal electrodes in their electrolytes, it turned out that the ionic conductivity of these membranes was quite low, but it increased by current flow between the water-splitting metal electrodes over about 30 minutes. A closer look at this improvement revealed a stepwise current increase as shown in the figure. The step width here is a few seconds, followed by a very fast increase of the current density, here by about 15 microamp per square centimeter. We attribute these steps to the consecutive opening of ionically conductive channels in the membrane, one by one adding their contribution to the overall conductivity. Detailed electrical and structural investigations were performed using conductivity, impedance, SEM-EDX, and mainly AFM investigations and are reported in our paper. In summary, from a fundamental point of view, most important is the detection of point-sized current channels by conductive AFM imaging and their microscopically observable consecutive opening, leading to a stepwise increase of the membrane conductivity, for the first time reported here. Thank you very much for your attention.
Thanks very much for for keeping time and also for the very interesting talk. Unfortunately, I lost contact with the conference for some minutes, but I think that there are no extra questions. I'm not sure. Maybe I missed them, but I cannot see questions directly relating to this talk. So if there is 1 minute chance to ask. Somebody is trying to ask, but I cannot hear them. Okay, maybe it's background sound. So thank you very much again. And let's move on to the next talk by Aisha Ojidi. I hope I have the name right. From the Euromed Research Center at the Euro-Mediterranean University in Fez, Morocco. You're welcome, please.
With the population growth, the energy needs and the production of municipal waste resulting are increasing more and more. In one hand, the energy needs are met by fossil fuel in large quantities, which leads to many environmental problems. Hydrogen, however, is a promising green fuel because of its high calorific potential, its renewability, and the non-emission of greenhouse gases. In the other hand, 70% of Morocco's household waste is fermentable and is disposed in uncontrolled landfills. That creates many noticeable problems, such as leachate and the contamination of surface and groundwater. Ladies and gentlemen, greetings. My name is Aisha Ojidi, and I am going to present to you my research entitled Technical Economic Evaluation of the Potential of Municipal Leachate for Biohydrogen Production in Morocco, Fez Area Case Study. In this research, we tried to analyze the situation of household waste in Morocco and to determine the area to work on in order to study the hydrogen production from the fermentable fraction of household waste and the leachate resulting. Morocco's household waste is dominated by organic matter, which accounts for about 70% of the total weight. The calculation of the household waste production in each region is realized in order to choose our case study area. Also, to know the evolution of our raw material in the coming years. Thus, it is found that the most important potentials are those of Grand Casablanca Stad, Rabat Saleh Kenitra, and Fez Meknes. Also, after taking into consideration these main criteria, the controlled landfill of Fez seems an adapted choice for our study. There are several methods that allow the calculation of leachate production in the landfill. The model chosen in our case is the production estimate using the water balance represented in this formula, and the results are presented in the table below. After the analysis of the composition of the household waste in Morocco as well as of the leachates, it is well noted that our raw material is rather wet and requires a treatment by photofermentation or dark fermentation. It is noted that the landfill of Fez presents production potentialities as well as important loads in organic matter. On the other hand, the absence of chemical analysis of glucose and total organic carbon, which is the basis of hydrogen production from waste under anaerobic conditions, led us to make assumptions on the amount of glucose present in the leachate to facilitate the sizing and design of bioreactors. On the other hand, by comparing the physicochemical parameters of the leachate with the values of hydrogen production, it can be concluded that the leachate of the year 2019 has favorable values of pH, nitrogen and phosphorus for a good production of hydrogen. Moving to the simulation using the SuperPro Designer software that will allow us to see the project feasibility via the different balances. The main substrate at the input of the software is glucose, which represents 2.5% of the initial composition of the leachate. The daily flow of the leachate at the landfill of Fez is estimated at 400 meter cubics per day. The first bioreactor for hydrogen production consists of a dark fermentation from two substrates, glucose and water, according to the following reaction. In order to increase the production of biohydrogen, a photofermentation bioreactor is added. It allows the conversion of fatty acids from dark fermentation into biohydrogen according to the second reaction. And the simulation allows us to produce approximately 400 kilograms per year of biohydrogen. The production of hydrogen from municipal leachate presents a solution to help remedy the energy problems, especially since Morocco has adopted in its national strategy for energy transition hydrogen as an energy carrier. It is also a solution to help remedy the environmental issues, especially to lower the greenhouse gases emission and act to limit the climate change. Finally, I would like to thank the organizing committee of the IRSEC and everyone who made this project possible. Thank you so much.
Thank you very much for this talk. And I ask again if there are questions to put them in the Q&A, and this will be sorted out during the discussion. So the next talk is by Nada Rifai from University of Moula Ismail Meknes in Morocco. The floor is yours, please.
Hello, today I'm gonna present the paper proposed for the IRSEC conference entitled Physiologic-Based Energy Management Strategy for Fuel Cell Supercapacitor Vehicles. Fuel cell vehicles have become a research focus for most automotive manufacturers around the world, especially for their ability to address the pollution problems associated with internal combustion engine vehicles. So hybridization has shown its effectiveness in overcoming these problems. Highly efficient online energy management strategies are then required in real-world application. This paper proposes an online energy management strategy based on a physiologic approach, which aims to increase the lifetime of the sources by respecting two major constraints. First, the low response of the fuel cell and the supercapacitor state of charge. The physiologic controller has two The physiologic controller shows good results during the simulation. So, a physiologic-based energy management strategy has been proposed for the regeneration of the reference power for fuel cell and supercapacitor according to its different dynamics. So here the fuel approach is preferred to neural networks in order to avoid dealing with the learning of neural network problems and to have a continuity from local to global behavior. Physiologic rules also allow to keep a minimum of human analysis possible in the optimization phase. So in this paper, the Mamdani-Fuzzy interference system have been applied since it have the most intuitive and easily understood rule-based. So the energy management is based on a set of if-then rules. So the Mamdani's Fuzzy system defines a function f that generates numerical inputs u from input values x. The trapezoidal membership functions and centroid diffusification method are adopted. This method determines the center of area of fuzzy set and return the corresponding crisp value. So we have 20 rules that are presented in table 2 in this table, and they cover all the working conditions of fuel cell and state of charge and supercapacitor under varying load conditions. For example, the first 4 rules shows the power provided by the fuel cell and supercapacitor under negative load conditions. This situation depicts the condition of a vehicle when brakes are applied. Under this scenario, the regenerative energy has been used to charge the supercapacitor, and as it has low state of charge, while the ultracapacitor remains idle as it has high state of charge. The fuel cell's power remains at its minimum limit. If the state of charge is fully charged, if the supercapacitor is fully charged, the remaining energy will be used for the auxiliaries. In this paper, an energy management strategy has been proposed for the fuel cell and supercapacitor hybrid energy storage system of electric vehicles. The aim of this energy management strategy is to deal with peak power demand and sudden variation by using fuzzy logic approach. Simulation shows good results for reducing stress on the fuel cell and thus increasing times. The perspectives of this work is to validate this approach based on a test bench experimental study. Thank you for your attention.
Thank you. Thank you, Mr. Rafai, for the talk. And are there any questions? I see there is a question. There is a question asking something about whether the same elements at the beginning of the reaction are the same for the simulation process. And it's not quite clear what the question is about, but I think they want to know if you used the same elements for the reaction that you showed earlier for the simulation or not.
Hello, everybody. I'm Nada. So the question is for me?
Yes, yes, of course. It's for your talk.
Yes, but I didn't understand the question. So
okay, I think the person wanted to ask whether the inputs for your simulation were similar to the reaction that you showed somewhere at the beginning. Alternatively, you can, if you can access the question and answer board, you could type live. You could type the answer there because it's not so clear.
Yes, if the person can re-ask the question more clearly, I can answer. But here I don't understand about which elements they are talking.
Yes, please, maybe then you can go to the question and answer board, and then
yes, of course,
ask from there, or to the chat, or maybe whoever asked, Zara and Nifa, could also send you a chat. I don't know if participants are allowed to chat with each other.
Yes, because on the board I cannot see the question.
Okay, so thanks to the three speakers for these talks, which are going now a little bit into details in the different technologies that would be helpful to realizing green hydrogen production. And once again, I invite the panelists back and the previous speakers to discuss on their opinions of maybe these research developments, and of course, overall in the grand scheme of the perspectives for green hydrogen development.
Can I just apologize for presenting such a specialized paper after such a nice general discussion? I think what is important here, as Professor Philibert already pointed out, the direct water splitting by solar energy, of course, is a very interesting topic, but it's still in the fundamental research field. So before really using this to improve the situation of Morocco or whatever, there's a lot of fundamental research to be done, even after 40 years of development. And in the last years, very big projects worldwide going on. However, I think the important message here is mainly you can write down nicely chemical equations which are very simple, like it was also done in the talk by Aisha on the photofermentation. However, to realize this in the practical system is a quite complicated story, of course, and requires a lot of work. And it may turn out that this is really not cost effective. So concerning the direct water splitting after 40 years, I must say we have a very nice system to do this. These monograin membranes can be produced in very large scale for very low costs, actually, and they can be used in this respect. However, there are still lots of basic problems to be solved, and it will take probably another 5 to 10 years to really develop this technology. Thank you.
Thanks. Are there any other comments? I've got one if there's. What I found interesting was after this talk about the issue of water use for electrolysis, then came the talk about the use of leachate. And this I find quite interesting because it's also one of the potential technologies in the far future that would help to alleviate this issue of using so-called sweet water for a technological use, and yet they're also human uses. So I think following on the previous panel discussion, I think that, of course, with all the problems that are also present in Morocco and all these other areas where we hope to be able to get green hydrogen, it's on the, let's say, the end users of this green hydrogen in Europe, the US, Japan, and so on, to already start to look for also some sort of new methods to use alternative sources of water and reduce the costs. I think mainly it's a question of cost, as was already also mentioned by Mr. Rashidi, that, okay, they are not using the solar energy in the desert and they're putting everything on the coast, but there's a lot of area in the desert. And if there was some way to reduce water consumption or find other uses, other water sources that don't directly compete with human needs, basic human needs, then this would also be a good thing. I see some additional questions.
I invite keynote and panelists to give questions.
They didn't seem to be any, unless, and this is where I'd moved on to now the Q&A, just to fill up the time. So if the organizers can allow, there is a question for somebody from the audience, to Nadia, and they're asking what type of fuzzy logic control can be used for the work that you described. Is this Mamdani type or some other? Well, okay, she says that she used the Mamdani type of fuzzy logic. Thank you, Nadia.
I think Professor Deser won't raising his hand.
Ah, good. Let's see.
Yeah, thank you very much.
Oh, yes.
I think one of the most controversial and most interesting discussions going on in the whole field, actually, and this is also connected to use of biomass and the leachant and so on, every of these waste utilizations is the question: what is really the source of energy or the source of fuels in the future, and what might be the contribution of biomass in total. As has been pointed out already, the main problem of biomass production is the low efficiency of photosynthesis, of course, which means you need large land areas to actually produce biomass. And of course, biomass production will compete with food production since it needs fertile land. It will compete with decarbonization because fertile land, of course, can be used and is used by forests and so on, and swamps to sequester CO2 from the atmosphere, and it's competing, of course, with freshwater use because you need fresh water. So in my opinion, biomass actually has a very difficult position. It has been the energy source of the past, of course, when we were all burning forests to heat our houses, but whether it really be the source of the future, I have some serious doubts, especially since photovoltaics is much more efficient in area use and today also much cheaper. Thank you. So a very statement which nobody likes to answer, but yeah.
Yeah, I suppose sometimes there are really no answers, direct answers, but the good thing is that that others get to know that there are other views upon certain things. And I must say that I always thought it was of, oh, Mr. Rashidi wants to say something. Please. You're muted.
Yes,
Okay.
sorry, I was trying to unmute myself. Yeah, I don't have a question relatively to the colleagues that just presented about the talks, and I would like also to congratulate the students that are also working on this innovative subject. I have a question to Professor Maxner. I don't know if it's the opportunity or the place to ask such questions, but we are really interested in water splitting in Morocco, because we think this is also some very promising technology. But I wanted to ask you what is your vision or what are your insights about the upscaling of the technology, because from what I could have seen in my readings, sorry, we still have we can have some modules that are small or big, but in terms of capacities, if we would like to speak about kilowatts, megawatts, what would be your perspective? Would it happen in 5-10 years? Because it's really it can be really a game-changing technology for the deployment of hydrogen. Thank you very much, Professor Meissner, in advance.
Thank you very much for asking me this question. As I pointed out, the production of these monograin membranes, which are suitable for doing this, is very low cost. But this, of course, makes it a very interesting material for electricity production also. And concerning the overall cost of different approaches, I think Dr. Kalnan can answer this much better, because she was heading a big project in which different technologies have been compared to directly electrolyze water. And one of the questions asked in this project was exactly how economic are these things. So maybe I can pass this on to our moderator. Thank you.
The question is, it's a very difficult question regarding the economics, but I must say the reason why, for the reasons being that a lot of the technologies or the equipment is still made on relatively small scale. And so if the capacities or the factories for building all these electrolyzers would, and the related components would be made as big as, let's say, the car industry, then the cost of this equipment would come down, and then eventually also the cost of hydrogen generation would come down. Another thing that's very important, and I think this is why there's been the push to have green hydrogen produced in areas with a high solar resource or high wind resource, is that the initial cost of the electricity also plays a role. And of course, the initial energy resource. So of course, sunny places will lead to a lower cost of hydrogen if production than places further away from the equator. And so this is really, for a given equipment, it also depends on the location. So the cost of hydrogen production would depend also on where this equipment is located. And so it's not an easy question. There are a lot of factors and also a lot of figures that are put out there in the literature. You have to look at them under what context the calculations were made and what assumptions. But actually in certain places, the target cost of below $2 per kilogram of hydrogen can be reached if you have a big enough system with some 100 megawatts and a really cheap primary energy resource like, say, wind or solar. This could already be possible at cost at the production site. In the end, what is required is a lot of research on scaling everything up so that we achieve economies of scale.
But have you an idea about the timeline, dear Sonia, or no? It's the $1 million question.
Luckily for me, last week I presented something like this, and for some of these very big systems where you have really, let's say, 100 megawatts of solar panels sitting in a desert area with a good water supply with electrolysis, I think within the next, by 2030, the cost will be really competitive compared to other sources of hydrogen, let's say steam methane reforming. And this is why there are also quite a lot of big projects where there is green hydrogen production at the user plant. So at steel mills, and I've seen also mainly at steel mills, but also at cement plants, and also at refueling stations. And these are really the projects that will show that it's feasible to do green hydrogen in really thousands of metric tons per year. And it's cheapest if this is done at directly where the user is, so that you avoid all these problems with transportation.
Just a word of warning from my side. This is talking about the direct combination of photovoltaic modules with electrolysis, of course. This is not photoelectrochemistry as I defined it or used it and researched it.
Yes.
So photoelectrochemistry will have a much longer time.
Yes. Now that you say this, I think I will add something else to my slides, although it was a little bit outside the project that I will discuss tomorrow. But for things like photocatalysis and photoelectrochemistry, these will really take much longer than anything that's using electrolysis, because for most of them, the biggest problem right now is the lifetime of the devices is few hours or few days, and we really need something that's lasting 25 years or so for it to make economic sense for anybody to want to invest in it. And so this is really the challenge for the people in the labs. But this is something that will be discussed tomorrow.
Thank you very much, Dr. Sonia, for sharing this.
Thank you very much, dear colleague. Thank you very much for the explanation.
Thank you very much for keynote speakers, Professor Jamal Shouki, Professor Tariq Shafiq, Mr. Cedric Philibert. Your talk is really very attractive. About 300 participants follow us on Zoom, without considering other followers via YouTube and Facebook. Now I think time to close this session. We have a break before starting the next section is section 4. Thank you very much for all panelists. Thank you very much for Dr. Samir Rashidi, for all other, for Yassin Nasiri from Mazen, Yunus Feidi from Mazen also, Ismail Bilhaj from Mazen, for to be with us in this conference. Thank you for all attendees and all authors of paper. Thank you also for our really interesting presenter, Professor Dieter Misner. I think the time to close this session. Thank you very much.
Thank you.
Thank you all. Thank you.
Thank you for the nice discussion. Very interesting.
Thank you.
Thank you. Thank you.
Thank you very much. Thank you, and see you in the afternoon. Thank you.
Yes, thank you all for the chance to moderate, and also for the very lively participation of the hosts and panelists. Thanks a lot, and also thanks very much to the participants.
Thank you.
Okay, bye-bye.
Hello, everybody.
Good morning, good evening.
Hello. Good morning. Good morning from my side.
Good morning, Professor Orlando.
How are you?
This time, good morning. And
Yeah.
I think we will start
Okay.
the workshop, the second part of this workshop. This will be chaired by Professor Ibrahim Bilhamou from University, professor at University of Marrakesh. Qadi Ayad, Marrakesh. Thank you very much for accepting to share this session. The floor is yours.
Okay, thank you, Professor Zaz. Just Sizaid. Sizaid كتسمعني؟ إلا عندي مشكل لقاش أنا في الدار إلا عندي مشكل ديال الواي فاي عافاك إلا تقطع عندي خذ أنت.
Okay, no problem, Professor. Okay,
thank you. Okay, so this is the third part of this workshop for sustainable energy for buildings and urban environments. It is my pleasure to chair this last part of this workshop instead of Professor Monsef Krati, who should be sleeping this time due to time difference. Okay, so in this workshop we will have two keynotes and 5 presentations. We will start with the keynotes. We will switch to the Professor Orlando, waiting for the other keynote speaker to connect. So the first talk, the first keynote will be given by Professor Orland, Helicio Orland. Just a moment to connect to his bio. So Professor Orland, Helicio Rangel Barreto Orland obtained his PhD in mechanical engineering in 1993 from North Carolina University in the US. He joined the Department of Mechanical Engineering of Federal University of Rio de Janeiro, where he was acting as head department during the years 2006 and 2007. His research area include the solution of inverse heat and mass transfer problems, as well as the use of numerical, analytical, and hybrid numerical analytical methods of solution of direct heat and mass transfer problems. Professor Orland's co-authored 4 books and more than 350 papers in major journals and conferences. He is a member of the Scientific Council of International Center for Heat and Mass Transfer, located in Turkey, and delegate in the Assembly for International Heat Transfer Conferences. Professor Orland serves as associate editor for many journals, including Heat Transfer Engineering, International Journal of Thermal Science. So Professor Orland will give a talk entitled Inverse Problem Solutions for Thermal Characterization of Materials at High Temperatures. Professor Orland, the floor is yours.
Thank you very much, Professor Benhamou, for the very kind introduction. And let me share my screen here. Okay. Can you see it?
Yeah, maybe for 30 minutes, yes?
Yes, of course. And
Okay.
please, if you, I do not follow the schedule, please remind me about the time limit.
Okay. Okay. Thank you. Go ahead.
So first of all, thank you very much for the organization to invite me to be here today and share with you this presentation. This is the summary of the presentation. Have a short introduction, talk a little bit about the inverse problems, the experiment that I'm going to present some results, the mathematical formulation for the heat transfer problem related to this experiment, and some results and conclusions. As we know, the estimation of parameters or functions in appearing the mathematical formulations of problems in nature, it's when we use measurements of the response of the system and also the computational response of the system calculated in the form of some dependent variables of the model. This is an inverse problem. And inverse problems, they have played a very important role for the characterization of materials in terms of their physical properties. And today it's a practical tool in many important applications. And we can see this by when we look at books related to inverse problems and also to physical properties, to the measurement of physical properties. And similarly, when we attend the inverse problems conferences. And in fact, many commercial equipment today, it already has built-in functions for the estimation of the physical properties based on inverse problems solutions. There's a very nice and important paper by Yvon Jarny that he presents a very comprehensive review of the application of inverse problems for the thermal characterization of materials. We can also find a very nice book by Janot de Giovanni about the different techniques for the measurement of thermophysical properties. And when we come to applications to the estimation of the physical properties in high temperatures, the space program, in the development of the space program in different countries has played a very important role for that. And many papers that we can find in this area, they were published by the group of the Moscow Aviation Institute in Russia, that is led by Dean Oleg Elifanov. And this, by instance, the same group that has developed the iterative regularization technique for the solution of inverse problems. Nowadays, there are many research and industrial paradigms that require the solution of inverse problems for the accurate measurements of physical properties. And particularly for many cases, the classical or standard measurement methods cannot be used. For example, many material processing techniques, they involve materials process. Many manufacturing techniques, they involve materials processing at high temperatures, where we need to take into account coupled physical phenomena and also nonlinearities. For example, one example is this vapor deposition of or plasma spray of ceramic material over a metallic substrate that is used as a thermal barrier coating for gas turbines, and where some dedicated techniques have been developed for the estimation of the associated physical properties. Also, at high temperatures, the measurement of thermophysical properties is affected by radiation. So usually as I mentioned a lot, like we have coupled heat transfer phenomena. There's also a very important paper by Jean-François Sacadura, where he presents the theoretical predictions and experimental techniques for the measurement of thermal radiative properties that I mentioned here. At high temperatures, in fact, the measurement of temperature itself becomes a challenging problem, because those temperature measurements are usually taken without any contact with the sample by using parameters or infrared cameras. And one example is this very nice experimental setup that was developed by the group of Professor Philippe Lemasson at the Université Bretagne Sud in France, where the sample of a metal is levitated by the flow of argon. And this sample is heated by a very powerful laser that can raise the temperature of the sample even to above the melting point of metals. And then it's a kind of a flash method experiment. And when the desired temperature is reached, there's another laser pulse, and from this temperature increase, you can estimate, for example, the thermal diffusivity of the sample material, even of liquid metals. I'm sorry. The temperatures of the surface of the samples, they are measured with a pyrometer, and the radiative flux measured by the pyrometer, it's then split into 6 wavelengths where we have the appropriate detector. So the solution, the temperature measurement become itself an inverse problem, where besides the temperature, we also have to estimate, for example, radiative properties like the emissivity at the different wavelengths. And this inverse problem was considered in these references. For the measurement of the thermophysical properties, you always have to cause some perturbation on the material, on the sample of the material that you are interested in. These perturbations, they can be associated with a steady, transient, or even periodic conditions. And while the measurements are taken, as I said, like by temperature or by radiation intensity, etc. In this sense, we can have, for example, a small perturbation caused to the sample at a uniform temperature, for example, inside a furnace, or that is approach usually considered in commercial equipment like the flash method, or this is exactly the same case that I have shown before in this experiment from the Université Bretagne Sud. But here we don't have a furnace, and the desired temperature is reached by the laser heating. And then you cause a small perturbation at on the temperature of the sample that was initially at a uniform temperature, and then to measure the temperature variation of the thermophysical properties, you have to repeat this process at different temperature levels. On the other hand, we can also think about a continuous larger temperature variations, and then you use whole domain temperature measurements within the range imposed by this external heat source to estimate the temperature dependence of the properties. And this is the kind of experiment that I would like to present results to you today, which involve the estimation of the temperature-dependent thermophysical properties of a solid material, which is continuously heated by an oxyacetylene torch. We assume that this material does not undergo thermal decomposition or phase change. the inverse analysis is performed within the Bayesian framework of statistics. As we know, inverse problems are mathematically classified as ill-posed, which means that their solutions do not satisfy at least one of the requirements about existence, uniqueness, or stability. And so to cope with this ill-posed character, we actually solve an approximate well-posed problem with some kind of regularization technique to stabilize the solution. By applying three basic steps. The first step is the design of the experiment, which means that before trying to solve the inverse problem, we have to define which quantities should be measured, where the sensor should be located, how long the experiment should last, etc. In order to obtain the most meaningful measurements for the inverse problem solution. Then we run the experiment and we go to the second step, which is the estimation of the model parameters or functions that you are interested in by using this measured data and also some solution technique that can cope with the ill-posed character of the inverse problem. The most general techniques, they involve minimization of an objective function. Usually this objective function involves the difference between the measurements and the dependent variables I mean, the computational solution of the mathematical model for the problem. And recently, techniques within the Bayesian framework of statistics, they became very, very popular because they intrinsically take into account not only the information provided by the measurements, but also the prior information available for the model parameters or functions. This prior information provides regularization for the solution of the inverse problem, but we need to be very careful with that because it also provides, it results in a biased estimate. And finally, we have to do some uncertainty quantification, which means that the solution of the inverse problem cannot be limited to point estimates of the unknown parameters or functions, but it must also allow the quantification of uncertainties related to the estimated unknowns and also to the mathematical output of the problem, I mean the dependent variables of the mathematical formula. Also, in this sense, Bayesian techniques naturally provide this framework for uncertainty quantification and also for sensitivity analysis, since the solution of the inverse problem is obtained as a statistical inference. This term Bayesian, it's related to the framework developed by Thomas Bayes, but an interesting point is that what is called the Bayes theorem is actually attributed to Laplace. And the Bayes theorem relates what is called the posterior probability density to the prior density and to the likelihood. The posterior is the conditional probability of the parameters P given the measurements Y, while the prior density is the statistical model of all the information that we might know or might not know about the parameters before the experiments are taken, while the likelihood function is the conditional probability of the measurements given the parameters. And this is, in fact, the statistical model of the measurement errors. The other probability density in the denominator here is called evidence, and for it's a normalizing constant for the posterior distribution, and for most of the cases it does not have to be known. So if we make some hypothesis here about the measurement errors being additive with zero mean and they being normally distributed. And the statistical parameters of these normal distributed, like the covariance matrix of the measurements, W being known. And also there are no, if we assume that there are no errors in the independent variables and the measurement errors are independent of the parameters P, we can write the likelihood function by this expression, which is actually a multivariate Gaussian distribution. And if we further assume that the prior for the parameters, this prior information for the parameters can be represented by a Gaussian distribution with known mean mu and a known covariance matrix V, we can write this expression for the prior. And when we couple the Gaussian likelihood with the Gaussian prior in Bayes' theorem, we get an analytical posterior distribution for written in this form, where D is the number of measured data, N is the number of parameters, and W is the covariance matrix of the measurements, V is the covariance matrix of the prior. So these are known quantities. And what remains here is a scalar given by this expression. And we see that if we want to maximize this posterior distribution, like we want to find parameters that maximize this posterior distribution, we have to minimize this quantity. And this gives what is called the maximum a posteriori objective function for this hypothesis of a Gaussian prior and also a Gaussian likelihood. But for many cases, the posterior is not analytical, and one possible solution to deal with this problem is to try to generate samples of the posterior distribution by using stochastic simulation, by using Markov chain Monte Carlo methods. Then, ideally, we can perform the inference on the posterior by performing inference on those samples. And the Metropolis-Hastings algorithm is a very simple and robust algorithm for this proposal. Let me skip this here and go to the experiment. The experiment that we have performed, it involves it's based on this ASTM standard. For the comparison of thermal protection materials, and it uses an oxyacetylene torch. Here we have used a sample with 20 millimeters of diameter and 20 millimeters of length, which is inserted into this holder, which is made of a refractory brick. And for the sample, we have used a high quality graphite that is used in the nozzle of rockets because of its thermal stability at high temperatures. We have some data from the manufacturer of these graphite for the thermophysical properties at high temperatures, and we also measured the temperature, the thermophysical properties from room temperature up to 200 centigrades in a flash method, which are these data here. And we also did a curve fit of these measured thermophysical properties in terms of these two exponential functions for the volumetric heat capacity and for the thermal conductivity. The sample was instrumented with 3 thermocouples, which were located at the center line, below 2, 5, and 10 millimeters below the heated surface, and also another thermocouple at the non-heated surface. The thermocouples were type K with 30 gauge, and we can see here that we got some good repeatability of the tests for some distance between the torch and the specimen, but for other ones we didn't get a very good repeatability. The size of the torch and the sample, they were selected trying to have a uniform heat flux over the sample. And we also made some tests with another sample that was instrumented with 3 thermocouples at the cross section of the sample below 10 millimeters the heated surface. And these are the measurements to these different radial positions at different times. And we can see that we get a pretty much uniform temperature distribution at this cross section. And then what we did, well, we used the one-dimensional model by using the measurement at 10 millimeters below the heated surface as a boundary condition, so that we could write the mathematical formulation of the problem in this form. Here we have the temperature-dependent volumetric heat capacity. Here we have the temperature-dependent thermal conductivity. The measurements that are used as boundary condition, we pretty much know also the initial condition from the measurements. But we have all this function here, which is the applied heat flux, the heat flux imposed by the oxyacetylene torch on the surface of the sample. So we did with the different inverse problems related to this mathematical formulation at different times. And these are the results that I would like to talk to you today. And most of all the experiments, they were done by Carlos Mota, who was my former PhD student. So in the first case, in the first work, we supposed that the properties were deterministically known and given by those exponential curves that were adjusted to that were curve fit to the experimental data. And the objective here was simply to estimate the boundary heat flux. And then we did parameter estimation with the Levenberg-Marquardt method. We also did functional estimation by using Elifanov's iterative regularization, which have shown that actually the heat flux had decreased in time as the surface temperature increased, because the radiation heat losses increased. But for both cases, we have observed a very large and correlated residuals for both sensors that we have used. Then we moved a step further and considered that the parameters that the 6 parameters that represented the exponential functions for the thermophysical properties, they were not exactly known, they were not deterministically known, but they were represented in terms of Gaussian priors. Okay. And the parameters for the heat flux, they were approximated in terms of constant piecewise functions in the same time intervals that we had the measurements, the temperature measurements. And we also considered here Gaussian priors for those parameters representing the heat flux, which were obtained from, which means were obtained from the previous work by using this functional estimation technique. And then we did a maximum a posteriori estimate. And these are the results obtained for the volumetric heat capacity and thermal conductivity. And we see here that the adjustment of the physical data was not very good. And we have here the heat flux varying in time. And in fact, the residuals at the sensors, for sensors 1 and 2 at 2 and 5 millimeters below the heated surface, respectively. Although these residuals were small, they were very much correlated. So we moved still a step further, and we then gave more freedom to those parameters representing the heat flux, which before they were considered in terms of a Gaussian prior, and now we have considered what's called a Markov random field prior for these parameters. And we then applied the Markov chain Monte Carlo, I mean the Metropolis Hastings, for the estimation of this vector of parameters. This prior is it's a non-informative prior. I mean the variance for this prior is unlimited, and in this case we have applied this Markov random field prior that resemble Tikhonov's regularization. Here, gamma is a parameter associated with uncertainties in the prior, and p tilde here is some reference value for p. It's usually taken as 0. While D is are the same kind of difference matrices that are applied for Tikhonov's regularization. Here we have a first order difference matrix, and here a second order difference matrix. In this case, we have applied this one, the first order difference matrix. Then we could get a much better reproduction of the experimental data for the thermophysical properties. Although we still have some points here that could not be very well reproduced, and this is particular in the temperature range that the experiments were conducted. Despite the use of this quite non-informative prior for the heat flux, the estimated heat flux was smooth. And the residuals are now, although they are still correlated, they tend to 0. You see that they tend to 0, and they are all below 1 degree centigrade. Then we moved still one step further and consider, instead of considering the exponential approximation for the approximations for the volumetric heat capacity and for the thermal conductivity, we considered also piecewise constant values for these properties within the temperature range that the experiment was conducted. So we approximated this in terms of NT parameters here for thermal conductivity and NT parameters for the for the volumetric heat capacity and for the thermal conductivity, while the heat flux was still the prior for the heat flux. The heat flux was still approximated in terms of piecewise constant functions for during the time interval of the experiment, and both for all the parameters, they were modeled in terms of those Markov random fields for this group of parameters for the this should be C for the for C, for K, and also for the heat flux, and for the parameters appearing in these Markov random fields, we considered them also in terms of they were modeled by Rayleigh hyperprior. So actually, posterior is written in terms of this expression here in the bottom. And then these are the results for the volumetric heat capacity. We can see that we get a much better agreement between the estimated quantities, which are represented here in terms of their means, and also the the 99% credible intervals. It's much better. It has a much better agreement with the experimental data, also for the thermal conductivity, particularly at that point that it was really off from the previous estimates. So there are like almost 70 points where the temperature points where each thermophysical property is estimated in this case. And besides that, we have about 150 points where the boundary heat flux is estimated. And again, all of these quantities that were estimated without any informative prior, they were smooth, and they, particularly here, they represent the measured, the independent measurements relatively well. And they resulted on the smallest residuals, which are also very close to zero, although they still exhibit some correlation. This is the posterior, the Markov chain for the posterior distribution, which shows some that it tends to an equilibrium distribution. And this is the histogram of the samples of the Markov chain for the thermal conductivity at a specific temperature, which shows that it's the nice thing with this approach, because we can also get an estimate of the uncertainties related to the estimated parameters. So very briefly, some conclusions. I guess that I'm running out of time. For this case is analyzed with the sample of this reference material. The smallest and the least correlated residuals, they were obtained with these non-informative priors. For the temperature variations of thermal conductivity and of the volumetric heat capacity, as well as for the transient heat flux. All the solutions were stable, despite the fact that we were estimating about 270 parameters. But of course, we need to go ahead on this problem, at least to consider the thermal decomposition of the heated material. So before I'm finishing, a little announcement here that I am organized with George Dubikrovich, Colasso, and Zbigniew Buliński, this mini symposium on inverse problems, design and optimization heat transfer during the ECOMAS conference next year. So you're very much invited to submit papers for this mini symposium. And of course, I'd like to acknowledge the organizers of IRSEC'21. Thank you very much, Professor Mohamed Garoun, Professor Najim Alarus, Dr. Zaid Romani, and Professor Youssef Zaz for inviting me to be here. And you're also very kind. I just noticed today that you promoted me to the workshop chair, and although I didn't do any work, thank you very much. This support provided also by Brazilian agencies here, I'd like to acknowledge. And so I guess this is it. Thank you. Thank you very much. Thank you.
Thank you, Professor Orland. Okay, now we are moving. We will have discussion later. So please, for the attendees, ask your questions using the Q&A panel. Now we will move to the next keynote, which will be given by Dr. Mirzai. I think.
Hello, and first I have to apologize because I thought it's 12:30 UK time. It seems it was 12:30 Morocco time, so that was a misunderstanding. So I apologize for that. Okay. I don't know if I can share my screen. So first of all, thank you very much for inviting me. That's a pleasure to present in IRSEC. And if I can share my screen, I can do it now.
Okay. Waiting for this, I will just present you. Dr. Parham Mirzai Haranjani, I guess I'm sorry if you are pronouncing your name not.
It's correct.
Exactly. It's already okay. Okay. He's from Faculty of Engineering, University of Nottingham, UK. Dr. Mirzai is an assistant professor in the Faculty of Engineering at this university. He is the director of the Building and Urban Energy and Health Research Laboratory. He has an extensive research portfolio about a variety of topics in building scale, such as airborne pathogen transmission, including COVID-19, energy efficiency, architectural design and efficiency, smart buildings, indoor-outdoor comfort, and air quality, integration of renewable energies, and so on. So Dr. Mirzai has published more than 60 journal papers and 5 book chapters. And many of these papers are among the highly cited papers in this field. So Dr. Mirzai will give a talk entitled Multi-Scale Approach CFD Modeling of Airborne Pathogen Droplet of COVID-19. So Dr. Mirzai, the floor is yours for 30 minutes.
Thank you very much, Professor Benham, and thank you very much again for inviting me. And yeah, the reason I picked this topic, maybe because then we are in the conference related to sustainability, energy efficiency, is that for years in building sector as a major sector which basically consuming energy, for years we were moving toward having efficient HVAC system and healthy buildings. So we cared much about energy efficiency. So our system mainly went through that direction. And after pandemic and after having very solid facts, we understood that ventilation system need to be basically rethink and be changed toward direction that we can basically make sure that they're not contributing in the spread of virus as they're doing now, based on the solid facts. In this aspect, so we have powerful tools of CFD, which encounters some challenges, and I try to go through it. I know this is basically, I got, I guess, 25 minutes. I try to be as fast as possible. The topic is wide, so I try to cover probably a bit of that. So just an outline is I'm talking about the airborne pathogen transmission, the mechanism, physics behind, and then I will talk about the approach that we have, the tools and techniques we can use, and after that, I address some challenges that we have in safety, and finally, I talk about some sort of assessment, risk assessment that we have done with collaborators across the world in these aspects. So I would like to just highlight some organization that I would say finally they recognize airborne transmission of viruses. So this came through SARS. I could say that was a decline in research on this topic, in understanding the importance of the topic, but suddenly after solid facts, we're back on the track to understand airborne transmission. So this is now a major, let's say, part that we transmit the virus across the world. So different organizations who now have the solid statement in this aspect, ASHRAE, governments. I just brought government of UK example, which is addressing that ventilation of indoor spaces to stop the spread of the coronavirus. So I think every country now is moving toward that, this fact that ventilation is one of the main and important factors in preventing to spread the virus. So look at just let's look at quickly on what we have regarding the transmission of the airborne transmission. So when we going through the respiratory events like coughing, speaking, sneezing, inhalation, exhalation, singing, different sort of activities, we spread about thousands to 100,000 of particles and droplets, I would say, sometimes more than 1 million of droplets. Many of them are in the range of large droplets, so they are basically following the ballistic trajectory, so they are fallen about 1 meter across ahead of us. So that's coming, the reason you sometimes hear about 1 meter. Then we have intermediate droplets, sorted sizes between 5 to 100 microns. And they can move based on the jet. So because we have it, we produce a jet, and under influence of the thermal stratification, it can be a plume. So we have about intermediate droplets. They can travel up to 2 meter, 2.5 meters. So this is the basis of most of the safe distances that we hear. And they came mainly from the SARS investigation or viruses before that. But now what is the major problem is the particles, submicron droplets or micro droplets below 5 microns. So those particles tends to linger. They follow the airflow, background airflow, so they can stay and remain in the air for hours, and therefore they can cause infection. So I will talk about that, how the infection is basically spread in terms of virus. It's very controversial in measurement, but still this is the major point of that. So also we know the background basically flow, which is the impacting these particles and droplets to circulate, and this is coming from the ventilation system, is coming from the movement of the people, and different basically reasons for that. We have some techniques ahead of us to investigate this problem. So it's about visualizing how basically a spread is happening, but I will talk through that in the following slides, that even measurements are not really giving us much of information because of the observation techniques that we have in hand. So we understand the droplets spreading, we know the mechanism, but we cannot monitor them in every situation. Mainly lab measurements are limited to very, let's say, the parameters are very limited, it's not changing according to reality. And also, as I will explain, the measurement devices, they have serious flaws. So that's a major point that we came across using CFD. So you see CFD models now getting popular, but I would like to today mainly focus what would be the problem with them. So they looks that we can generate fancy and beautiful pictures, informative picture, but at the end we have to consider that there are so many problems and challenges, and we need, as researchers, scientists, we have to focus on them before we can make sure that these tools are really giving us the reality. So what CFD can do for us is that it can help us to understand spaces in terms of the spread of virus, so we can redesign ventilation system, redesign the space arrangements. So it will help architects, it help building engineers. It can also help us to understand elements of the HVAC, like filters, HEPA filters, for example, PPEs. So different elements can be investigated with CFD. But as I go through the problems, we encounter with the 4 major problems when we're dealing with CFD. The first one is computational cost. Second is, which I think is very important, is oversimplification of the physics. behind particle dynamics, which is integrated to our CFD calculation. Uncertainty in the collected clinical data. That's another major problem. And at the end, how we want to translate the results, that's also another problem. So I go through these four major parts one by one. Hopefully I can stay in my time. So the first one is computational cost. If you have worked with CFD in sense of Lagrangian aspects rather than Eulerian, that is very much popular, you understand that is heavy. So the calculation is heavy. We need clusters, we need nodes and supercomputers to model the basically droplets. And therefore, not every single, I would say, institution or entity or individual have the access to that. And I think this is something against freedom in science. So we need to basically make this accessible, the resources for if we have a talented scientist somewhere without having access to some resources. So I think that's one of the barriers, major barriers. If you have done some CFD aspects, you could see that simulation for not very large space, rather than, for example, this case of 4 people sitting somewhere. So I would see if I can have my marker. So we use other platforms normally. Yes, I've worked with Zoom, but yeah, I work with normally other platforms. So I want to see if I can find the pointer here. So which I couldn't. Sorry about that. I hope you can see my mouse is moving. So in this case of a simple case of, you can see that, right?
Yeah, it's okay.
Yeah, thank you very much. So in this case of a very simple case of 4 people sitting around the table, so probably it's days of the simulation with the supercomputer. For example, for a case of a room that recently we have modeled for about 60 seconds for each calculation, we have to put it to a cluster with many nodes for 1 day. So for 60 seconds, 1 day, and you have to pay. Sometimes you need to maintain your server, your node, and the problems happen sometimes. The electricity problem, so it's expensive and it's time consuming, and I think that's one of the problems that should be solved against the researchers. So if somebody wants the access in some, let's say, other countries, they have these resources. So that's the one major question that I think that should be answered. The second one, which I think is a much more important fact for scientists, is how we see the physics in CFD. So again, if you work with CFD, and we normally, if you are working with Eulerian cases, we deal with the scenarios that so many details maybe can be assumed, simplified. But in this sort of CFD modelings, which deals with the droplets, we cannot really much simplify the model. And I would start with the Stokes number. Stokes number will tell us that how droplets are moving in a space, because as I mentioned, we have 100 plus micron droplets, we have submicrons, and the virus size, coronavirus size is about nano, so it's submicron definitely. So, but some of these droplets, as you can see in this basically orange line, they're following the airflow. So let's say we have a particle, a large particle over here, and there is a particle on the orange one. So it can pass if the Stokes number is basically low. And if the Stokes number is in a certain range, it can just, it's not following the airflow. So it's impacting the other particles. So the mechanism, the number of droplets and the size of droplets is very important to shape the form of the model. And this is not really easy task. So many codes, they cannot do that. Even commercial codes, if they can do that, again, you encounter with more and more complexities to your model. It means more computational cost. Also, if you want to consider so many complex phenomena in your models, if, for example, breakups, so because of the surface tension, particle droplets, they can be broken to the other particles. And this is again about, for example, Weber number with a state, if its droplet is going to be broken or not. And I can say science related to these sort of droplets and particle dynamics is even very recent, and so it still is going on. For example, how droplets are collide together, the knowledge is not completely there. Still, so many scientists are trying to understand what is the collision in droplets. So if for example, two particles are colliding together, they can form a bigger one. They can, in this one, you can see a satellite, third satellite can be born. In this case, 3 satellites can be born. So it's all about different conditions. And imagine we have about millions of these particles and droplets. Another thing is about evaporation. You hear that evaporation in coronavirus spread is very important, because in the fraction of second, I think mainly below 0.3 second, a particle or droplets will shrink or evaporates and shrinks to mainly 97% of its size. So it will be shrink in a very, very short span of time. So that's why evaporation is very important. So we have to include. So this is one of the understanding that we had, that we cannot, for example, ignore evaporation, because that's very important. So that's why you hear that some guidelines, some Nordic countries, for example, they say to keep the ventilation high to prevent, for example, evaporation. But the fact is, the side effect is, for years, they tried to make their HVAC system to keep the relative humidity low because of the mold problem and the health problem, energy problem. So now it is contradicting these efforts that we tells we have to keep it high, relative humidity higher than 60% in some offices, spaces, to make sure that spread is minimized. So therefore, we can say in models, evaporation cannot be ignored. Other effects in this scale also will get important. Brownian motion, for example, is about molecular impacts and kicks to the particles. Normally, when we do CFD, even particle CFD, we don't bother to see Brownian motion. But imagine we are talking about problematic droplets, which are about submicron. And in those scales, if you do a simple calculation, you can see that Brownian motion, which is the effect of molecular scale, is getting important. But are we have any models, because that's about quantum physics, or if you want to say it's molecular physics. So do we have any models can be adapted to our safety model? There are efforts, but I would say just few studies on this to add to this scale. Also, turbulence models, that they are mainly tailored for average, if you're talking about RANS models, they are about averaging the velocity. So the averaging is not helping in this scale. If we're talking about LES, again, we have filters for vorticities, for circulation. Again, in this very small scale, those smaller scale vorticities and circulations, I would say, are very important. So even good models like LES might not be suitable. So there's lots of challenges behind this in terms of oversimplification. Also, in terms of background flow, let's say ventilation mechanism, we mainly, when we talk about ventilation, for example, this is a recent study by us and our collaborators. When we talk about ventilation, we normally do the simulation for the hours. So we go through steady state simulation, we do this assumption, but when it comes to the transient and very basically time-dependent solution, we see some phenomena that we don't expect to get it by ran CFD and such models. But those are very important for the spread of the virus. Those are basically the essence of the spreading virus, this sort of backgrounds. Either is natural ventilation, like cross ventilation cases, or if it is about mechanical ventilation. Also, moving of the people is very important, but there are not so many research on how we can really technically model walk and movement of the people. So if we're going to use dynamic mesh or a moving mesh, so there are going to be many challenges. So therefore, I would say there are so many challenges about the physics. Just we can not go follow the same guidelines as we have done for years about ventilation and applied to the CFD of airborne pathogen transmission modeling. So the third one is about the problem, or I would say challenge against us, is uncertainty in the clinical data. So when it comes to the clinical data, so first of all, we talk, I think we are two different realms with the medical sciences and engineers. And I think this is a problem. Sometimes terminologies are lost in translation, and those aspects is important for them, might not that be much important for us, and inverse. There are things important for us which are not really concern of those communities. Example is we, as a CFD modelers, we always need data for applying on the boundary conditions, applying for the validation scenarios, and therefore it's very important for us to have those values. But for, let's say, clinical scientists, they focus in are not really on to see exactly how many droplets would be released exactly on the place of the nose or mouth or nasal system. So they are mainly concerned for the numbers of the, for example, pathogens. And therefore, this is, I would say, lost in translation of two communities. What we understood from literature that respiratory events generate different number of droplets and with different sizes. And still, when we dig through the data sets, we don't get that consistency in the data. First of all, this is common sense that when we cough, sneeze, we can see different people, they have different, I can say, style of sneezing or coughing. And this is true, and even gets more complex when a person has different age, gender, even we understood ethnicity, when it's about exhalation profile, the style, I would say, or sneeze profile, is about temperature of the room, relative humidity of the room that we are in, background flow of the room. So different things will impact, I would say, either environmental or individual parameters impacting on the number and distribution of these released droplets. I mentioned about 1 million droplets, but that's only true for some cases. So different values are really reported. And also within this droplet, mucus and saliva ratio is different. So this is also understood. So we are very uncertain about the boundary conditions of our models. And when we want to validate, also we don't have that much of certainty. Harmful dosage, how many dosage we have, how many droplets we have to inhale to get sick. So what we could find is a number like 100. That's what we use. Not 100 droplets if we inhale, we get sick. But this is basically controversial. You go some other papers in clinical aspects, they say more or less. But for us, when we use it as a parameter, so we can be 100, 200, but for clinical science, that's another aspect. They see how this will affect on the system, immune system, and other aspects. So it's very different and very uncertain realm, if I would like to say. The techniques that we normally use to measure this clinical data was not much advanced and tailored to be used for droplets in these aspects to basically see the nucleus that may contain viruses. For example, PIV, particle image velocimeter. If somebody worked with that, knows that the screen, the size of the screen is not that great. If you want to cover a room, it's not that much possible. But you might place it in front of a person, but there are safety issues because we're dealing with laser. Also, we're talking about seeing the images that we might miss some particles with different smaller size because our camera might not get it, and different, so many things. And we also have inconsistency in generating droplets. We cannot ask a person to exactly release the same amount of droplets. So it's very different issue. Are we going to make some mannequins that can do constantly release basically droplets? So many questions. Other techniques being used like laser Doppler, basically just targeting one very small space in the basically domain, which is not very handy. Other techniques also been used, but as I said, there are major limitations with them. For example, when some measurement, they just inhaled, exhaled, or did the speaking mode through the chamber, and then they counted the number of particles. But we know that in very short span of time, in a reality, in a room, like 0.3 seconds, most of the particles or droplets will evaporate. So is this phenomenon really seen in these experiments? That's a question. That's a big question. So that's why at the end, we see different results and different, so let's say numbers, which are very important as modelers. Those are very important for us. I would say, yes, profile is seen. So we expect that we cough. When we cough, there is a peak on the airflow, airflow rate. But what's the peak number and what's the amplitude, or let's say what's the size of this peak, or what's the different aspects of this profile? What is that? So that's uncertain point. This is also about breathing cycle. So this is, so we expect to breathe like this, but the maximum, minimum numbers will change from people to people. Athletes, or it's a sick person, or it's an old person, or it's a young person. So that's all different for us. But so therefore, when we see some result from safety, we have to really think what they are typically put as the input. So if you're talking about heat generated by a person, we have this for years. So we know that a typical person generates how much of the heat, or CO2. When we say CO2, that's typical. We know a typical person in a certain location of the world will release this much of CO2. But when it comes to the droplets from the respiratory events, we don't know really. We don't know that much. What does it mean, a typical one? Again, in terms of the distribution and size of the droplets, you can see different studies. They address many different numbers. This one, for example, addresses very large particles. But when it comes to the place that is important for COVID, you don't see that much of resolution because of the equipment's problem. But in a higher resolution one, we can see that there are much happening. So thousands of droplets is within this range, which is ignored. But in this also, this one, so there are other limitations for the measurement. So that's why we have a major uncertainty in measurements of the size and distribution of the droplets. Also, the jet that we released, it does have an angle. So it is changing through gender, through different situation. This is also changing through speaking, breathing, singing, even loud speaking. Some people are speaking loud, some people not. And therefore, very uncertain, I would say. Also is coming about how much, what's the velocity when I talk, when I speak, when I breathe, when I cough, what is the speed that really released? And that's changing a lot. So what we dig in through the literature, so these are numbers that's been averaged through different papers. And you can see if you want to model a sneeze, what you're going to put. It is 18 meters per second or 50 meters per second. And that can tremendously impact on your final result. So I would like to end the third problem and go to the fourth one because of time, and I hopefully can finish in a few minutes. So the post-processing. So for years, we understand that if we do CFD, if we do CFD modeling, we can expect to have the airflow field, and we can analyze that. But I would see a trend. I think everybody recognizes that so many CO2 studies as a marker of the COVID is happening at the moment. But CO2 is a gas, and particle droplets are solid. Just I want to talk about basic science. So those are behaving very differently. So CO2 being used again as a marker of the COVID transmission is not really a good one. And if we look at the CFD result, so this is for 10 seconds of release of the droplets, and this is 10 seconds of release of the CO2. You can see even for 10 seconds, and these are released from this person to the receptor, which is this one. So you can see the trend. It's very obvious. It's very different. So, and this is the trend now that many governments even put efforts to get the CO2. So how you want to translate your data is very different. The average flow, as I mentioned, because of Stokes number, because of the scale of the problem, scale of the these sort of droplets are not helping. Some risk models like Wells-Riley model, they are for the conditions that droplets are not well mixed. The room are well mixed, air is steady, but this is not the situation. So we need to develop models that are fit to purpose for our cases. Therefore, I just want now to give you some examples for a couple of examples that we are doing in collaboration with the colleagues. So instead of going through the major domain of the velocity and turbulence field, these are the things we said, okay, we have to trace particles. And you can see in one study, we have defined a secondary mesh that is basically we place so many small contours in this space that we can see what is the accumulation of the droplets at that specific space of a location. So let's say, then we could see if we have, for example, a person here, how many droplets would reach that person through the time. And the result obviously is very different from the main velocity field. For example, if you model this is how you would see the average Eulerian velocity field. But the risk is not associated with that, as I mentioned. So the risk, and you can see we have done a 3D visualization, is like that, around that person. So this is a model, basically a synthesized data of CFD to not the one that we traditionally use, which is the velocity contours and vectors and fields. So we have translated them to some risk models, which are telling us different things. So if we have, for example, different temperature, relative humidity, velocity released by people, you would see that there is a cloud risk forming around the person, and that cloud, which means that how many droplets would reach to each point of that cloud. So that can obviously we expect to be different in different climatic situation, and as I mentioned, also according to different characteristics of an individual. But if you look at simply to the airflow field, you won't get that much of difference between all these cases, and if you get, it can also mislead you to somewhere that is not really saying what is about the particle movement. As I mentioned, I just want to highlight that the droplets and particles are not necessarily following the main airflow field. This is another one, so you can see how the cloud of risk can evolve through time. So then the safe distance in terms of the, let's say, horizontal aspects or vertical aspects, if you would like to place some ventilation, will change through time like this. So it is also, this risk is changing through time. So you might stay somewhere from a person which is sick for a period of time, which can be safe, but after a certain time, that place can get risky. So this is important when, for example, if we sit for 8 hours in an office. So it might be for 5 minutes, might be safe somewhere, but after, let's say, some hours, it gets risky. So these are translation that we got from CFD rather than using directly showing the vectors and velocity fields, turbulence field. So it's very different methods that we would like to use, and still it's very early stages. So you can see out of this safe distances, as I mentioned, horizontal, vertical, we can develop some simplified models. This is a linear regression model. This is ANN model. So we can see, for example, if you are in a room that you expect the person to cough or speak, but if you have different temperature, relative humidity, you can expect what is the safe distance. We can also fit it to ANN model. For example, this is case 4 for certain relative humidity, certain temperature in a room. So we can understand what would be the, so this is telling us the vertical spread of the virus. So it is basically through time, it is spreading like this. So it is, you can see after, for example, 30 seconds, about 30 seconds, it starts to, the cloud of risk to go higher and higher to reach its maximum about this. So it also will help us in the design of ventilation stages. We can generate same thing for the horizontal risk and so on. Another example is about ventilation design. So the question is, if I have an office, what would be good? If I just put the people in close to the window, if I use cross ventilation, if I use single-sided ventilation, if I just close the window, which one is better? Because in some cases, the wind can help to spread the virus. And we saw this is when mechanical ventilation. This is obvious now, mechanical ventilation can contribute to spreading virus. So which one is good? And again, we went through the, you can see that through this risk assessment. So the IP1, the person one is now here infected here. You can see the risk cloud after a certain time, which is, I think is 1 hour, is spreading like this in different situations. This is mechanical ventilation, for example. This is one single-sided, let's say, case. The person is close to the window. And if you want to correlate these risks with the general flow field, they barely match each other. So there is a mismatch. So if we want to just don't use the synthesized data from CFD, we go with this, we're not going to get that much of the result we want. So we have to translate them somehow to other risk models. And as I mentioned, some risk models, previous risk models are not really helpful for the COVID cases. So we need new risk models. And as we are doing, this is the earliest stage result that I'm showing to you. So another result for the place of people. So if the infected person is basically the place is changed, you can see that the risk is also changing. So this will give us the a tool that we are able to do design for different spaces, to be understand safe distances, to understand the situation, to optimize them. And this is also going to be case by case, because there might be an office that ventilation needs to be one side, but another office in the other side. And this is the purpose of CFD in general, that can help us to do this in a cheap way rather than putting expensive devices to do measurement each time. So in conclusion, I hope I didn't pass my time that much, but CFD is a powerful tool, though it should be carefully used. So many challenges ahead of that, and the barriers in general are computational cost, oversimplification of the physics, uncertainty in medical data, and how we see data coming out from the CFD. Calculated result, we can see there is not much of the meaningful match between the traditional CFD result and our indices that we have to develop. So we have to make sure that those indices are tailored for this spread of virus purposes, and also safe distances and ventilation strategies can be designed by this sort of new indices. Thank you very much for your time, for listening, and I'm very happy to answer your question if I get any time. Thank you very much.
Thank you, Dr. Mirzai, for this interesting lecture. Now we are moving to the discussion. We don't have a lot of time, maybe 10 minutes for discussion for both the keynote of Professor Orland on inverse problems and the keynote of Dr. Mirzai on COVID spread. I am going to the Q&A. There is no question in the Q&A panel, maybe in the chat. I am checking if there is any question there. Yeah, a question to Professor Orland from Dr. Zaid Romani. In the case of on-site experimental measurements of building envelope using thermal cameras, the meteor uncertainties can impact the quality of results. How we can reduce these uncertainties?
Yeah, this is a very good question, and because it's uncertainties is on the model and on the parameters. It's always a problem, and we have just seen in the presentation of Professor Mirzai also all the uncertainties that are related to the predictions that are done for this important case related to the spread of the coronavirus. The nice thing is that when we deal with the solution of inverse problems within the Bayesian framework of statistics, is that we can carefully look at each parameter or related functions or boundary conditions to check the effects of their uncertainties on the solution of inverse problems. I mean, the estimation of the parameters that we are interested in. It depends also on the time scale that we are talking about. I'm coming back to Dr. Zaid's question. If you think about the question of hours or days, or you need to take into account meteorological data that you have about these external conditions, and somehow model them and for the solution of the inverse problem. But this is challenging. Always when we talk about the solution of the inverse problems within the Bayesian framework, we think that the prior information miraculously solve all solve the ill pose the problem, the ill pose the character of the problem. But this is very tricky because it also induces bias. So you may go to a totally different solution if the priors are not appropriately modeled. But this is a very important question. It has to be dealt with case by case. That's my point of view.
Okay, thank you. There is one question from Kautar Wali to Dr. Mirzai. The model developed to simulate the distribution and the flow of COVID particles can be used to simulate the impact of all pollutant particles on the air quality and the comfort. That was the question to you, Dr. Mirzai.
Yeah. So is that a question? So is that can be used? So this is the thing. Air quality been basically around for many years, because we understood the problem, and the models, I think, are there. So many CFD models. I don't know if I lost the connection.
We are still hearing you, Dr. Mirzai.
Hello, can you hear me?
Yeah.
Yeah, so I think I'm back.
Yeah,
Sorry, I got disconnected. So yeah, sorry about that. So I think, like everybody, we were very surprised in the CFD community when the pandemic came. I would say we were not ready for modeling this sort of virus transmission, like everybody else. What we see that we don't know much. And when it comes to the air quality, as I mentioned, it's about for example, CO2 as a marker. So we have models there. So it's about diffusion. So it's gas dynamics. It's about the equation. If you go to for example, Navier-Stokes equation, it's very well developed. The turbulent models, how it's behaving. But when it comes to the particle dynamics, as I mentioned, there are so many things that we don't know. And there is a range of droplets from submicron, which also can be impacted for Brownian motion. And this was, to my knowledge, ignored in almost all the research, maybe few research on this aspect, and not in our field. In our field, which is building, I would say, energy and environment, I barely could name even one single paper or study to see this impact, for example, or other impacts. So it's very, I would say we were also very surprised with this. Yeah.
Okay. There's one more question to you, Dr. Mirzai. In the last slide, you showed the unopen space, probably an airport. Did you any simulation with the COVID-borne particles for designing ventilation in such environment? Open space.
No. It's about the COVID ventilation. I think, as I said, everybody now is we are in the very early stage, maybe viability stage of this sort of simulation. In the UK, at least, there are some project is going on, but still, it's very soon we can address on the realistic design. And I think communities like ASHRAE addressing the problem, there should be some funding for that, but I won't expect in very near future we can really have realistic design based on the COVID. If you name it HEPA filters, still everybody is trying to maybe move that direction, do some research, be the first one, but no, we didn't, and we hope one day we can do that.
Okay, so two more questions from Dr. Zaid Romani. What are the best CFD model to use in the case of natural ventilation? The first one, and the second one, what are the boundary conditions of static zone in the CFD model you are using?
Yeah, so for the ventilation, I cannot address one ventilation model. In CFD, there are some commercial tools like ANSYS, like Star CCM, like Phoenix. I think it's very regional. People are using, but all of them, in terms of the science, they have serious flaws. So for this project, we have used three major softwares, commercial software. We added bespoke code, so we coded because they don't have things that we wanted. So I would say this is one of the problems. Industry realized the problem. I think they also will move to create something for us or for organizations they can use. So I barely can say we have done our own codes. We added to ANSYS, for example, OpenFOAM, and also we use Star CCM. The second question was about static. Sorry,
the boundary condition. Yeah. The boundary condition. Yeah.
Yeah, boundary. So we try to basically use a statistical model to develop boundary conditions for our safety, because as I said, there's uncertainty involved. So we cannot put a single number or a couple of numbers. So we try to put a range of some profiles based on statistics to the boundary conditions, and we do multiple simulation or series of simulation to cover all the cases. So this was what we have done. For example, we have done in one of the cases, we have done about 40 cases to cover a range, and for each of the simulation, we spent about 1 day with the cluster. So 40 days took because we wanted to make sure that the boundary conditions are covered in the range of uncertainties.
Okay. Just one more question from Amiri Said. Difference between flow visualization and particle tracking velocimetry. Just flow visualization is qualitative visualization, while particle tracking is velocimetry, is measurement of velocity, isn't it?
Yeah, the particle tracking and the flow. So one is the Eulerian aspects that we see the average velocity, we see the average airflow mainly, and the other one is about Lagrangian. So we set the coordinate on the particle, and we have, let's say, 1 million particle, we have 1 million set of equations, and that's the difference, the main difference.
Okay. I think we are answered all the questions almost. I don't know if there is some question from the panelists.
Yes, I can ask
go
some
ahead,
questions, please.
Yeah, go ahead, Professor
Okay.
Garoom.
Garoom. Okay, thank you very much. Hello, dear colleagues. Thank you very much for your lectures. I have two questions to my colleague, Elcio Orlando. In our works, we have sometimes more than 15 parameters to estimate in thermal problems and in acoustical problems. And the first question is how we can to estimate the standard deviation of parameters. In general, this standard deviation is unknown. We can to fix any values like 1, for example, in the Bayesian estimation. And the second question is when the parameters are highly correlated, the problem is also highly ill-posed problem mathematically. Which the best strategy we can to use? For example, the Tikhonov regularization, and the problem here is how we can to estimate the parameter gamma. It's very difficult for us to estimate these parameters, or we can to fix, for example, when we have two parameters, we have two parameters, we can to fix the ratio between them if they're, for example, correlated. Thank you very much.
Well, thank you very much, Professor Garoom. Very nice to see you again, although I cannot meet in person this time. And well, these are two important questions. I think the first one was related to the prior, right? Or to, because when you talk about the posterior, when you do the inverse analysis within the Bayesian framework, especially when if you apply MC, the uncertainties related to the parameters, it's a natural outcome of the solution, because you are actually simulating the posterior distribution by samples. Of course, those samples ideally they represent the posterior distribution, but there are different ways to take that you can check that. So I think that you are talking about the prior information. Regarding the prior, it's a model. It's a statistical model of the information that you know about those parameters of function. So it's really as I mentioned before, it has to be done case by case, and so if you don't have good confidence, a great confidence on the mean values that you are assigning for those parameters, and if you still want to model it as a Gaussian distribution, it has to it needs to have a large variance. And in this case, you have to be careful because you have to truncate this Gaussian prior. So, for example, that you don't have negative values for, let's say, thermal conductivity or things like that. Otherwise, you simply model these parameters in terms of a uniform distribution, the prior, a uniform prior distribution. This might make more sense.
Okay, thank you.
Okay.
I'm sorry to interrupt you because we
no
have
problem. I understand. We can contact you later, Professor.
Yeah.
Okay.
No problem for 5 minutes. No problem for for extra 5 minutes.
Thank you.
Oh,
okay. Thank you.
Okay. So can I continue? And
yes.
The other question about about Tikhonov's regularization parameter. You see, when you solve the problem with in the Bayesian framework and you assign a prior that is similar to the Tikhonov's regularization, you can consider the regularization parameter, I mean the equivalent of the regularization parameter, as an unknown parameter as well. It's a hyperparameter, so you can propose a prior for this parameter. It's called the hyperprior. In the last example that I have shown you, I have used the Israeli distribution. It's a very simple distribution because you have one single parameter to set for this distribution, which is the center. But still, you have to do some numerical experiments to find the an appropriate value for the center. But it's I think it's,
we can, for example, to fix any values for these parameters and to try the simulation, the calculation, and to try again.
Yeah, but I'm talking about a step further, because instead of fixing the regularization parameter, you're assigning a statistical distribution function for this regularization parameter. So, and of course, this statistical distribution, it has some parameters that need to be fixed there, but it will be considered as a in terms of it will not be deterministic, but it will be considered as in terms of a statistical distribution. And the Rayleigh distribution is very nice for this, because it's very simple.
Okay, thank you very much.
Thank you.
Nice to see you.
Yeah, good to see you too.
Okay, thank you, Professor Orland. Thank you, Dr. Mirzai, for these nice keynotes. And now we have to move to the video presentations. We have 5 papers scheduled to be presented in this last part of the workshop 4. ID 169, ID 167, 165, 186, and 153. So we'll move to this presentation. Again, thank you, Professor Orlando.
Thank you.
Thank you very much.
Thank you, Dr. Mirzai. Thank you very much. Thank you very much.
It's a pleasure to be here. Thank you.
Thank you very much.
So we can still stay with us for the. So we have 30 minutes presentation and then 30 minutes discussion. Okay.
Over here.
I think the organizer can show the program of the next of the last presentation session. Professor Abdelaziz Hibawi. Well, yeah, okay. Okay, this is the, okay. Okay, the program of the video presentations should be the next slide. Yeah, okay, that's it. So the next presentation will be, okay, go ahead. Will be presented by Fatima Zahra Riyahi from Ifran, Al-Akhawin University in Ifran. So we can go ahead.
And this presentation is about PV siting of a grid-connected solar carpet system linked to charging stations and its economic analysis. The outline of the presentation includes a background about the national energy sector, photovoltaic solar carpet, methodology and results, and the conclusion. Looking at some statistics about the national energy sector, the years between 2011 and 2013 marked the large energy import bills between $8 and $10 billion, mainly for crude oil and petroleum, and particularly coal and natural gas. Also, the yearly electricity demand is estimated to increase by more than 6.5%. To respond to these challenges, investing in renewable energy sources is a potential solution, and the following case study targets this goal through designing photovoltaic solar carpet, which is based on a simple principle, yet it has many potentials. It is composed of solar panels mounted on the top of a steel structure which have a tilted roof of 10 degrees. So many parkings take over large areas. Therefore, it would be beneficial to utilize that space and install solar carpets and link them to the charging stations for first energy production and also charging the electric cars. There are three types of the solar carpets: the DU pitch, the barrel arc, and the monopitch. This case study is conducted on the basis of installing a monopitch solar carpet for its potentials to attain higher energy production in addition to providing natural drainage. And in this application, the carpets are linked to the utility grid. Looking at the methodology and results section, the methodology is based on the following process of 5 steps, which starts by determining the daily energy demand of 65 kilowatt hour per day. It accounts for the supply of 3 electric cars, each of battery capacity of 22 kilowatt. Since the PV system must supply high AC load, the system voltage is then 48. The number of solar panels needed is 102, calculated with the first equation based on system advisor model analysis. We obtained the daily average solar irradiance as shown by the graph on the slide, and the PV array power output is 64.44 kilowatts. The performance of the PV system is affected with the type of connection between the solar panels, either in series or in parallel. For this, the number of panels connected in series and in parallel is 2 and 51 according to the equations on the slide. To have insight about the monthly and yearly fluctuations of the PV system energy production during its lifetime, with SAM, the energy produced during the first year is 42,150 kilowatt hour. That is degraded by 0.5% every year to reach 37,092 kilowatt hour at the end of the useful lifetime of the PV array, as shown by the graph on the slide. The installed inverter is a central one that is connected to multiple solar strings and has integrated AC and DC disconnect switches. The power rating of the inverter is calculated by the equation on the slide, and it is equal to 81.25 kilowatt. There are 3 types of the power meters. The selected electricity meter is a bidirectional meter. It shows the amount in kilowatt hour delivered, received, the net one, in addition to the instantaneous demand in voltage and also in current. For wiring, we use copper wires of 120 millimeters square to link the PV array and the central inverter, and wires of 25 millimeter square between the inverter, AC control panel, and the charging point, and wire with the same cross-section to link the grid with the power meter. To have insight about the economic potentials of the system, the following economic analysis is made. Initially is the capital investment cost, which is shown on the table on the slide, and it is 518,000 Moroccan dirham. To have an insight about the total cost of owning and operating the solar carpet system, we look at the life cycle cost expressed with the first equation. The lifetime of the PV models is 25 years, while for the inverter is only 10 years. Therefore, an extra 2 groups of inverters should be purchased after 10 and 20 years. Their present worth is calculated with the second equation on the slide. The third equation expresses the present worth of the operation and management. With this data, the life cycle cost is 902,470 Moroccan dirhams. The levelized cost of energy, LCOE, is determined using the software SAM. Through inserting the necessary inputs required by the software, it generates that the LCOE is 1.23 Moroccan dirham per kilowatt hour. And the payback period is an important indicator for the economic potentials of the system. As explained in the table, the payback is estimated to be 7.5 years. Finally, it is interesting to account for how much the designed PV carpet mitigates emissions. This amount is determined by the equation shown on the slide, and it is estimated to be 657,347 kilograms during the whole lifetime of the PV system. To conclude, the solar carpet PV system contributes to clean energy production and help in reducing emissions, and thus it contributes to sustainability in the transportation sector. Furthermore, the results of the analysis performed in this research can further be applied in other PV sizing applications. And thank you.
Okay, that was the presentation related to paper ID 187, and now we're moving to paper ID 169 by Mrs. Kautar Wali from Mohammedia School of Engineering in Rabat.
One of the most documented phenomena of the urban microclimate is the urban heat island. It contributes to global warming and leads to an adaptation of the city's sustainable planning policy. The consequences of urban heat island remain challenging to predict and very variable according to climate conditions. This phenomenon was defined as the difference between the air temperature on an urban and rural site geographically proximate. However, some studies have compromised this definition lately. Local climate zones is a recent and systematic classification of filed sites for urban heat island studies to provide recommendations for sustainable urban planning. LCZ divides rural and urban landscapes into 17 classes, which are defined by 9 urban indicators encompassing morphology and surface cover characteristics. The use of LCZ classification for urban heat island studies and its quantification is deemed scientifically justified. This case study deals with applying LCZ classification to Rabat in Morocco, characterizing and quantifying urban heat island in Rabat, and simulating air temperature distribution for 24 hours. Rabat is the capital city of Morocco, located in the Atlantic coastal zone with a temperate climate. The information about urban characteristics and parameters of Rabat used for LCZ classification are gathered from the LCZ sheet data provided by Urban Agency of Rabat and Saleh, the geoportal of Ors, and fieldwork. Several field visits are done in many places, and pictures of different places of Rabat are taken and coupled with the aerial picture from Google Earth for more details. The collected data about each zone and sector is organized and consolidated in database created in MySQL server. LCZ of Rabat city are digitized in Google Earth and preliminary LCZ cartography is done. To validate this classification, stratified random sampling with the condition of answering a minimum separating distance between sample sites is used to design the areas for simulation. The XZ represents strata in our case. The margin error of sample size is calculated with a confidence interval of 99%. 99%. 9 validation sites are chosen. One site of each identified L size, LCZ, and 2 sites are selected for compact mid-rise because of the spatial morphology of its spatial morphology and structure, the spatial morphology and structure of the Medina tissue. The high-resolution prognostic three-dimensional microclimate model ENVIMAT is used for simulation. We ran ENVIMAT for 24 hours on July 10, 2018. The general data for the simulation are presented in these tables. 10 tree spaces are listed for all the simulated cases. These figures and table represent the Earth temperature inter LCZ differences by day and by night. The findings below are that the differences between the average temperatures in different LCZ are widely more important at nighttime than daytime. In the daytime, the temperatures of field LCZ are hardly different. However, significant variance exists between built area and vegetation area of about 2.5 degrees. This figure shows the inter-LCZ amplitude of air temperature by night in Rabat and some cities of the world. The highest level of contrast in Rabat is 5.6 degrees. This methodology approach is an example of using geographic information system and numerical modeling as a tool to aid urban planners and designers in decision making. The novelty of this approach is also the interconnection of two urban scales, the local scale and the microclimate scale, and characterizing and quantifying the intensity of Head Island for the first time in the city of Morocco. Thanks for watching.
Okay, that was the presentation related to paper 169, and now we're moving to paper 167. The presentation will be given by Mr. Adnan Sauri Elbat from Abdelmalek Sadi University, Tangier.
Hello everybody, and welcome to my presentation. First of all, let me introduce myself. I'm Adnan Sauri Elbat from Abdelmalek Sadi University. In my presentation, I would like to report on the impact of canyon and courtyard microclimate interactions on building energy performance. In this presentation, we will follow the following plan. First, we introduce the problematic, then the methodology, followed by a description of the courtyard energy simulation model, and before the conclusion, we will discuss the main results we have obtained. Nowadays, it has become essential for living in cities to build new buildings able to adapt their environments with less energy consumed and meet the requirements of a sustainable development. In this context, several building energy modeling tools have been developed, such as Transys and Energy Plus, for buildings' energy performance assessment. However, the weather data generally used in this type of simulation are given for a typical year from weather stations located in rural areas, so they do not represent the urban microclimate condition. For this purpose, several models can be found in the literature that model the urban microclimate and its impacts on buildings. These models are generally detailed. However, their use is complex due to the high computation time and the coupling between several softwares. In this presentation, we have used a simplified approach that aims to present at the same time the building and the microclimate in order to achieve more accurate results, without going through time-consuming safety calculation generally performed with satisfactory accuracy for thermal and energy evaluation. This simplified approach is integrated in the Transit software. It allows the description of airflows and thermodynamic balances coupled at building and street scales. In this approach, the radiative model is based on the Gebhardt factor as well as the solar radiation distribution coefficients, while the IRSEC model is based on the Harman model and the Solhack model, which allows to take into account the effects of dominant winds. In order to evaluate the energy needs of the studied courtyard, we have analyzed two different cases: stand-alone courtyard and same courtyard surrounded by street canyons. In terms of the impact of the aspect ratio on Riyadh energy needs, it can be seen that for a Riyadh in a wide street canyon, the cooling energy needs are higher than those of a building in a narrow configuration and also higher than for an isolated Riyadh. Indeed, the narrow canyon, preventing the entry of solar radiation, offers energy advantages during the summer season, while it has the opposite effect in winter. This is expected as the Riyadh openings are shaded and located in a controlled microclimate of the courtyard space. However, in winter, this is due to the fact that solar radiation is the engine of energy needs trends. If more solar radiation reaches the building envelope, the heat system requires less energy. And then the impact of solar absorption of courtyard surfaces on Riyadh energy needs, we can see that the impact of multiple reflections of solar radiation generated by the courtyard on both the cooling and heating energy needs of the building is low. This is due to the shape of the courtyard of the building understudy square shape, but also to the effect of shading on the surfaces constituting the courtyard, which has the effect of limiting the multiple reflections. In conclusion, the simulation methodology used in this study can be applied to similar urban contexts and to other building typologies. Moreover, it can be used by architects, planners, and modelers to better understand the relationship between urban morphology, urban microclimate, and the building energy performance. Finally, thank you for your attention.
I think that's enough. So we had just 3 presentation. Is there any further presentation from the other papers? I am asking the organizers. Okay, there is another session. Okay, so now we are so we can go back. Can go back to the okay. There is another session. So the program was updated. So now we are moving to the discussion. We are discussing these 3 presentations related to paper 187, 1679, and 178. The first one is about PV design. The second one is about urban heat island characterization in Rabat, and the last one is about canyon effect. Yeah, I see there is one question in the Q&R. Okay, one question. The question is, I don't know what this question is destined to which paper. From American point of view, do you think that the disadvantage of solar energy affect this war? I think it is destined to paper 167. From an economic point of view, do you think that the disadvantage of solar energy affect this war? For example, the initial cost of purchasing solar system? No, I'm very confused with this question. It is not clear. So if
I think
yeah,
is
okay. It's okay. It is to the question is for Mrs. Fatima Zarar Yahi.
Yes, exactly.
Yeah. Okay. Now it's clear. So the initial cost of processing the solar system is very high, weather dependent, solar energy storage expensive, use of so lot of space associated. So the question is about the economics of this. I don't know if Mrs. Fatim Zarariahi is here, can answer this question.
Hello, can you hear me?
Go ahead, please. Yeah.
Yeah, so thank you for the question, and I would like to first start with the utilization of a lot of space as was addressed. So this kind of project, we are not installing it on we are installing it on the top of a parking area. So first, there is no space is wasted. The cars will be parked as usual anywhere, but we are still optimizing the space by installing a carport, meaning that we are installing the solar panels on the top of steel structures on the top of the parked cars. So basically, there is no space which is taken. Second of all, in terms of the cost, so basically, of course, the PV system comes with a very large cost, but its operational lifetime is for 25 years. And for this reason, we calculated the payback period, which is seven years. So in 7 years, we can get back our initial investment. And also to recap all the expenses of operating and managing the system, we also calculated the levelized cost of energy, and it is 1.23 Moroccan dirham per kilowatt. So whenever we are selling the electricity, we are selling it by 1.23 per kilowatt. So in this price will help us also recap the initial investment and also the amount of money and expenses incurred during the lifetime of the system. So I think from an economic perspective, it is an optimal system in terms of the indices that we have calculated.
And the payback period was estimated to
be 7 years.
7
years.
7.5 years.
Yeah, indeed. And the lifetime was 25. So in the lifetime of the whole system is 25 years, but we are recapping all our expenses in 7 years. So I think it's optimal.
Okay, thank you. There is no other question in the Q&A, not in the chat. I don't know if the panelists, there's questions from the panelists. Yeah, there's a question from your Q&A. This need to paper 169. What year did you 169? So the urban theory, the data correspond to which year? That's what's the question. To Mrs. Wali. Mrs. Wali.
Mrs. Wali, please unmute your mic.
Yes. Can you hear me?
Yeah.
Yes. Hello, everyone. First, I would like to thank the organizer and the keynote speakers and all participants. And I apologize because I didn't present myself in the beginning of the 5-minute video. So I'm Wali Kautar. I'm an engineer in energy systems, and I'm PhD doctor in energy efficiency on buildings. And my latest researchers are focused on the urban microclimate and the characterization of urban islands. So for the question, the data used for this paper is for 2000. It's
16.
19.
19. Okay, 2019.
Yes.
Okay, you used the satellite image for this year.
Because there is lots of data, so there is data from Earth Agency of Urban so there is data
the Urban Agency in Rabat, yeah. Okay.
Yes, and
okay.
But simulations are for 2018. Yes.
21/8.
Yes, 2018. 28.
Ah, okay. 28. Okay. Okay. I don't see any further questions. I don't know if the panelists can ask question live. Otherwise, we will move to the next session. I guess it is the last one in this workshop. Okay. So next paper 165 will be presented by Imna Khamasi from Tunisia.
Hello, I am Emna Khamisi, a PhD student in the National Engineering School of Monastir, Tunisia. Today I will present my study about development of an energy sustainability index of mobility for Tunisian cities. According to the increase in energy demand of transportation sector has been increasing. Therefore, several impacts on the environment and quality of life have been generated. So it is necessary to quantify energy sustainability of transportation system. To do this, we need indicators of energy sustainability of mobility in order to calculate the composite energy sustainability index of mobility. This study can help to more development the adequate policies and reinforcing the sustainability of transportation system in terms of energy. During this study, we begin with an introduction, then we present objectives and case study, then we present energy sustainability of mobility indicators. In another hand, we will describe major steps to calculate the composite energy sustainability index of mobility, then we present methodology adopted, and finally we present results and we finish with the conclusion. Sustainability of energy development has become a political objective at the international level and has also become an integral part of sustainable development. Sustainability consists of three main dimensions: environmental dimension, social dimension, and economic dimension. Transportation is becoming a major issue of sustainable development, so it is necessary to establish a set of robust and comprehensive indicators to measure progress towards sustainable energy development for transportation. The objective of this study is to analyze the energy sustainability of the mobility in Tunisia by comparing the 24 Tunisian cities. Two main objectives: spatial analysis of the national transportation policies in terms of energy and measure the energy sustainability deficiencies related to mobility policy. During this study, we take Tunisian cities as a case study. Energy sustainability indicators of mobility, we have three main dimension indicators: environmental indicator, social indicator, and economic indicator. For environmental indicator, we have three main subdimensions: air pollution and greenhouse gas emission, energy, and environmental efficiency of vehicle. And such subdimension includes a set of indicators. For social indicator, we have three main subdimensions: safety, accessibility, and diversity. For economical indicator, we have two main subdimensions: expenditure and benefits of transportation system and users, and overall energy use. And such subdimension includes a set of indicators. How to calculate the composite energy sustainability index of mobility? All indicators were normalized and weighted using the principal component analysis method and aggregated to form composite subdimension and subdimension index. Then composite subdimension index were weighted and aggregated to form composite environmental index, composite social index, and composite economic index. Finally, the composite dimension index were aggregated to form composite energy sustainability index of mobility. The methodology adopted in this study is the one applied by Mehdina et al. In 2018. This method consists of normalizing indicator and weighting them using principal component analysis method and aggregated into composite subdimension index. Then composite subdimension index were weighted and aggregated to form composite dimension index. Finally, composite dimension index were aggregated to introduce a composite energy sustainability index of mobility. Step 1, normalization of indicators. Indicators were normalized using the max-mean method. 2, calculation of composite subdimension index. First, the principal component analysis method was adopted for the weighting of the indicator using the following equation. Then a composite factor index CFE corresponding to each of the latent factor G was calculated. Therefore, the composite factor index CFE was weighted and aggregated to form a composite subdimension index. 3, calculation of the composite dimension index. Composite dimension indexed in this step were calculated by aggregating the composite subdimension index calculated provisionally. First, composite subdimension index was weighted by the following equation. Then the composite factor index corresponding to the latent factor G dash was calculated by the equation below. After calculating the composite factor index CFE, this were weighted and aggregated to form a composite dimension. Step 4, calculation of composite energy sustainability index of mobility. In this step, composite dimension index were aggregated to form a composite energy sustainability index of mobility of Tunisian cities. This figure shows the composite dimension index, composite environmental index, composite social index, and composite economic index. These 3 composite indexes reflect regional inequalities in social terms between coastal and inland regions. This regional disparity are among the problems the country has to face, which are the results of inadequate transportation infrastructure and a lack of investment in transportation facilities. Results show that Sousse, Mahdiya, and Manouba are the most sustainable cities in terms of energy, while Sfax, Qasrin, Beja, Silena, and Tataouine are the least sustainable cities. Our study helps to better show regional inequality and point various transportation problems in terms of energy in some Tunisian cities and to guide the decision-making progress. Therefore, this methodology approach can be an effective tool for decision-makers towards the progress of cities. During this study, we adopted the methodology calculation of Mehdina et al. In 2018 with some modification to calculate the composite energy sustainability index of mobility for Tunisian cities and measure the energy gap between this region. Developing a comprehensive system of indicator and a composite sustainable energy index could be a precious tool to measure the state of the art and the progress of countries regarding energy towards sustainable development. Thank you for your attention.
Okay, that was paper 165, and now we're moving to paper 186. I think there is an error. This paper was already presented, so we can move to the next one.
Hello, my name is Fatima Zahra Riyahi, and this presentation is about PV sizing of a standalone solar carpet system linked to charging stations and its economic analysis.
Okay.
The outline of the presentation includes a background about the Moroccan energy sector, photovoltaic solar carpet, methodology and results, the amount of mitigated CO2, and the conclusion. The Moroccan energy sector known high energy import bills for fossil fuels and the yearly electricity demand expected to exceed 6.5% from 2015 to 2030. Therefore, the national aim is to increase electricity generation from renewable sources. The shift toward clean energy generation is encouraged by the installation of solar carpets, which are ground-mounted structures with a slightly tilted roof by 10 degrees. They come in 3 types, but the optimal type is the monopitch. Why we would think about this solution? Because many parking lots are taking over large areas which we could cover with solar panels for mainly energy production and also shading. In our case, the solar carpet is designed to supply electric cars as it is linked to charging stations and it is not connected to the grid. Looking at the methodology and results section, The methodology is based on the following process of 7 steps, which start by determining the daily energy demand of 65 kilowatt-hour per day for 3 electric cars, each of battery capacity is 22 kilowatt. As the daily AC load is high, the system voltage is then 48. The number of solar panels is calculated with the first equation, and it is 102 panels that will be mounted on the steel structure of the carpet with a power of 64.44 kilowatt. The number of panels connected in series and in parallel is 2 and 51 respectively. According to the software SAM, the energy produced during the first year is 42,150 kilowatt-hour, that is degraded by 0.5% every year. The capacity of the battery is determined from the first equation, and it is 7,966. Therefore, the whole system requires 40 batteries. For wiring, we need in series 4 batteries and in parallel 10, according to the equations 3 and 4. The inverter should be sized to provide 125% of the maximum load we wish to run simultaneously at any moment. The selected inverter has a power of 25 kilowatt, therefore we need 4 inverters. The charge controller must have a specific current and voltage determined with the first 2 equations on the slide. Also, we must account for the minimum input current determined in the third equation. Based on the fourth equation, we need 17 charge controllers. A crucial element in our system is to assure proper wiring between the components. So we have 3 different wires in the system, and their cross-section area is calculated with the equation shown on the screen. Therefore, the copper wires should be of 120, 325 mm square between the PV arrays and the batteries, between the batteries and the inverters, between the inverters and the AC load respectively. It is critical to protect the components of the system when the maximum load current is connected through installing fuses and switches. The voltage and current is calculated based on the equations shown on the slide. Performing an economic analysis is necessary to identify if the system is potential from an economic perspective or not. The capital investment is described by the table, and it is 661,000 Moroccan dirham. The life cycle cost is used to estimate the total cost of owning and operating the system over its useful lifetime, and it is expressed with the first equation. The lifetime of the PV array is 25 years, and of the batteries is only 5 years. Therefore, we need 4 extra groups of batteries, and their present worth is calculated with the second equation. The inverter lifetime is 10 years, therefore an extra 2 groups of inverters should be purchased, and their present worth is calculated with the third equation. We also have to account for the present worth of the operation and maintenance as expressed in the fourth equation. Summing all the costs, the LCC is about 1,460,000 Moroccan dirham. The levelized cost of energy identifies how much money must be paid per unit of electricity to recap the lifetime costs of the system, and it is calculated with the equation shown on the slide. The following table is an explicative table of how the calculations are made, from which the LCOE is 1.6 Moroccan dirham per kilowatt-hour. The payback period is an important indicator for the economic potentials of the system. As explained in the table, the payback is estimated to be 10.5 years. Finally, it is interesting to account for how much the designed PV carport mitigates emissions. This amount is determined by the equation shown on the slide, and it is estimated to be 657,357 kilograms. To conclude, the solar carpet PV system plays an important role in the domain of sustainability and transportation, as it provides shading for the cars and contributes to clean energy production. Most importantly, the analysis made and the obtained results for the designed system can further be applied in applications for solar PV system sizing. And this is the list of the references used. And thank you.
Okay, that was the presentation for paper ID 186, which correspond to standalone PV. It's a companion paper of the paper ID 187, which was presented in the previous session, which was related to grid connected. So sorry for the confusion. For now, we are moving to the presentation related to paper ID 153 by Mahmoud Badi from Islamic University of Medina, Saudi Arabia.
Assalamu alaikum wa rahmatullahi wa barakatuh. I'm going to introduce my paper, which is entitled Investigation on the Ground Temperature Profile for Shallow Geothermal Energy Applications in a hot and dry climate. This paper is a part of a huge project that's carried out now in the Islamic University of Medina. The project team members are Professor Muhammad Wazan, Dr. Mahmoud Badi, and Engineer Mohammed Shaheen. First of all, I'm going to give a small introduction that in hot and arid climate areas, shallow geothermal energy represents a very good local energy source that is also represents a promising alternative. So in this regard, it is essential to know and understand the ground temperature profile in order to design shallow geothermal applications and estimate the energy contribution. As we know that there are many parameters that influence the ground temperature profile, such as soil properties, surface cover, soil moisture, and degree of compaction. So here in our investigation, we are going to just emphasize on just two parameters, thermal diffusivity and depth of damping depth of the ground temperature. I'm going to investigate experimentally the effect of solar radiation and ground humidity on these two parameters. As you can see in this photo, this is a annual history of the ambient air temperature and the relative humidity of Medina in order to confirm that the area is dry. So we can see that the relative humidity is almost less than 20% along the year. This means this area is a dry area. We use the cathode model, as we see in this figure, in order to investigate experimentally the ground temperature profile. As you can see, we measured it. We calculated the temperature profile at different days, in different seasons. There are some photos of our project that we started in digging a well of 14-meter depth in certain area in Medina here in order to carry out our measurements. This is also some photos for the measurement. This is a schematic diagram of the arrangement of the ground temperature measurements. We can see that for the first 1 meter, we bought seven thermocouples in order to measure the variation. For the second 2 meters, zone 2, we bought 3. Also in the zone 3, we bought 3 thermocouples. And the last zone, which is underwater level, we bought only 1 thermocouple. The distribution of thermocouples here is started from sensor 1 to sensor 14. This is for the temperature measurement, and the last thermocouple is for ambient air measurement. This is a comparison between the predicted temperature profile and the measured one. We carried out this comparison on August 4. This figure shows that the reflecting manual that is used in order to eliminate the solar radiation, in order to investigate or study the effect of solar radiation on the ground temperature. Also, this is the period that we measured the effect of soil moisture on the ground temperature. This is the result of the first parameter, which shows the ground temperature profile before, during, and after covering the ground above the well at different depths. As we can see that the amplitude is becoming almost zero as soon as we put the cover, and as soon as we remove it again, it is returned again as it is before. This is the second figure for the damping depth. We can see that before putting the cover, damping depth is almost constant at around 5 meters. As soon as we put the cover, we can see that it is increased to around 14 meters. Then as we remove the cover, it is returned again to its initial value. This is a result of the second parameters of the water soil humidity. We can see that the amplitude decreases also significantly as we add some water to the soil. This is a damming depth also result. We can see that the dry soil has low damming depth compared to wetted soil. From this investigation, we can get these conclusions. First, that the effect of solar radiation on the ground temperature is limited to layers close to the surface, as we can see, because we used it for just a short time of period. A considerable effect of the solar radiation on the damming depth is noticeable. It is increased, as we can see, during the period when the ground surface is covered and decreased otherwise. The damming depth also increased as the soil becomes wet compared to dry soil. So in the second phase of our project, we are going to evaluate the effect of these parameters on seasonal period, not only just for a few days. So the insulation cover will be applied for a long time. Also, more water will be added at lower temperature to understand better the effect of soil humidity on the ground temperature profile. At last, I'm going to thank the research deanship of the Islamic University of Medina for giving the support, the funding support for our project. Thank you for your attention, and I am ready for any question. Jazakumullah khair.
Okay, that was the presentation for paper ID 153, and now we are moving to paper 192 that will be presented by Mrs. Rita Al-Boukili from Mohammed V University, Rabat.
Hi everyone, my name is Rita Al-Boukili, PhD student at University Mohammed V of Rabat. As you can see on the screen, our topic today is entitled Improving of the Rheological Properties of Bitumen Clay for its use in clay brick production. Obviously, clay was and still the prime construction material through the ages. As we all know, using clay on construction has a lot of benefits. It's a recyclable and energy-saving material with a good thermal properties. In Morocco, clay is an abundant raw material with a variety of structures and compositions. Unfortunately, its exploitation is considered poor and insufficient. Consequently, the Moroccan government imports clay products from other countries such as Spain and Italy. For example, Bitumen is a mountainous region in the Middle Atlas situated near Ifrane city. This isolated poor village is desperate for affordable housing with decent thermal properties. The cheap, the natural and the affordable raw material in this region is clay. Unfortunately, this clay was found to be not suitable as a raw material for the clay brick industry if it's used in its raw state because of its weak plasticity. So the objective of this study, and in the perspective of a sustainable development of the region, this study aims to improve the properties of this unexploited clay and make it suitable in the clay brick production. The exploitation of local clay resource of this region in the production of building materials have many beneficial impacts. Clay-based materials will be produced locally with similar features and lower cost than the imported ones. The cost and carbon footprint of material transportation is also minimized. Now, let's talk about the used material in this study. We used Bitumen clay extracted from Bitumen region and extra brick clay recovered from a brick manufactory named Extra Brick and located in Meknes city. This clay was used as a reference in this study because it produced good clay bricks with good performance and good properties. And finally, bentonite clay. This clay was used as an additive in this study. The first step in our study is the raw material characterization. We performed XRD diffraction and grain size distribution test. We also performed Atterberg limits of our 3 samples. From all the conducted tests, we can say that, the weak plasticity of benzene sample is related to its low clay fraction, the absence of expandable or swollen clays, the dominance of quartz. However, extra brick sample is considered as plastic clay because of its large clay content and the presence of swirling clay. From all this, we can conclude that, or we can suggest that the addition of bentonite clay to benzene sample can improve the plasticity, and thus it will also improve its performance.
Okay. So that was the last presentation in this session. Now we are moving to the discussion for, let's say, 15 minutes. I see that there is 3 questions there in the, okay. The first question is, did you take the, did you quantify the polluting element in your environment? I think that is, this question is dedicated to paper, the paper from Tunisia, paper ID 165, Mrs. Khamasi. Can you
Okay,
answer
hello.
this question? Yeah.
Okay. Hello. Thank you for your question. Yes, we use during this study, we use some indicator to quantify air pollution and greenhouse gas emission caused by transportation system, like air pollution caused by transportation, greenhouse gases caused by transportation per capita, per VKT, per area, etc.
Okay. There is one more question from the same attendee. What are the difficulties that you encountered during your experiments?
Yes, okay. I have some difficulty in the collect of data to quantify indicator from the case study of Tunisia.
Okay, I would say the difficulty is related to the availability of data.
Yes.
Okay. Okay. I'm checking if there is questions in the chat. I don't. There is no question there. No question there. Okay, I don't know if there is some questions from the panelists that can be asked live.
Professor Benhamou, I have one question,
yeah,
please.
Go ahead.
Okay, my question is to ID 186. Fatima Zarari Akhi, what is the trade-off between economic and energetic results of your PV system?
Hello, can you hear me?
Yeah.
Yes,
Go ahead.
So I want to also mention that the paper 186 is also related to the paper 187, and basically both of them, they have investigated the both system, whether we want to opt for a standalone with no grid or a system with a grid. Basically, from an energetic perspective, both of them they meet the energy demand. So from an energetic perspective, we could say that they are optimal. But from an economic perspective, through the comparison, of course, the grid connected is much more cheaper than the standalone. I hope this answers your question.
Yes, okay, thank you.
You're welcome.
Okay.
Yeah, okay. But the problem is how to deal with this grid connected PV with the law that is going to be implemented for auto producers. Okay, I see that there is 1, 2, 3 questions. The first one is for paper 192. Yeah, the last one, Mrs. Rita Al-Boukili. It's not a question yet. It's not finished. Sorry for this. The presentation was not finished. Sorry for this because maybe there is a technical issue in the video. So the question from Zahran Nafah for paper ID 153, Mahmoud Badi. What are the difficulties that you encountered during your experiments?
Yes. There are many difficulties, sir, that first from getting permission to dig wells, then connecting all these together, and also to account for weather condition, because we selected August, which the temperature above our head was around 49. So we was working very difficult weather, but alhamdulillah, the result acceptable, and now we are going to second phase.
Okay, I have a subsidiary question to you, Mr. Mahmoud Badi.
Yes, sir.
Yeah, the duration of experiment, you say that it's what, just 1 month? What is the duration of the experiment?
The measurement is still till now, but we started in July. But I mean that we are receiving and recording data each day till now. But we are going, I mean that to now we are talking about seasonal variation, not only few days like our paper. So we are going to investigate these effects based on seasonal period, not only just a few days.
Yeah, okay. So these first are preliminary results.
Yeah, exactly, sir. Yeah.
Yeah, because the duration should be at least 1 year.
Yes, should be, because
yeah,
it should be, exactly.
Yeah, just for your information, we conducted similar experiments in Marrakesh.
Yes.
Yeah, for since 2015, yes. And there is two publications. One in this conference related, yes, to this experiment, and the other one is in the Thermal Science Engineering Application Journal. Professor Uzan, maybe is aware about these experiments, because I know him very well, Professor Uzan. Okay, so if there any other question to the presenters, to the authors, I don't see any further question. I have a question to Mrs. Rita Al-Boukili. Sorry for the technical issue with your video. But I guess that your objective was to improve the plasticity of this Bersmim clay. Now, the plasticity is not the let's say the most important. Yes, it's important, but it's not the most the most important parameter to get this clay suitable for earth construction. There is other parameters such as the main parameter, I think, is the durability of this. Did you check this? Water absorption, durability. Mrs. Bukili, can you unmute your mic, please? You can speak live. You can answer the question live. Mrs. Bukili? Can you unmute your mic, please?
Yes.
We don't hear you, no. You have to unmute your mic.
Hi.
Yeah.
Do you
I
hear
say,
me?
okay, go ahead. Yeah. It's okay
yes,
now.
Yes, Professor. In this study, we performed several tests and several analysis to our clay. But we found that the main problem in our clay is that it has a weak plasticity, because leading to a weak mechanical properties. The bricks that we made from this clay were too weak, and they were under the minimum standards. For this, we characterized our clay, and we compared with another clay, I can say that it's an industrial clay that is already used in the clay brick production. And we compared the microstructure of the two clays, and we noticed that the main cause, or the main factor that weakens the mechanical properties, it's the weak plasticity that is caused from the mineral composition and the grain size distribution, and also the nature of the grains, the small grains that composed our clay. For this, we performed several characterization tests, as I already said, and we choose, or we suggest, that the addition of the bentonite clay, which is a small clay, clay with the small particles, and with the expandable properties or sweating properties, may act as a binder or as a glue to the whole soil. And for this, we added several percentage of this additive, and we performed the rheological properties, which is not shown in the video, because I don't know why, but the video is not finished. We performed the rheological measurement, and we found that the addition of this additive improves the rheological properties of the soil and makes it closer to the reference sample, which is extra brick clay.
Okay, so you are focusing on mechanical properties.
As a first step, yes.
Yeah, okay, but also
mechanical properties.
You should also address the durability of the blocks, or the bricks.
Yes.
Maybe you have to add some stabilizers to the brick to have it more resistant, more resilient to water absorption, which is the main problem with the earth construction.
Yes, Professor, I agree with you, but this is the objective of the whole study. But as a first stage, we focused on the mechanical properties first, and then we're gonna move to the thermal and the durability properties.
Okay, that's fine. Thank you. I have
you, Professor.
one further question to paper ID 153, Mr. Mahmoud Badi. It's about the probes. How are you dealing with? I see that your hole is a small hole, and you are using a PVC tube to place the probes, the thermocouples. How did you deal with this? What is the diameter of the hole you have drilled to implement the probes inside the ground? Mr. Mahmoud Badi, are you here? Mr. Badi? Or one of the co-authors? Mohammed Shanin, Mohammed Uzan? No one is here? Okay, maybe he left. So, I don't know if there is a further question from the panelists. To be asked live. If not, we are now at the end of this last part of the workshop 4. I have to thank the organizers of this workshop and the keynotes, the 2 keynotes, and also the authors that have presented their work there.
Thank you very much, Professor Brahim bin Hamou, for sharing this session. Thank you also for keynote speakers, Professor Parham Merziai and Ranzani from University of Nottingham, UK. Thanks for the chair of this workshop, Professor Elisio Orlando from University of Rio de Janeiro, Brazil. Thanks for all organizing committee of this workshop, Professor Najman Rossi, Professor Mohamed Garoum, Dr. Zaid Roumani. Thanks for Professor, another time for Professor Brahim bin Hamou for sharing this session and the first part of this workshop. Thank you very much, and hope to see you in the next edition.
Thank you to all. It was a great workshop with more than 200 participants.
Thank you very much.
Okay.
Thank you.
Thank you to all, and see you in the other sessions, in the IRSEC sessions.
Yes, now we switch to another workshop, workshop 1. Advances in lithium-ion battery and beyond. This workshop is shared and moderated also by Dr. Amin Khalil. I think Dr. Amin Khalil with us. Dr. Amin Khalil is an Argonne Distinguished Fellow and the leader of the Advanced Battery Technology team at Argonne National Laboratory, where he is responsible for directing the research and development of advanced material and battery systems. Dr. Amin is also the Deputy Director of the US-China Clean Energy Research Center and serves as a Fellow of the US National Academy of Inventors and committee member of the US National Research Council at US Academy Science and Battery-related Technologies. He is an adjunct professor at Stanford University and holds a joint appointment as professor at the University of Chicago and senior fellow at the Northwestern University, Argonne Institute of Science and Engineering. Dr. Amin holds over the 207 patents and patent application and has 664 publications with Google H index of 136 from 1998 to 2019. Dr. Amin was one of the most cited scientists in the world in the field of battery technologies. Dr. Amin, the floor is yours.
Okay, well, thank you, Yusuf. Good morning and maybe good afternoon for the folks in Morocco and in Europe. I'm actually in my hotel room in Washington, D.C. So I have to apologize. I will not be able to moderate the discussion, but I've already asked my friend Gao Liu from Berkeley and Moayed to do just that, because I have to leave after the last talk. Just my apology. First, I would like to congratulate you, Yusuf, for this very successful IRSEC'21. As we all know, it is a very large and successful international meeting that address a number of different topics, including advanced battery technology, obviously, which is a topic of this workshop, but also energy semiconductor for photovoltaic, renewable resource forecast, and solar energy and green hydrogen. So it's very, very broad topics, which are of big interest to the world community at the moment. So today's workshop is again on battery technology. So we are very fortunate to have with us very outstanding keynote speakers from United States, China, Europe, Germany, and France, and Spain. And they will be addressing a whole range of different topics within the lithium battery, either advanced battery for automotive or advanced electrolyte, either polymer, ionic liquid, or solid state, and also sodium-ion battery. I would like first to introduce the first speaker. I'm a little ahead of time, maybe, but we can go up. So we'll give Wenjian more than 30 minutes if I know she can speak more than that. So let me introduce the first speaker, Dr. Wenjian Mattis. She is a good friend and colleague. She's also the Chief Technology Officer of Microvast, which is one of the largest battery company in the United States with a significant presence in China and in Europe. Before joining Microvast, she was a senior scientist and manager at Dow Chemical, and she got her PhD from Penn State University. You can easily check her CV by clicking at her name in the webpage of IRSEC. And she will be talking about a high safety and high energy lithium-ion battery for application in automotive application through a novel material design. So Wenjian, you have almost 40 minutes. If you want to start, you're welcome.
Sure. Yeah, let me share my screen. Share screen. Okay. Oh, you can't start screen sharing. Oh, so Dr. Min, you may need to. Okay, good. Thank you. Everyone see my screen at the full screen mode?
Yeah.
Good.
Yeah, we can see it, yes.
All right, good. Hey, good morning, good afternoon, everyone. Wenjian Mattis here. I have been working on the development of lithium battery technology for over 16 years. I hold 22 papers, 81 patents. In Microvast, I'm responsible for the development of battery materials, cells, module, and pack from R&D to production. Yeah, thank you, Dr. Amin, for your introduction and giving me the opportunity to speak at IRSEC'21. It's my great pleasure to talk today about Microvast and how we work to enable the competent high-energy electric vehicle batteries and mitigate its safety. Before we proceed, I'd like to ask you, please refrain from using or posting any information shared today without our permission. Firstly, at the glance of the company, Microvast was founded in 2006 in Houston, Texas. We dedicated in developing battery technology for electric vehicles, has been working on this for over 15 years. And we followed the market, established the R&D, production, and the business, started in China, and then expanded into Europe, and now in United States. Today, our batteries are integrated in more than 28,000 vehicles that is running in 160 cities over 19 countries. And with those electric vehicles, altogether, they have traveled over 3.8 billion miles in the last 10 years. Earlier this year, we raised about $820 million and went public on NASDAQ this year on July 26th. Microvast is fully vertically integrated, meaning that we design, develop, and manufacture a complete battery system, starting with battery materials, cells, module, and pack, including the battery management system, thermal control, high voltage charging box, and also the charging station. We will discuss more in details later. The three underlying battery features Microvast envisioned 15 years ago were fast charging to ensure the mobility, long life to maximize the total cost of ownership, and the design for safety from the start, given the critical demand for high energy density. Those features are foundational to the innovative technologies and the products that we're delivering to the market. Here, I'd like to give you a snapshot of our geographic footprint today. We are headquartered in Houston, Texas, and have established the factory in Huzhou since 2011. We have 3 gigawatt-hour from the cells to pack production in Huzhou. Totally have about 1.7 million square feet of the production line, including the cathode, electrolyte, anode, and separator production. And we established the module pack production facility in Berlin, Germany. And the whole building can hold about 6 gigawatt-hour. Currently, we commissioned 2, supplying the Europe right now. And earlier this year, we have acquired this existing facility in Clarksville, Tennessee, which is about 45 minutes northwest of Nashville, Tennessee. And here we have 85 acres and over 577,000 square feet of existing building that is being converted into a cell to pack production line, holds for about 4 gigawatt-hour. And Dr. Amin, in the beginning of the meeting, introduced the Microvast is one of the largest cell producer in the United States. This statement is accurate. Being an American company, building a 4 gigawatt-hour cell to pack line, making Microvast the largest USA battery suppliers in the States. And so this was announced publicly. We purchased another existing facility in Orlando, Florida. This will be established as the global innovation center for Microvast. Yeah, so totally we have about 8 acres, 75,000 square feet, over 250 parking spots, and over 100 offices, and 25,000 square feet of this large working space, workshop space that we will establish from materials to pack development in the States as well. We plan to hire about 150 researchers. Yeah, so this is a community sitting by I-4 in the Interstate 4, and very welcome for the attendees of the meetings today. Come to visit Microvast. We communicate, discuss about the newest technology, how to make the high energy density cells and safe cells for the electrification of the world, not only in commercial vehicles, passenger vehicles, but also in the stationary energy storage, including our consumer electronics. Yeah, so on this page that demonstrates the showing cases for the vehicles and the energy storage that Microvast has delivered to the world. What's special about this page is in every single of this picture, there are Microvast batteries. We took some of these pictures. So those are the examples of the 28,000 xEVs that Microvast has been powering, including 1,000 red double-decker and all of the heavy-duty AGVs in the port of Singapore that are moving heavy containers. We are also supplying passenger vehicles for SAIC, Shanghai Motor, the largest OEM in China. And Microvast makes the full concentration gradient cathode material, has successfully scaled it up to 600 tons per year at the reactor size of 20,000 liters. And this material can supply for the passenger vehicles, commercial vehicles, including the consumer electronics. And the aramid separator created and industrialized by Microvast is a great choice for the consumer electronics separator, since it's thinner than the current separator in the battery that we use in the cell phone, and can offer outstanding safety. So we will talk about that later in my slides. So this slide demonstrates the comparison of our products with our peers, the largest ones in the world. We are uniquely positioned in focusing on the commercial vehicle space, while most of our major peers are passenger vehicle focused. Why do we focus on commercial vehicle? Because of its earlier EV adoption, a broader range of use cases, more stringent performance requirements, resilience due to use under the harsher conditions, such as the passenger vehicles operate a couple of hours per day, while commercial vehicles need to operate 8 to 24 hours per day. Therefore, commercial vehicle batteries need to double to quadruple passenger vehicle batteries cycle life, and to offer faster charging and higher power capabilities. The total cost of ownership is calculated over longer lives, so that heightened the customer's focus on performance. The technology for commercial vehicle is more difficult, but more profitable. By the way, the commercial vehicle market is massive. So the CV is our prioritized choice with our current capacity. And as a matter of fact, I mentioned earlier, we are supplying for the passenger vehicles. Microvast offers all the major chemistries on the lithium battery market, including NMC, LFP, LTO. The products on the top 3 rows that have been in the production as early as 10 years ago, and each of them outperforms their peers. Those are third-party tested and market validated, both through the customer wins and extensive real-world deployment experience. So the last row is the next generation battery product to come. With this product, we won the R&D 100 award together with Dr. Amin's team. This technology has been validated by Argonne National Lab. It can offer 30% higher energy density comparing with the current passenger vehicle technology, and still yet can offer fast charging, long cycle life capabilities. So the components as a key to enable this cell product, which we did use higher than 90% nickel cathode material with the full concentration distribution, and also with the aramid separator, non-flammable electrolytes, and also craftily designed the silicon carbon components that is patented by Argonne National Lab. So those technology won us this R&D 100 award and draw the attention from several prestigious OEMs in Europe. Currently, these are being tested in their factory. So we have more products in the pipeline, such as the solid-state battery, lithium metal battery that can reach higher than 1,000 watt-hour per liter energy density, and also 80 degrees Celsius high temperature cells, which is highly appreciated by a high-end PV company for a sports car application. On the next page, I'd like to put things in perspective. What kind of BEV performance can we create with our product? On the right, we listed a general spec of a high-end BEV in the market. But if we replace the battery with Microvast high energy density product that has been in the production since 2019, the NMC-2 that we listed on this page, then this whole car can be fully charged within 30 minutes. And with one full charge, our battery can offer 20% more mileage and roughly 3 times of cycle life. With those parameters together, that can lead to about 1 million miles of lifetime throughput. This is 3 to 4 times of a regular EV. But of course, we don't need 1 million miles for a passenger vehicle, not yet. But that is exactly my point. Our batteries are made for more demanding applications, and the passenger vehicle commodity batteries cannot meet the lifetime requirements of a commercial vehicle. Then it would need the multiple replacements that can greatly damage the total cost of ownership. My immediate question may rise, how? How could you do it? I would like to summarize our technology success into those 3 columns. Microvast has the broadest chemistry, the capability of manipulation all the way into the material level, and a whole spectrum of the cell products which have been verified and benchmarked that are highly differentiating. From the end user to the chemistry, we have this complete approach, the full customization that can lead to the faster development cycle, higher efficiency, and cheaper development cost. At the meantime, with a better quality guarantee. And now let's discuss each column in detail. The heart of a BEV is a battery pack, and all the energy in the battery pack are from the cells, while the performance of the cells fundamentally depending on battery materials. To build the best, highest performance battery, that's what driven Microvast into this vertical integration, just like Apple building microprocessors. Microvast has over 1 decade of designing and manufacturing expertise in battery components, from a cathode, anode, to separator, to electrolytes. We gain an intimate knowledge of how those components would interact with each other under specific conditions. And this differentiates us from most of the battery makers who source their components from vendors. But people may ask, well, other battery makers can also make materials, but it's important to note that the cell makers do not have the right to produce the materials they did not invent or have the license for. While Microvast has invented or licensed and manufactured all those 4 key battery materials to ensure the unique performance in the cells. And that can further lead into the module and the pack products. And with this material technology, that can ensure our leading time, because the material patents are the strongest patents that are legally protected for decades. Our success is founded in our deep technology portfolio, which is fully owned and protected by over 550 patents and thousands of know-hows within the company. Amongst all the battery materials Microvast makes, 2 products stand out that no one else has in the world: the 100% polyaramid separator and the full concentration gradient cathode material that I will talk about one by one. The current separator in the market are mostly made of polyethylene, polypropylene, the same material as plastic bags, plastic bottles. Microvast manufactures one of the kind, the high temperature 100% polyaramid separator that is based on the same material as bulletproof vest. This material has outstanding thermal, mechanical, chemical, and electrochemical stabilities. Polyaramid itself is intrinsically non-flammable. It also does not melt. It does not dissolve in any solvent. But that would make it extremely difficult to process. But yet, Microvast made it into a 10 micrometer thick, several meters wide, thousands of meters long industrial separator product that increased the shrinkage temperature of the PE-PP separator from around 150 degrees C to 300 degrees C Celsius. That's nearly 600 Fahrenheit. But why do we choose 300 degrees C as the goal? As we know, the cathode materials, particularly at high energy density cells, is a high nickel NMC, which at fully charged states, that's the most unstable, most unsafe state, they would start to decompose around 200 to 230 degrees C. And the separator, its only goal is to separate the cathode from the anode. But if the separator shrink before the batteries being disabled, then the massive internal shortage could happen. And several accidents have happened due to that, such as 787, the recent explosion of the stationary energy storage in Beijing, China, and also suspected to be the root cause of the GM battery, and also the Note 7. Well, when we have the separator designed, we want the separator to overlast the cathode material. If it can hold about 300 degrees C, so the cathode material would start to decompose, and the separator holding its forte, and after most of the electrical energy has been released by the chemical energy, the thermal energy, the separator would now be finished the task of preventing the massive the shortage. And beyond that, we also have the thermal control, the BMS in place to have the whole system have the redundancy of a safety design that we also would briefly mention later on. But while the temperature rises, the cell could, the electrolytes it would evaporate, the internal pressure in the cells would increase, the cells could break open, and if at the time the flammable gas rush out of the cells, meeting the high temperature, high voltage, that could cause explosion. Therefore, that's why we designed this non-flammable electrolyte. Itself can stay non-flammable in its liquid phase, including the gas phase. So with this design, we aim to increase the safety margin. But still yet, it does not solve all the problems because of its decomposed product. Well, at this high temperature or high voltage reaction, the product could still be flammable. But our goal is to increase its safety margin. The same reason for the aramid separator and the full concentration gradient cathode material. So another product Microvast produces are this FCG cathode. So this cathode material offers all the energy in the lithium battery and also takes more than 50% of the cost in the battery. So Microvast is the only one in the world who can produce FCG cathode material in the industrial scale. In this illustration, the FCG material differentiates from all the other homogeneous cathode material in the market. This technology allows us to be specific about the distribution of the transition metal elements so that we can maximize the energy contained in the particle with high safety and the lowest cobalt content to minimize the risk and minimize the cost. The FCG material we produce can offer 20% higher capacity than what's available in the market, and yet stays 10% lower in cost because we minimize the cobalt content. So this material is also validated by Argonne National Lab, and we have won the low-cost fast charging US ABC project with this material as well. So in the second column, we have this whole spectra of the cell products that allows Microvast to access the application of all industry. The broadness makes us less vulnerable to be the commercial success of a single technology. So I mentioned about the LFP supplying to SAIC. So in this project, we actually competed with CATL, the largest battery maker in the world, and we won this project by performance. And also demonstrates that Microvast has the quality control in our mass production line, meeting for the most stringent automobile standards. The last but not the least, we have the internal built the vertical integration from R&D to production. So with the vertical integration, that can confer significant competitive advantages to shorten the product development cycle, to win the race in tech evolution by eliminating the need to communicate with the vendors. And that can minimize the cost, ensure the quality control from the materials to the end product, from R&D to mass production, and we can customize the solution to the client's needs that help us to build a higher bar to competitors because of the material development takes decades. It also gives us the flexibility to work seamlessly with any customer. We can offer at the whole power solution level, at pack level, module level, cell level, and in the future, in the component level. Another important, feature of Microvast innovation and product design is the extensive simulation efforts that helps to optimize the battery system and predicts the potential issues in the computer before encountering the issues in physical devices. So during the fundraising, our investor hired a prestigious third party to do the technical assessment on Microvast. Here are their conclusions. We talked about several components in the previous page that enables the high energy density, high safety, fast charging products. Each are the gradient cathode material, the 100% polyaramid separator, and the non-flammable electrolyte. And their contribution on the cell energy density, the charging rate, cycle life, and the safety are summarized by the third party as below. So the black bar showing the industrial leader, and the dark blue are amongst the best in the class. So the cathode material in their evaluation for all those 4 aspects are amongst the best in the class. And the non-flammable electrolyte, its most advantage is in safety. It's an industrial leader. And as for aramid separator, so it only contains less than 1% of the weights in the cells, and so does not change the cell energy density much, and would not affect the cycle life much, but its contribution is still mostly in the safety, which is crucial for all the applications. Yeah, so this also coming from the third party. On the cell level, every company have published their roadmap, and compared with the largest, the best in the field, Microvast products that are leading in both of the volumetric energy density and the gravimetric energy density. And comparing the performance that we briefly touched in the comparison, and also in the market applications. And here are 2 of our products that to compare with the leading performer and the standard performer. So as noted here, the leading performer data coming from the LG battery, and the standard performer coming from the China EV cell maker. And most of the cycle life is RAM from 0 to 80% SOC. So that's what coming from the third-party database, comparing what's in the market. So that's Microvast product has been deployed to the market. So that's a fair comparison, apples to apples. And as for the energy density, our HNCO, that's NMC-2, is leading the energy density. And still yet, it can do the fast charging. And for a lower energy density product, it can run 3C cycling between 0 to 100% SOC for over 8,000 cycles. So considering this case in a commercial vehicle, even if we charge twice or 3 times a day, this battery can last 15 to 20 years. And as for the safety, both of these products is way beyond the leading performer. And for the future technology, we proposed such as the solid state battery. The close one would be the silicon containing product that we are would be in the SOP phase in the next 2 years. And also would keep improving the energy density by using lithium metal as an anode. We're also working on this project with Dr. Amin's team together, and also developing the solid state battery that has been a project in Microvast since 2015. We have over 12 patents in this area, and also with a high temperature operating cells. So more are being developed. So with the future technology, we are at the frontier of the innovations. So the comparing with the competitors as the time scale of the roadmap proposed, that's where Microvast is standing. So as I mentioned, we internally have the vertical integration from the cells all the way to the final product. And that helps Microvast to gain the advantage in development time, and also a thoroughly in control BMS, because the BMS need to understand how the cell would perform at different SOH, SOC, different temperature, different power requirements. And we have developed the cells from the R&D, has been going through the intensive testing for over 3 to 4 years before it's getting into the mass production, and how to apply that in the module, the optimal thermal control, the pressure to be added, the pack design. So that's all in this the vertical integration designing, and the BMS have the intelligent control And we also have that in the digital twin that can run a simulated virtual vehicle on the cloud. While on the road, you have this actual the vehicle operating, and you can always comparing the predicted and the tested can send out early warnings. Yeah, so that gives us the advantage in the pack level. So we are winning in both the volumetric and the gravimetric energy density as well. So comparing the charging speed, that's what microvast is leading by far. So that would offer more mobility to all kinds of applications. And for some, even the stationary energy storage would require, such as the wind storage, that would require fast charging occasionally, and that can also accommodate this application. Yeah, so the microvast safety design, as I mentioned, so first of all, that has demonstrated good safety performance for the last 10, 11 years. And we have a multi-layer of safety design from the materials, which is fundamental, that can prevent the mass, the recall from happening. And beyond that, by fully understanding the cell performance, the pack design, the thermal propagation, insulations, the pack design, and most crucial, the BMS that can need to take in place by separating the responsive time. And we also work closely with the OEM on the vehicle design, the vehicle control units as well. So the vehicle needs to respond the first to send out the most of the early warnings, and then followed by the pack with a separated responsive time. Then the pack cell to the materials that would go to the core of this, the whole technology there. Yeah, and for the BMS, we are having the ISO 26262 certified at the C level, both on the software and the hardware. Yeah, so the cells has been through the most vigorous test by all standards, the GB, the EU CAR, including USABC. We are working on a TAP project on. And even on the pack level, it has been tested for the electrical abuse, mechanical, thermal, environmental. This one is impressive. So the whole pack is sitting on the external fire for over 10 minutes, and the pack remains safe. Yeah, so here I want to give you a glance at microvast mass production line from all the 4 key battery materials to standardize the cell, module, and the pack. There are videos available online if you want to review more of our company, facilities, and our business. On this red corner, there are 2 examples of the power system solutions offered for delivery trucks and commercial buses. We have invested, yes?
Jen, there is only 2 minutes left, so.
That's my last page though.
Okay, good, yeah.
Yeah, so yeah, I can welcome questions now.
Question will be after the 3 talks. I know that you will not be able to join us for the discussion, but if there are questions, we will forward them to you by email so you can respond to the interesting parties, okay? Excellent. Okay, so well, thank you very much, Jen, for this interesting.
Excuse me, Dr. Amin, she can answer questions before the next talk is possible.
Okay, yeah, so all right, so let's see if we have any questions from the audience. I don't see any. Obviously, this is more of an introduction of the impressive technology that microvast has. So if there is any question regarding automotive battery, I think she is the right person. Okay, let's see. That can answer these questions. So yes.
There is some questions. Okay,
can you read them? on my behalf.
Yeah, thanks for the great talk, and you presented LTO-like anode for lithium-ion batteries. Please, any insight about using mixture of graphite and silicon?
I'm sorry, using the mixture of graphite and what?
Yeah, graphite and silicon.
Oh, on the silicon, yes, yeah. So as for the silicon material, generally two families, right? So pure silicon and also the silicon monoxide. Silicon monoxide have a smaller expansion, but also coming with a lower the capacity that can come with larger particle size. And what we observe with this material, its first cycle efficiency is lower, but afterwards it would have a flatter decay. So if you have the technology of the pre-lithium supplement, that would be a good material to use. But again, need to look closer into this material. Some would just be simply the mixture of silicon with silicon the oxide instead of monosilicon oxide, right? And in the other class, silicon material, because of the 4 times expansion, this material needs to nanosize so that it can hold its integrity. And that comes in different formats. It can be the particles, it can come in the silicon nano fibers. So all of those materials also need to have the surface to be coated by the carbon to avoid the first cycle efficiency consuming too much lithium. And Dr. Amin actually have a patent published on this using the deposit grow silicon in between the graphene layers that we have tested the material. It shows a good performance in the lithium battery. So really need some company to industrially commercialize this material to be more massively used in the high energy density cells.
Good. So I just look at the question now. So there are 2 quick questions that on silicon. It seems to be the audience is interested to silicon. The first one is, what is the ratio of silicon to carbon that is usually used by the industry, and in your case? Yeah. The other one is, what is the strategy to stabilize the capacity of silicon during cycling?
Sure. Yeah. So that is depending on the energy density requirements, also correlated with the cycle life. So for the cells about 300 to 330 watt per kg, the silicon component in the total anode material, if that's silicon, 100% silicon, that would be about 5 to 10%. And that can come in the silicon carbon composite. And this composite can contain about 15 to 30 or 40% of the silicon. If you want to reach a higher energy density above 330, then the cycle life would reduce. So then the components, total silicon components in the anode material would be above 15%. But if apply silicon mono oxide, then that can compose about 20 to 30% or even above when you want to achieve 350. So the key to apply the silicon material well is to accommodate its volume expansion from the beginning. Therefore, with such as the CNT, this type of conducting carbon would be helpful, so that it would stay in contact with the material, even with the large volume expansion. But then the key is to the well dispersion of this conducting carbon. And of course, as Dr. Gaudiu has been studying the binders that better can also help with the conductivity, but still yet it needs to be resilient, better have the self-healing power, but at least got to bind with the material tightly and kind of grow with the expansion. And also the electrode design, the porous electrode design is also crucial. And then beyond all that, the pre-lithiation is a key technology, and how to industrialize that with a high safety, low cost is also another focus.
Excellent. So the last question is from Mohammed Shakir, who is from Renault. He's one of our panelists. Do you want to speak up, Mohammed?
Yes, thank you, Sekhari. Thank you, Matisse, for your presentation. I have just one question related to energy density, volumetric energy density, especially you claim that in your pack, your energy density is higher than your competitors. And you mentioned also that you show that your energy density at cell level, it's comparable. The question is how we can explain this high performance at pack level. Did you maybe design, or you use, for example, cell to pack, or can you say some words in this way, please?
Yeah. So the pack energy density and the cell energy density, those can be varying because of the cell format. So cylindrical cells would have a really high volumetric energy density on the cell level, but not necessarily on the pack level, because it cannot pack really tightly, right? It can only use about 68% of the volume. So the pouch cells and the prismatic cells would have a higher packing efficiency. Microvats make pouch cells, and comparing between this, the prismatic cells would have even higher efficiency because it's already kind of like in the confined space with a good mechanical protection already, stability. But for the pouch cells, comparing with prismatic cells on the cell level, it actually gains advantages in both volumetric and prismatic energy density because of its thin skin. So in the end, those two are in the fair competition, almost similar in the pack level. But what Microvast gained on the pack level of the energy density is by doing close to what C2P. So in each of these module, we have about 72 cells. So that's a big module. And to control this big module, that would require thorough understanding of how this thermal control field to be designed, how to prevent the thermal propagation. So with all that, the know-how and the knowledge in place, that we can minimize the components, while at the same time maintains a uniform pressure field, the thermal field, and also with the high safety design. So that's how we can gain the advantages in the whole pack level. And also in the pack, we have the bottom housing and the cooling plates all in one that also saved some weight. And for the cap, we use the composite as the cover of the housing that also reduced the weight. So with multiple levels of measures.
Okay, well, thank you, Dr. Mattis, for this really nice discussion. We're going to move forward now with the next speaker, my good friend Theo Rojo, who is a full distinguished professor at the University of the Basque Country. Until recently, Rojo was the scientific director of CIC, which is a very big national lab there. He has published extensively in the battery field with over 600 papers. He's very well known. He's actually a member of the Royal Academy of Spain and other academies as well. And he's very well known for his work on sodium-ion battery in the world. And he will be talking about, I don't see his, he will be talking about, all right, so I need to see his title. Can you move?
Sorry, can you give me permission?
Yeah, so, okay. You have it now?
Yeah.
So, so he'll be talking about advances, advancing in sodium-ion battery, the critical role of electrode selection. Theo, please go ahead.
Thank you. Thank you very much. First of all, I would like to thank the organizing committee for inviting me to participate in this interesting conference, in special for Professor Khalil Amin. My talk today is Advancing Sodium-Ion Batteries, the Critical Role of Electrode Selection. After a short introduction, I am going to speak about the retrospective advances in sodium-ion batteries, basically anodes, cathodes, and I am going to speak also the relation, the electrolyte interfaces, the industrial developments, and summary and conclusions. Sodium-ion batteries is an nascent technology. There are currently significant developments and rapid advances, And also there is already commercialization of the first generation systems. Regarding the publication of patents, and we can see important and exponential increase in the publication of patents in the last 10 years. Sodium-ion batteries, there are some advantages and disadvantages. The main drawbacks are electrochemical performance, the gravimetric and volumetric energy density, and the difficulty in achieving broader voltage window. So further research is mitigating this challenge. So I am going to start with the anodes, speaking about the most important materials focused to the applications for the market. I'm going to focus my presentation in carbon derivatives and phosphorus derivatives. Regarding the anode materials, we can divide it in two groups. Regarding the energy density, one of them 250 watts-hour kilogram, organic electrodes and oxide materials, and higher energy density than 300 watts-hour kilogram, carbons and, for example, phosphorus derivatives. Regarding the carbon derivatives, we have a low average potential. We have the hard carbon is the black ball, the CB, the higher capacity, but the main drawback is the poor phase cycle Coulombic efficiency in these materials. But we can see that Professor Komawa 2 years ago prepared one hard carbon for 180 milliampere per gram. Regarding the soft carbons, the green ball is exhibit energy density similar to the graphene derivatives. Phosphorus anodes, it's I'm going to speak about black phosphorus and red phosphorus. In the case of the in both of them, they have high theoretical capacity, sorry, low voltage, but the main drawbacks here is the large volume expansion and the instability of CI. There are some recent interesting results in composites. In the case with carbon nanotubes, we have approximately 2,000 milliampere per gram with a capacity retention of 75%. And also in the red phosphorus, there are two important publications. One of them, Professor Khalil Amin, with antimony and carbon nanotube with excellent capacity, also a low and high C rate. And there is another publication with Professor same groups with a capacity of about 2,000 milliampere per gram up to 2,000 cycles. If we compare if we compare the hard carbon with the phosphorus anodes, we can see in the hard carbons we have low operative voltages, good experimental specific capacity, and easy synthetic rules and good cost performance balance, easy to process. In the case of phosphorus, they have very low operating voltage, excellent experimental specific capacity, but they have complex synthetic rules and cycle life must be enhanced, and also unstable SCI electrolyte degradation. It means that further study should be performed in the case of phosphorus based on us in order to facilitate reaching the market. Regarding the cathodes, the three most important families are layer oxides, polyanionic compounds, and Prussian blue. If we compare all of them, there are some advantages and disadvantages. Sorry. In the case of sodium layer oxides and Prussian blue, they have high reversible capacity, high specific capacity, but the drawback in the case of sodium layer oxides, they are highly hygroscopic and relatively low potential. In the case of the Prussian blue, low Coulombic efficiency. In the case of polyanionic material, they have good thermal stability, not hygroscopic, but they have relatively low reversible capacities and low specific energies. I'm going to discuss briefly all of them. In the case of sodium layer oxide, there are different structural classification, O3, P3, P2, or P2 types. The most important on the O3, they are fully oxidative phase, sodium 1 content, and the transition metal, the oxidation state for transition metal is 3, with a multiple step cycling performance. And in the case of the P2, the transition metal, the oxidation state for transition metal is 3 and 4. It means, depending on the transition metal, if we have manganese 3, for example, we have a Janteler effect. If we have manganese 4, no Janteler effect. On the contrary, we have iron 3, no Janteler effect. If we have iron 4 is a Janteler effect. So there are some limitations, major limitations that I am going to discuss only 3. There are more, but I am focused my presentation today in 3 of them. Basically, stability of the host structure, the deficiency in sodium capacity in P2 phases, and the hysteretic oxygen capacity and the relationship between oxygen redox and voltage. There are different approaches. In the case of stability of host structure, we can use some dopants, electrochemically active like iron, or electrochemically inactive like titanium, lithium, and magnesium. We have prepared some doping effects in the manganese iron phase. We have made a substitution of 10% of titanium but iron, and we can observe that in the case of the manganese iron, 80% and 20%, there are a moderate capacity fade and there are different plateaus. On the contrary, with a 10% of substitution, there are more stable electrochemistry behavior and also very good capacity retention. Also, not only a low C rate, but also a high C rate, and excellent electrochemical answer can see here at up to 300 cycles. If we increase, for example, the amount of doping, if we go to 20%, we can see that in the case of the unsubstituted phase, manganese and iron, there are very good capacity, but moderate stability. With 10% of substitution, titanium substitution, they have good capacity, but also good capacity retention. But 20%, this is excellent capacity retention, but very low capacity. So this is the best amount of doping in these cases in order to improve the electrochemistry behavior is approximately 10%. Regarding the second limitation, if we have sodium deficiency, like in the case of the P2 phases, we can use sacrificial salts. There are some sacrificial salts used previously published in the literature, like sodium azide, sodium phosphide, and some organic salt. But there are in the case of sodium azide and sodium phosphide, there are explosive, and some cost, expensive, and so on. We are going to use this sacrificial salt. It's a sodium mesosalate. It's a sacrificial salt, safer and cheaper than those previously reported. The important in this case is to use this sacrificial salt decomposed electrochemically at approximately 3.9 volts. That's in the working voltage limit of active materials. So using this sacrificial salt, we can overcome the problem of deficiency in our P2 phases. The electrochemical study in the manganese iron titanium phase, we have analyzed the electrochemical behavior in both in half and full cells. In half cells, we have with the pristine and sacrificial salt in the green color, we have higher capacity, but in the case of the pristine, at about 25% higher capacity by using sacrificial salt. We have analyzed also in the full cells using the P2 phase, the manganese iron titanium, and the sacrificial salt and without sacrificial salt, and using hard carbon as anode. We can see that the capacity in the case of the sacrificial salt is approximately 4 times higher than that corresponding to the pristine without sacrificial salt. Another important topic here in the layer of side is the hysteretic oxygen capacity and the relationship between the oxygen redox and voltage hysteresis. It's important to determine the factor causing this effect, is the anionic redox process. There are some alkali-rich transition metal oxide that exhibit anomalous capacity, like in the case of this phase, manganese magnesium P2 phase, with a capacity of 220 milliampere per gram that can't be explained by the redox reaction manganese 3 manganese 4. This phase was prepared by Professor Kumaba's group. 4 years later, Professor Bruce explained this behavior, saying that the existence of a reversible oxygen redox process. This group, Professor Bruce group, published recently the study of 2 phases in sodium lithium manganese oxide. One of them with a ratio manganese lithium of 3, and the other one with manganese lithium of 4. In both cases, manganese 4 without Janteleret. In the case of manganese lithium 3 ratio, they found a honeycomb superstructure with a formation of molecular oxygen with migration, the transition metal layers on the cations. On the contrary, with a manganese lithium ratio 4, this is a ribbon superstructure without oxygen formation on manganese migration. This Professor Ron published recently another paper with lithium manganese, with a manganese lithium 3.2 ratio, also with manganese 4, and they found a decrease of the capacity of about 200 milliamperes per gram by reducing the voltage window. They explained this. The first charge attributed only to an anionic redox reaction, and this charge both anionic redox reaction and manganese 3 manganese 4 redox reaction. However, there is some significant controversy regarding this interpretation because it's a radical departure from a materials chemistry point of view. This way, Professor Van der Velde recently published an interesting article of lithium-rich manganese positive materials, in which they found a process, manganese oxidation process from manganese 4 to manganese 7, also with migration of these cations from octahedral to tetrahedral sites. The formation of manganese 7 was followed by a spontaneous but dimerization of oxygen, but they found also the composition of the cathode material. So it's important to analyze in detail experimental data in order to understand the process of this hot topic. The following systems is polyanionic compounds. This is a great range of choices due to the inductive effect. They are sulfate, borate, phosphate, pyrophosphate, silicate, and so on. These exhibit higher redox potential than sulfides, and they have high thermal stability and safety. There are some limitations. For example, in the case of the pyrophosphate, because they have low operating voltage. In the case of sodium sulfate with iron 2, they have a strongly hygroscopic. But the most important families in this polyanionic system for sodium-ion battery are the fluorophosphate and the phosphate. Briefly, the pyrophosphates, they have a high specific capacity. It's important to have two plateaus, 2 voltage plateaus at 3.6 and 4.1 with high energy density. They have excellent cyclability and good Coulomb efficiency. Without modification, for example, of the thermal preparation or sorbothermal preparation, they can have also excellent capacity at high C rates and with a capacity retention of 1 to 1,200 with a cycle with an excellent Coulombic efficiency. If we move to the NASICOM, for example, in the NASICOM, we find two plateaus, two voltage plateaus, one of them in a 3.4, 1.4, another one at 1.5, indicated that these materials can act as anode and cathode in asymmetrical phase. The specific capacity, experimental capacity, is practically similar to the theoretical capacity, and is worth noting in this case the extraordinary cycle life up to 2,000 cycles at 100 C. It's excellent from the power point of view. The Prussian blue analogous, they have a cyanoferrate with transition metal oxidation stage 2. There are high reversible capacity, high energy density. It's important in the case to get a range of operation voltage, high range of operation voltage. If we analyze the results of the electrochemistry behavior of some of them, the metal, nickel 2, iron 2, cobalt, and manganese, we can see that the nickel and cobalt, they have moderate electrochemistry behavior. On the contrary, in the case of the iron, they have good reversible capacity and excellent cyclability. And the manganese, they have excellent reversible capacity and good cyclability. So the two best materials, two best transition elements, are in this case the manganese and iron, that are not expensive and environmentally friendly, at the different in the case of the cobalt and nickel that are very toxic and expensive. So the preparation of solid solution on manganese and iron is a good, can be very good candidate for cathodes in sodium-ion batteries. In overview about the cathode, we can see that the layer of sites in green color has high specific capacity. The polyanions, we analyze both of them, considering the filled symbols is theoretical capacity and the empty symbols are experimental capacity. We can see here that the polyanionic materials exhibit practically similar experimental specific capacities than theoretical values. And the Prussian blue in the blue color, they exhibit greater variability depending on the transition metals involved in this process. Another topic to analyze is the electrode-electrolyte interfaces. I am going to speak only with electrodes in general, but this is important for the electrochemical, to get good electrochemical results, to analyze the electrode-electrolyte interfaces. In the case of the sodium-ion material, we can have some non-aqueous liquid electrolytes, carbonate, they have created a protective SCI with the addition of a small amount of fluoroethylene carbonate, for example, FeC. We improve the electrochemical behavior in this case. In the sodium-ion batteries, unlike the lithium-ion batteries, we can use ether-based electrolytes that allow the sodium solvent co-intercalation in graphite electrolytes. And the SCI of this electrolyte are, we can see here, more compact, highly stable, thinner, and conductive organic layer at the exterior, prevent the extra decomposition of this electrolyte. It's important to also analyze the electrolyte stability windows. The electrolyte stability windows can be defined like the electrolyte potential reduction at negative potential and the electrolyte oxidation potential at high potential, a positive potential. If we analyze the evolution on the conventional electrolytes with advanced electrolyte, we can see that the use of advanced electrolyte with a larger potential window can prevent the degradation of the electrolyte, improving performance of these systems. We have analyzed briefly the solid electrolyte interface, the effect of the electrolyte effect in a solid electrolyte interface for the bio-waste hard carbon using the conventional electrolytes and ionic liquid electrolytes. In the case of the conventional electrolytes, in the blue color, we have an homogeneous rough surface and inorganic rich ACI. In the case of the ionic liquid, basically we have uniform and thin ACI, basically with insoluble organic rich. In the case of red phosphorus, with a conventional electrolyte, we have rough and porous surface, soluble in an organic rich outermost. And the case of the ionic liquid, we have also, that in the previous case, uniform and thin ACI with insoluble organic rich compounds. If we analyze the cathode electrolyte interface, we studied this behavior in the manganese iron titanium phase with this conventional electrolyte, and we can find thicker and rough Ca inorganic. This is a layer from inorganic rich fluorinated species, this one close to the electrolyte, and carbonaceous species close to the electrolyte. On the contrary, with ionic liquid, we have a smooth and homogeneous Ca with insoluble organic rich species. In the case of the family of phosphates, we published a work recently with phosphate pyrophosphate in conventional electrolyte, and also we can see here a layer of soluble outermost layer and two main layers here with organic rich and semi-organic rich. We have not studied ionic liquid for comparison, but we can analyze, for example, another polyanionic material like vanadium phosphate, with Nasse-Coulomb structure, and we see also homogeneous stable CI in inorganic rich layer. So we can say that the carbonate-based electrolytes, they don't give rise to a homogeneous and uniform interface. The chemical composition is rich in inorganic compounds, but soluble in the electrolyte. In the case of ionic liquid, they form a fine but uniform interface with rich composition, with chemical composition rich in inorganic, but not soluble in the electrolyte, giving rise to excellent stability during cycle. If we try to compare the knowledge from lithium-ion battery related to electrolyte interfaces, we can be of help, but the direct and full transfer of knowledge is not granted. Considering the ionic liquid, they are very expensive at the moment, but with an adequate scaling plan can become electrolyte to choice for future need, sodium-ion batteries. Regarding the industrial developments, we have at the moment with using the first generation of materials of commercial available non-aqueous electrolytes. They have different materials, different systems with hard carbon, all of them as anode, but they are layer oxides, polyanionic materials, and Prussian blue analogous. In the case layer oxide, vanadium have an energy density of 160 Wh/kg is higher than the lithium iron phosphate graphite cells. And also with aqueous electrolyte, neutron energy using Prussian blue as both cathode and anode, they have excellent values for power and also with excellent cyclability at high C rate. This is briefly the sodium-ion batteries with the vanadium working with layer oxides and hard carbon. In the second generation, they have 160 Wh/kg. The French network, they are working in vanadium fluorophosphate and Tiamat, 150 Wh/kg in the second generation. And also the Hina Chinese company, they have recently, this year, they got a battery with a megawatt-hour. 2 years ago, they had one battery for stationary application, 100 kWh, and this year 1 megawatt-hour. And I would like also to comment the last information of the Chinese company CAT. that successfully integrate a sodium-ion battery, sodium-ion cell with lithium-ion cells in one pack, using Prussian white as cathode and hard carbon as anode. They have high energy density, 160 watts-hour kilogram, and they try to get 200 watts-hour kilogram in second generation, with fast charging capability, excellent thermal stability, and in parallel, they say that they are going to develop an industrial company for sodium-ion batteries and plans to form basic industrial chain by 2023. So, summary and conclusions: anode, hard carbon derivative materials, still leading technology. Cathode, layer oxides and polyanions offer very good performance. The electrode-electrolyte interface is important to analyze in order to improve the electrochemical behavior of these materials. Ionic liquid can be very good candidates in the future as advanced electrolytes. In the market, we have at the moment prototypes for 0.1 kilowatts hour to 1 megawatts hour. So sodium-ion technology is well positioned as a future energy storage technology. It's important tailoring the first generation materials to move to second generation materials. And I would like to thank the Ministry of Economy and Competitiveness and the Basque government, Spanish government and the Basque government for funding. And thank you very much for your attention.
Yeah, thank you very much, Theo, for this real nice overview of the sodium-ion technology, which is obviously very attractive because of the sustainability issue that we have with the lithium, especially cobalt and nickel. So this could be an interesting technology if we can increase the energy density to the same level like lithium-ion. That could be an immediate replacement. Obviously, it's a long shot at the moment. So we want to entertain a few questions on the sodium-ion for these topics for Theo to answer before we move into the last talk, keynote talk. So let me see. There are quite a bit of questions. Yeah, so there is one question about there are many type of phosphorus, as you indicated in your talk, Theo. There is the red, there is the black. The white obviously is dangerous because it's explosive and inflammable, so it's out of the question. So the question is, which one really provide the highest energy density? Is it the black or the red?
The red phosphorus, yeah. The red,
yeah. The only problem with the red is the conductivity is very low comparing to the black. So but the cost obviously way much cheaper. There is another question. Is it possible to extract 1.2 to 2 sodium ion and having just one plateau in the case of sodium-ion battery? That would be the dream, actually, if we can do that.
For what family? With
it doesn't mention which family, but from your extensive experience in the cathode, is there any cathode where we can extract up to 2 sodium with a single plateau, high voltage preferably? Does it exist?
No, but in the case when you have 3 sodiums, you can start, for example, 1 sodium, 1 sodium point half. Not all of them, not the 3, but not, for example, in the case of the layer of sites. It's a sodium. In all 3 phase, you have sodium. It's full sodiated. It's only 1 sodium there.
Okay, so I actually have my own question that I would like to get your insight. The CATL is planning to produce 200 watt-hour per kg sodium ion, which is very impressive, using very likely one of these cathode with the hard carbon. So imagine if we are able to enable, let's see, phosphorus, red phosphorus, either in a dopant form to get us, let's say, 2000 milliampere per gram, and combine it one of the highest energy, high voltage sodium cathode. Do you think that we can equal some of the energy density of lithium ion in this case, assuming we resolve all the problems?
Yes, yeah. I think it's important to work to make research in this material, in red phosphorus. I believe in these materials. I think it's a very, very competitive material to improve the energy density. But the problem, you know very well, because you are working on this system, that is very difficult to have composite. It's very difficult to prepare good materials. But obviously, it's you know, lithium-ion batteries, they are working for 30 years and it's not finished. It's not finished at the moment, the research. But if people start working, more people obviously, in red phosphorus, I think it's a very, very good candidate. It's the excellent candidate, I think.
Yeah. So the other question is about the density comparing to the homolog lithium-ion, the density of sodium. I'm talking about the pellet density because it's very important when it comes to you know, loading active material in the electrode. How is it? Is it comparable, or I never heard about people talking about that? That's very important parameter.
I don't know. Perhaps it's difficult to arrive to get the same energy density of the lithium in the future. But you know, it's if you are thinking in the application, I think this is sodium-ion battery is not competitive with lithium-ion batteries. I think it's complementary. You are thinking, for example, in energy storage, in stationary energy storage. It's a very competitive technology, I think.
Okay, so there is one question about the cost. You know, the price of 1 megawatt-hour sodium-ion battery comparing to lithium-ion battery.
Yes, I haven't studied about that. I didn't have time to present here, but I think sodium is very, very competitive in cost with lithium. But also, you know, in this case we have excellent cathode material with high energy density, cobalt and nickel free. That is really very important. I don't know if using hard carbon, we can increase, people say that we can have working in hard carbon to get 1000 milliamperes per gram. I don't know. But if we are working, for example, in the best candidate for red phosphorus, for example, it's important to dedicate time funding, yeah, sure. But the cost could be very, very competitive energy density if we arrive to that. But it's difficult. As you know, if, for example, in silicon for lithium-ion batteries, yeah, it's difficult to get to the market. After 10 years working on silicon, there are not, I don't know, but there is not a way to go to the market at the moment for silicon.
Yes. Yeah, so I would just add that one of the reason why there is tremendous focus on sodium ion because of the secure sustainability. As you mentioned, the cathode of choice that are used now in sodium are basically manganese based or iron based. These are very abundant element. Unlike in lithium ion, nickel and cobalt obviously is a major concern. The industry now is concerned about nickel as well. So with the big demand in electric vehicle, you see the price of cathode will jump to the roof, and that can basically backfire when it comes to the cost. So that's one of the reasons why sodium has that edge or advantage. I will take one more question.
Yeah, you have, sorry, Khalid. If you are thinking, for example, in the results presented by CAT, the Chinese company, they have a hybrid lithium and sodium-ion batteries. They can be complementary in the system. They are speaking about 200 watt-hours per kilogram with the battery, with sodium battery. You can compensate with lithium battery. You can prepare for a hybrid, and you can compensate, for example, energy and power. Because in power, using vanadium fluorophosphate or the Nasicon vanadium phosphate, you know, it's a excellent cyclability. You have 10,000 cycles at 200 C. It's excellent for power.
I see.
You have is complementary. You can have an hybrid of lithium-ion battery in energy and sodium-ion battery. For example, they are working in Prussian blue, the CAT company. They are working in Prussian blue. Prussian blue is also excellent, but also vanadium fluorophosphate or the excellent cyclability. You have a hybrid with both. Is the future.
Excellent. Yeah, so I think we'll stop here. The other question that the audience has asked, my colleague Gao, you will bring him back during the panel discussion after his talk. Okay, let me thank Theo for his excellent work on sodium-ion battery. He's really a pioneer in this area. And I would like to introduce the next speaker, my friend Galio. He's the group leader of the Applied Energy Material at Berkeley National Lab in California. He's very well involved in most of the DOE national program on lithium-ion and polymer batteries. He has published extensively. He has over 100 articles and has 2 R&D 100 awards, which are actually known as the Oscar of the technology and innovation when it comes to the industry, because they are commercialized. Ga will, if you can share your screen. Theo, can you give him the? Yeah.
I just what is I have to remove it one.
Okay, I think
you can do that.
I will do that now, and he will be talking. Yeah, he will be talking about the application of conductive polymers in lithium rechargeable battery. So, Ga, once we finish your talk, you will chair with Moad moderate the panel discussion, because I will leave in 5 minutes to go back to the airport to head back home. I'm actually in DC now. So, thank you so much for accepting to fill in for me, and you can go ahead and start. You can make I think you need to change your screen to one big screen. Yeah, we can see. Yeah, thank you. All right, thank you. You go ahead now.
All right. Thank you, Cal, for the introduction, and also thank you for the organizing committee to inviting me to give this presentation. So we talk about in the section we talk about the applications of lithium-ion batteries. We also talk about the new system, right, sodium-ion. So what I like to talk about is emerging new materials which can be used in a lithium-ion and also maybe sodium-ion batteries. And this is a material called conductive polymers in lithium-ion rechargeable batteries. So in the audience, people ask about silicons, right? So we're going to focus on later on the application of these conductive polymers in silicon applications. So let's go into talk about, let's see, the outline of today. We're going to first give a very short introduction on the polymer binders in composite electrode. So most of us here know lithium-ion batteries, know materials, but if you look into electrode, right, how the electrode form, right, what the polymer binder, the role plays for this application. And also we're going to talk about the critical roles of the binders in the composite electrode. And then we're going to move on to talk about silicons. So why binder is so important for enabling silicon materials for anode applications. And then we're going to move on to talk about using the conductive polymer to enabling silicon chemistries, and then talk about the ways that we can make this polymer binder that very versatile for our applications. So let's move on to the next one. Let's have a complete look of a electrode as a functional composite, because normally in the polymer case and composite, we think about polymer composite as has at least 50% of polymers without the particles in it. And we don't really think electrode as a composite material, but indeed the electrode in lithium-ion battery, the cathode and anode, is a unique kind of polymer composites. The reason is because it has a polymer binder inside to bind all the particles. It has 2 types of particles normally. It has active materials and also conductive additive, which we call them carbon black. So the polymer binder in this case is only 5% to 10%. So that makes it really unique, because in the normal composite, you have at least 50% of polymer in it. So in this case, we only have around 5 to 10%. And in some extreme cases, we only have 1% of binders in order to increase the energy density. And one of the unique features when polymers mix with particles is that polymer differentiate. So the polymers no longer as one physical property when they mix with particles. So they differentiate into three types of polymers within the composite. One is called the bonded polymer, which the polymer are tightly associated with particles. Then there's really no, the physical properties become very rigid. And after that, there's layer of polymer called immobilized polymer, which is still very rigid, but not as rigid as one that next to the particles. And then only after you satisfy both requirements, now you have free polymers all around it, which provide adhesion. So this is very important to understand, because in the composite system, in the regular polymer composite, most of the polymers are actually in the free polymer form. But in the electrode system, most of the polymer is in the either bonded or in the immobilized form. So the way of adhesion is actually provided by the polymers that have very rigid property than its original polymers. So why this is important? Look into the ways that we make electrode. For example, if we normally talk about if we want to have electrode with very high electrical conductivity, which we do want that, right? Because that's the electrode, we want high power. So we have a lot of carbon blacks, right? We have PVDF, which is a binder in this case, as just an example. So we almost want to have one-to-one ratio of AB and PVDF, and then we put in active materials. In this case, is black, is the orange colored bigger particles. Alternatively, what we can do is we can also put in a lot of binders, which in this case is acetate black is in the minority and the binder is in the majority, and then we put in particles. Let's look into these two scenarios. In this case, the conductivity is low, electric conductivity. In this case, electric conductivity is high. But then when you mix the same amount of active material, for example, if you have a lot of active material, which that's the composition you want, the problem is now in this composition, you have a lot of, conduct additives versus the carbon black. All the carbon blacks are aggregated. That's because the polymers are immobilized by the particle surface. So you don't have a polymer to distribute this conductive additive. So they're really aggregated. And in this case, you actually create a electrode with very high resistivity. So the only way you can increase conductivity is actually putting a lot of this acetate black PVDF composites and with less amount of active material. In this case, you have high power electrode, but you have less adhesion and you have less energy density. Alternatively, if you have more binders, less conductive additive, you end up with a well-distributed conductive additives. In this case, you can see the well-distributed under the ACM. So now you have a thin and complete coating. In fact, you have a higher conductivity compared to the one you have here. But then if you have more of AB PVDF composites, what happens is now you have a lot of free polymers. You have a very robust electrode mechanically, but you lose the mobility of iron, so you have a highly resistive electrode. So that shows you how the composites form. When you form the composite, how they actually impact the electrode performance. So these set the stage. We talk about silicon and also talk about the conductive polymer applications. So let's look into the case for silicon electrode, where it's a really hot topic now, how we can enable silicon materials in lithium-ion batteries. There's a lot of talks. There are certain amount of type of silicon actually go into the lithium-ion battery now, but it's in a small amount, it's 5%, right, in that range. So how can we enable high silicon content with composite electrode is still an unanswered question. So you can think about silicon active materials in the traditional electrode where you have carbon black provide electrical conductivities and you have binder provide adhesion. And once you expand contract, one sure thing is going to happen is the electrode the mechanical property going to fall apart, and then you're going to have the silicon particles essentially walk out of the conducting network because the carbon black is not conductive, and you really rely on the carbon black to provide these connections for electron pass. But in this case, you actually don't have that here. So the other problem is actually the surface failure of silicon materials. The silicas expand, contract, at the same time they form ACIs. So the ACIs are inorganic or organic metallic materials, so they tend to fall off. So they don't have elasticity, they don't have adhesion property. So they fall off every cycle, every cycle they regrow. There's also another issue is this type of ACI in here is now stable. So it's not unlike on graphite, which the actually stable ACI, the ACI on silicon is not stable. So there's no way the electrolyte with regular additives can actually passivate silicon surface because of both the chemistry reason and the mechanical reason we show here. So that's the main challenge we have for the silicon materials. And let's see how the conductive polymers can actually make a huge difference to enable silicon materials. The reason that these conductive polymers can be a really good, unique alternative is because of the four reasons here. One is by having a conductive polymer, which the polymer itself conducts electricity, you can actually form a very molecular level electrical conductivity to say, unlike you rely on carbon black to provide conductivity, which is a nanometer scale connection. So this is a molecular level electrical connection. The second one is you can engineer the conductive polymer in a way that they form strong covalent bondings with silicon material. So we'll talk about that later. And also the lithium ion transport, we can manage lithium ion transport so they can either get onto the silicon surface. And also we can use these polymers to actually protect the surface. Remember the surface, the ACI, they fall off, they reform, they fall off, they reform because of no binding. If you have good binding, you can protect the surface. So in 2011, we actually championed this idea of using conductive polymer for silicon materials, and we have developed generation of approaches to actually solving this problem. And the other unique advantage when we talk about manufacturing is we can use silicon-based particles by anyway, right? We can use all kinds like silicon oxide and pure silicon and also carbon-coated silicons, and it's also fully compatible with conventional lithium-ion manufacture process. For example, the laminated electrode, we can take advantage of the existing process to make these materials. So let's see if we want to have a conductive polymer for this application, we can buy them on the market. There's a lot of conductive polymers on the market because people use it for different optoelectronic applications in the past. But what would be the requirement if you want to use it for lithium-ion battery applications, right? So that's a very different system because when you look into how tricky it is to develop a system for lithium-ion rechargeable batteries, so you know each of the material designs has to fit specifically for the applications. So the first we want to do is, since we use this for binders and also as a conductive network, do we have the conductivity? So if we look at here, the requirement of conductivity, the electron conductivity is about a Siemens per centimeter in conductivity. Conductive polymer has a wide range of conductivity, all the way from 10 to the minus 4 to 10 to the 4th power or 8th power. So it could be extremely conductive depending on how we design polymer, conductive polymer. So this gives us a comfort level, we can do it. The other way we look at this is to see where is actually the polymer going to operate at, right? So because for conductive polymer is redox active, unlike a neutral polymer, it's not like this is redox active. So that means it's getting reduced, getting oxidized. But for lithium-ion batteries, if you look at this graph we show here, if you design a binder for cathode, so it has to operate between 3 to 4 to 5 volt versus lithium metal. But for anode, it's work around about 0 to 1 volt versus lithium. So that tells you that you need to have a polymer which can be reduced at that potential and actually can be electric conductive at that potential and also has to be very, very stable. So how can we design, what kind of polymer are those polymers? How can we design that? So remember the the earlier talk, we use HOMO and LUMO level to understand, right, the stability of electrolyte. We can use the same principle to actually design the binders for the silicon materials. The only difference is the LUMOs are the extremely important part of that we need to design, because if you look at the potential of the lithium-80 silicon, is around -2 electron volt, and versus the cobalt oxide, which is here. So when this is a DFT calculated stability of conductive polymer. In this case, we choose the polymer that we want to use, and it shows that the different level of the molecular orbitals, and it shows that at which potential, in case it's here, is actually getting reduced, which is start conductive, and also shows at what potential you start to see lithium deposition. So you want to design a polymer which you can actually reduce at the potential where before the lithium ion can deposit, which in this case, the polyfluorine polymer can do that. So that's the DFT calculation. And once we come to the choice of that, so we can see a polymer that can be stable and can be reduced is the polymer such as polyacetylene, polyphenylene, which is all these, it's called electron deficiency polymers, and polyfluorine. And those are the polymers, and we show the calculation is the polyfluorine here. And the reason we like polyfluorine is because for those polymers, it's very hard to chemically modify it. But for polyfluorine, there's a 9 position which you can do a lot of chemistry here. And we can start from here, we can make LQ chains. Now this is soluble. If we use as a binder, we want it to be soluble, so we can use them to glue all the particles together. And we can also do chemistry on this 9 position to actually create a carbonyl bonding, which we can further adjust the voltage that we can reduce them properly. So if you look at all these designs, we know that we can really synthesize this polyfluorine and polyfluorinol. We call this a copolymer, right? So that's easily done by one step. And now what I like to show is if we make this called PF polymer, and we show the performances here, and the polymer can be made, and then the conductivity is actually the cycling performance is actually good for the 2 cycles, but then they decay really, really quickly after 2 cycles. So that shows the actual application is actually can be used as both a conductive additive and also as a binder, but the problem, they decay really fast. So when we try to understand the adhesion properties, we know the PF doesn't really glue the particles in a very, very forceful way, very strong way. The reason is because we need a better adhesion functionalities to increase the binding force. So that's where we come to this part, where when we look at we can add another functionality to the PF we designed. That's our 1st generation PF. And these, we call this PFM, where we have both the conductivity region and also the adhesion unit. The reason these ester group can provide adhesion is because when we have these polymers in contact with silicon particles, when we increase temperature, where that's the process we make electrode, we can have a transesterification reaction where the methanol group disappears, and then we can form this bonding. And this is confirmed by which is confirmed by the top C measurement. We can see these molecular unit in a fairly large amount. So, and also when we make this called PFA material, we mix with silicon, and you can see the performance coming up significantly. This shows a 15 cycle performance compared to the PF. So these are the regular satin black composite electrode that goes down, and that's where the graphite at. And if you look at both the PFA and also the PF electrode, what this tells us what this shows is the electrode with only silicon and conductive the polymer. There's no conductive additive in it. So in that case, we still hold a record of that. Although this publication is fairly old, we all still hold a record of using silicon and PF conductive polymer without any carbon black to actually increase conductivity. So this shows that the conductive polymer can really be used as both bifunction binders and also adhesion unit for the electrode. And that's how the electrode looks like. It's very uniform. And if you look at the ways that how the adhesion increases once you put the adhesion unit, it goes from almost 0 here without the adhesion unit to 2.5, which this unit, this is only the lows, but these two automatically increase actually put you into the adhesion as good as any adhesion tapes. You can actually pull the electrode apart. So let's see, we were able to design these conductive polymers by putting another function unit in here. We're able to not only have a good conductivity, but we're also able to have a very strong adhesion. So these can really use both as a binder conductive additive for silicon materials to enable silicon. And if you look at the performance, and for this kind of pure PFM and silicon electrode, so we can run 600, we can even run 1,000 cycles. The fading is most common from lithium side, actually. So that's half cell. If you take away the lithium, and you can run these things forever. And a lot of the silicon electrode, when you put them apart, the electrode start to fall apart. But in our case, the silicon stick really well to each other out of the current collector. But then the question we ask ourselves is, the silicon supposed to have a capacity or close to 4,000, right? For nanoparticle, we say it's 3,800, but why we only get 2,500, right? What's the reason we don't get another 1,000 milliampere per gram capacity? So when we look carefully into the binders, what we understand is this binder is highly nonpolar. If you have a nonpolar binders, it's very hard to bring electrolyte to the particles. So the particles that are hiding deeply into the binders will not have access to the electrolyte. So what we did is in designing the second generation binder is if we can bring in a electrolyte intake group, which in this case is polyethylene oxide, what we can do is we can really enhance the electrolyte intake capability of the electrolyte. So we can actually make all the particles available for ion transport in the electrode, which is a key part of the porous electrode capabilities. So when we look at, so that's how we design our second generation of PEFM, where there's ethylene oxide on the side chains. And what we can see is for the PFM, which doesn't have the electron intake group, the swelling is fairly minimum. It's less than 10%. But once we have the EO unit here, the conductivity, the electrolyte intake goes to 30%. That's come to the equivalent of PVDF binders in terms of the electrolyte intake capability. And if you look at the polarity, we know the PFM is more polar compared to PFM, which they all fall into the same picture. So now if we take PFM and take silicon, again, we don't have any conductive additive in these systems, we can actually enhance the capacity to the theoretical level now. So as you can see, our generation from PF, where there's no adhesion, higher capacity, fast fading, to PFM, where we have better adhesion now, good capacity, stable cycling, with PEFM, high capacity, stable cycling. So for conductive polymers, if you design the conductive polymer right, you can actually achieve the functionality you want. If you really miss some functionality, you can always redesign this conductive polymer to have more functionalities. So this is actually really the unique part of conductive polymers is you can design them in a way that you want. So we can design them in a way that the system requires to achieve the functions we need to do. So with that, I'd like to show you some example of the real life application. So some of the audience ask, what kind of silicon we use for silicon material? What are the best silicon materials these days? So one of the materials is called silicon oxide, where Matthias also mentioned that, is a material that first produced by a Japanese supplier called Shin-Ishu, and now is, the small amount is used in a lot of these power batteries, such as Tesla power batteries, for their electric vehicles. And so we take this SiOx material, we have capacity around 1,500 or 1,100 milliamp per gram capacity, compared to graphite, which is already 3 times higher than that. And we combine our binders. In this case, PFM we used, and we use 3 different kind of compositions. We use 10% of PFM, 5% of PFM, 2% of PFM. So remember, this material, SiOx, has over 100% volume expansion when they take in 1,000 milliamp per grams. So, and we show here that the 3 of them all give you a very stable capacity, but this one with 2% of PFM, they perform as well as the one with 10% and 5%. And that's 2% of PFM with 98% of SiOx. And this till now still hold a record how less of binder you can use for silicon materials. So you actually can produce an electrode with very, very, very stable capacity for many, many cycles. And here we show another example is, in the current system, we like to put some graphite into the system. So if we have 60% of PFM and 20% of graphite, and with binders and some conductive additive, we can build the electrode like this, and that's after cycling. And most of the result you see is silicon after cycling, they form a lot of debris. But in our case, before and after cycling, it doesn't really change a lot, right? And also when we build full cells, so this is the half cell, and this shows you the capacity we get in the half cell, and this shows you the full cells, how stable the capacity is if we use SiOx with lithium iron phosphate electrode. Again, I want to remind you, these are, we don't have proliferation. That's why you can see there's a lot of capacity drop in the first cycle, because SiOx taking a lot of is lithium material in the first place. But then what we want to show here is the stability of this SiOx after the first cycle loss. And you can see in our case is extremely stable. And also the impedance is very, very stable. And you can see all these the efficiencies. And what I like to point out here is this system is very close to a commercial system now. So we use regular electrolyte, we use the regular cathode coupled with our system. So that shows these binders, this conductive polymer binder, is not only good for the lab, but also it really, we're making huge progress towards making them into a commercial system now. And I like to show you that the polymers you see, right, the PFM or PFM, when you look at the polymers, and for organic chemists, polymer chemists, we know this kind of polymer, when you synthesize these polymers, right, it's a bit difficult because you have to form carbon-carbon bond in a conjugated method, right? So we think about the ways of, can we make this more versatile in terms of chemistry, right? So that's come for, although it's a scale-up thinking, but it's really a thinking we have to think about, how the electrons are holes, which in the term of the semiconductor business, actually transport within these conductive polymers. And most of times, right, people think about conductive polymer, they think about like a wire, so the electrons go through the wires. But in fact, that's not the case. If you look at the condensed physics of these conductive polymers, they call this polarized. It's actually not only a hole, or actually is dislocated to these pi systems. They can transport along the chains, or actually can transport it between chains. And in fact, if they align right, these between chain hopping is actually a much faster transport mechanism for polarized. So by understanding that, what we can do, you can think about cutting these variable into pieces and really connect the pieces in a way that we can really run a radical polymerization. So we use this pyrene as an example. We can tether them onto a polyacrylic type of monomer, and then we can polymerize them. The good thing for that is now this one is in a much smaller size, and we can have a copolymer which can have all kind of functional group we want, because we want either adhesion or we want a swelling or we want all other things we can put on there. And then once we run the polymerization, it can be run in many different kind of chemical medium to do this reaction. This is such a versatile chemistry, what we can do with this radical polymerization. And in fact, we take one of our binders, we combine with two types of commercial available material. One is the silicon T material from 3M. That's our work with 3M to use their material combined with our silicon our binders. And the other one is the using our binder with a really high type density pure silicon particles. So in both cases, we can achieve very high energy, there's a very high capacity and very stable cycling performance. So what I like to conclude that, I know my time is up. So I will say that, I hope I show you that, the multifunctional conductive polymer binder is really a promising and enable material for silicon. And we didn't talk about alloys, but we have publication on pins and different things. And also we have a collaborative work with Carl Min and working on his alloy system, and also show really remarkable results. And also, if you think about these conductive polymers, so they really solve the four critical issues for the electro. They provide molecular level electrical conductivities, strong adhesion to covalent bondings, and also ion transfer, and also they can protect surfaces. So the other thing we want to say is really you have versatile chemistry you can enable these both the scale up and also the application down the road. So again, this work was done by by generation of my postdocs, through the years, and really for all my collaborators here, and also funding from a variety of funding agencies. And I want to thank you for your attention, and thanks for the organizers. And if you're in the United States, I say happy Thanksgiving. Today is the holiday, so really, enjoy to spend some time, in this holiday season. Thank you. And I actually want to, if you have a question, you can put in chat. And I think Cal is he's off today because he has to run to the airport. And we if you have questions, please submit to the chat, and we're going to administer that and answer some of your questions. So.
Thank you, Gal, for the nice and clear presentation. May I start the first question before the audience can post it in the chat? The question. So my question about the loading weight of your silicon oxide with LFP, the full cell. The loading weight, yes. So it can be reached like the practically when we compare to graphite and NMC in the real full cell.
So Mount, I think that's a fantastic question, because most of the silicon materials, and although we say it's really high capacity, but then the loading is fairly low, right? Is some of them are 0.1 millimole per square centimeter, which is so, and if you get to 1 to 2, that's become reasonable, but still actually, if you compare to graphite, it's still low, right? So what we show here is we have a publication, is in one of our talks, we can get up to 4.5 now with stable capacity for over 100 of cycles. So, and we have the density is also very reasonable, right? So if you have a less dense electrode, it also doesn't really count. So the density is around 30% to 40% porosity. At that region, the capacity of 4.5, so the thickness of the laminate is only 45 micron. So it really shows that with this bind, and what also amazing is we can cycle this, and we take the electrode out, the electrode is still intact. So it's really a strong binding and really good conductivity for that.
Yeah, thank you. And please, for the panelists, just raise your hand if any questions. So Professor Rojo or Dr. Mohammed Shakir, if you have any questions, please go ahead. Yes, Mohammed Shakir, please go ahead.
No. Sorry?
Yes,
no,
yes, Professor Rojo, yes, please go ahead, yes.
Okay. I have no question, eh?
Okay, so please, your mic, turn on your mic, Mohammed Shakir, please.
Yeah, I'm sorry.
Yes.
Yeah, sorry, thank you. Yeah, in the same context as Muad's question, what about the swelling, especially when your electrode is, when you use high loading? For example, you talk about 4 to 5 milliamps per square centimeter. And you know that the swelling is very, very big issue for application of this kind of technology.
Yeah, that's a really excellent question. Again, I mean, I would say that swelling comes from two things, right? One is from your material swelling, right? Because the silicon inherently they expand, and not only silicon, actually we have already publication to show that graphite, after 400 cycles they swell by 30% by volume. So it's actually they never come back. They just either they go up and down, but after 400 cycles you get 300%. No, you get 30% swelling for the graphite. So for silicon is the same case, right? They swell much bigger. So they swell, in case of SiOx, they swell by 100% in terms of its own volume, and then they come back, and in the end, if you run for 500 cycles, the swelling is there, right? There is a permanent swelling. There's also swelling depending on your charge and discharge. So in our case, what we measure the swelling is we measure the swelling, and then we look into, after many cycles, how much electrode goes up, right, after each cycle. So the swelling is roughly in line with the swelling of the materials, and you have to, of course, considering the porosity inside, because you really need the porosity to be able to have the electrolyte come in and to give you the performance. But in a sense, I mean, the material, the good thing for conductive polymer is such a rigid polymer, right? It doesn't really swell that much, and it's actually hold on to the structure. So we measure the electrode, the 45 ones, after we cycle for 100 or 20 cycles, the swelling is about, if I remember correctly, it goes to about 60 something, 60, 65. So it is substantial. It's substantial, I would say, but then it's really in line with what the materials swelling. So.
Yeah. Okay. Thank you. Yeah, this is issue because I'm working from Rono, a car maker. That's why I'm asking this kind of question.
Sure.
And when we design the pack or the cell, we cannot, for example, expand or put a lot of volume in the beginning. That's why swelling is more important. And the next question in the same way is. As you know, a lot of people are using N2P, a higher N2P, negative to positive ratio, to reduce this swelling. And in your side, did you check, for example, this parameter, and what is the effect of your design on this point?
Yeah, so that's a very, very, very good question. The way that people normally play N2P ratio is, in research, you pretty much can do any ratio you want, right? To get to a good cycling result, right? But in you actually making batteries, your N2P ratio really, screw up the energy density, right? So you want to design the N2P ratio, which is just about right? So that's why, if you have, for example, SIO, right? If you don't do prioritization, you pretty much limited by N2P ratio. So you can only use 5 to 10% of the SIOX along with graphite. If you use too much, then you have too much cathode to compensate for that. But if you want to use a high amount of silicon, which that's people's goal now, right? We like to use high silicon electrode, 60%, at least 50%, 60%, 80%, right? Now we're actually testing something in the 80% range, right? So if you go to that region, clear N2P ratio is not enough. You really need to do prioritization, right? So what we're doing now is we work with some of the leading industry partners to do prioritization. So if we do prioritization, then the N2P ratio would be reasonable coming back to what you do with graphite, right? So you have a lot more freedom to do. You actually get a real capacity gain. Otherwise, you won't, right?
Right.
We have a question for the audience. We have one question here is about redox polymers. So recently, redox polymers are used as active binder in cathode side with LFP and NMC. So could you comment on the challenges on this hybrid system?
So again, these I would say that the redox polymer, or I call them conductive polymer, is an emerging material. So I would say that using this kind of material as a binder provides a lot of advantages. We talk about this, right? You can engineer adhesion into it. You can engineer swell into it. You can engineer all kinds of properties because organic chemistry gives you infinite amount of possibility to actually make this. And additionally, a lot of these polymers are backbone rigid, so it's mechanically extremely stable, right? Extremely stable. So for anode, we say the anode, they work about 0 volt against lithium metal. So it's in an extremely reduced environment. Most of these polymers, when you go to that reduced environment, they break down, right? So so the stability at range with the redox active is very, very important. So do cathode. If you work on a cathode with low voltage, for example, in the early days, the Good Enough has worked on polyaniline for the lithium iron phosphate, because at the time, people have very electrical resistive, so using conductive polymer make a lot more sense there. So that's actually okay, because iron phosphate is the 3 volt versus 3.5 volt versus lithium, but versus hydrogen electrode. It's really in the range that the polymer is very stable, right? The oxide is very stable. But then if you think about high voltage cathode, for example, high nickel NMCs, you want to push for 4.55 volt, that really goes to the range of the polymer start to decompose. They're almost organic polymers, right? You have to really think about how can you design an organic system that can really withstand a 4.5 volt stability. I think that's the key, right? Because at that range from 4 to 5 volt, I think there's really paper talking about even carbon black, they start to oxidize around that voltage, right? So by thinking about, it's really important to think about stability. I think that's the most important part. Think about stability. So if you do have a stable polymer, you can withstand the 4.5, even 5 volt. It's a game changer, right? So, I encourage you to think about that, but really put the stability in mind. That's really the first important thing for that.
Thank you. Let me come back to Professor Rojo. So we have one question for sodium-ion batteries. So is about the sodium plating on the hard carbon. This is the first, and the second is about life cycle assessment of sodium-ion batteries if we compare to the lithium-ion batteries, especially this new regulation of in Europe in order to recycling the battery. How about sodium-ion batteries?
Is this a question for me?
Yes, for you, please.
That is to the solution of hard carbon. It's a good proposal. It's a good thing, but the problem later is to move for the industry, for the market. In the market in general, they don't. This is a expensive process, if you want, that is not interested generally in the market to study the hard carbon. I think is the most important in this case is to increase the capacity, but perhaps following the Professor Komaba method, using some support like magnesium oxide or something like that in order to create a porosity, inadequate porosity in order to move in to facilitate the sodium diffusion. But yes, it's possible to do sodium to pressuriate the hard carbon. Yeah.
Yeah, and the second question is about life cycle assessment of sodium-ion batteries or sodium-ion batteries recycling.
Sodium-ion batteries, sorry?
Yes, recycling, battery recycling compared to the lithium-ion batteries.
Well, I think it's the recycling is not an important topic because, you know, the materials, the raw materials are not expensive, are not toxic in general. Not in the case of lithium that you have cobalt and nickel. That is very important to recycle, and also lithium. But in this case, you have sodium metallic sodium, or usually the carbon, the cathode is carbon and nickel, cobalt and nickel free. This is, in my opinion, is not necessary to invest funding for recycling in sodium-ion batteries.
Maybe one
Yes,
question
please,
to Professor
please.
Rojo.
Yeah.
Yes, you know, for example, in industrial point of view, for example, cost is more important. And for this point, for example, the storage of the material or how you handle your materials in air, the stability of cathode materials for sodium-ion battery is one of the questions that we have today. And my question behind is, did you check the stability of different materials that you are using in your lab in terms of moisture, for example, effect or not?
Well, it's obviously if you are working for polyanionic material, you don't have problem for degradation. In the case of layer oxide, you have yes. In the case of layer oxide, you have the same problem that with lithium, with the manganese in the lithium ion. This is a problem, but not, for example, in the polyanionic or in the Prussian blue materials. The problem, the degradation, is coming in, for example, the degradation of sodium or manganese in the layer oxide. But we are working in the same direction that the lithium. We are trying to form a coating for aluminum oxide, nickel oxide, or titanium oxide in order to avoid the degradation, in order to avoid the manganese problems in these materials.
Yeah, with the kind of doping, you don't check, for example, because I had some work with Jean-Marie Tarascon on this topic, and what we found is just doping by, for example, copper, you can suppress this kind of moisture effect. That's why I'm asking you if in your side. Okay.
Yeah, in my side, for example, we have not. We are working basically in the layer of side. We have not any problem because we are working in thermal synthesis. Is a high temperature. No problem at all. In the case of the vanadium fluorophosphate, we are working in hydrothermal synthesis. This is we work that. We are trying also to prepare some for the sol gel method, but the particle size is not significant enough to move in this direction. But yeah.
Okay, good.
Yes, thank you. Let's move to the video's presentation given by the PhD student, postdocs, and researcher. So then we will have discussions. So please. So the first speaker is Marwa Tiyuri. She's a second year PhD student, and she will present high rate sodium zirconium phosphate electrode materials for sodium ion batteries.
Dear audience, I have the honor today to present a part of my research work entitled High Rate Sodium Nickel Zirconium Phosphate as an Electrode Material for Sodium Ion Batteries. That work was carried out in MSN department at Mohammed VI Polytechnic University. The rapid development of renewable energies and electric vehicles has led to a very high demand for energy storage systems. In this regard, different technologies of energy storage have been developed, but the electrochemical devices, and specifically secondary batteries, are the most suitable technologies for these applications due to their flexibility to electricity systems, their high efficiency, modularity, and their faster response time that they provide. The performance of these systems is highly dependent on the electrodes material. The phosphate polyanionic materials have attracted increasing attention due to their excellent electrochemical performance and versatile structure. Among these phosphate polyanions, we can find the Nazican sodium superion conductors, which are indicated as one of the most favored frameworks to provide phase stability on cycling in sodium ion insertion systems. Add to that, they provide a low price and they are safer compared to other materials like the layered oxides, for example. Our phosphate-based material was synthesized through a simple source-gel method. Firstly, the following raw materials were mixed and stirred in an aqueous solution, then heated up at 60 degrees Celsius until complete evaporation and gel formation. After that, we proceed to a calcination for 9 hours at 750 degrees Celsius with intermediate grinding. As we know, phosphate-based materials have a poor electronic conductivity, so for that we proceed to a carbon coating in order to increase it. Our material was mixed with an appropriate amount, 15% of the total weight of the material, with in an acetone solution, then calcinated for 5 hours at 600 degrees Celsius and the continuous flow of argon. For the structural characterization, the XRD analysis shows a well-crystallized sample with hexagonal symmetry and R3 space group with the following cell parameters. The comparison with those of good enough groups confirmed the accuracy of our refinement and the stability of the material. Raman spectroscopy analysis was conducted to check the carbon coating process. We can notice the appearance of two bands, which refer to the G and D band characteristic bands of carbon. Thermogravimetric analysis was also employed to determine the amount of carbon. We can notice that we have 3.55% of the total weight of the composite material. The morphological analysis shows uniform and well-shaped particles with an average particle size of 1.5 micrometer. Also, we can notice the presence of some agglomerations in the coated sample. Concerning the electrochemical test, cyclic voltammetry is performed at the scanning rate of 0.2 mV per second. We can notice a cathodic portion at 0.8 until 1.2 volt, while a anodic portion appeared at 2.2 and 2.4 volt. We didn't notice any significant difference from the first cycle until the sixth, which indicate the stability of this phosphate material. Concerning the galvanostatic test, our material was tested in a half sodium electrochemical cell between the potential window 0.01 until 2.5 volt at current density of 25 milliampere per gram. It delivers an initial charge capacity of 121 milliampere hour per gram and a discharge capacity of 114 milliampere hour per gram. Also, it presents a good efficiency of 98% after 25 cycles at 25 milliampere hour per gram. This phosphate-based material was also tested at different current densities. We can notice that the capacity still remains 19 milliampere hour per gram at the current density of 500 milliampere per gram, and it's stable compared to the other current densities, which indicate that our material works very good in high rates.
So to conclude, the pure phase of sodium nickel zirconium phosphate was successfully synthesized by local soldier method. Electrochemical tests show good discharge capacity and an excellent stability at a high current density. As a perspective, we are seeking to perform forward analysis such as an in situ X-ray operando to well understand intercalation and disintercalation mechanisms of our phosphate-based material. And thank you very much for your attention.
Okay, so let's move to the second registered video. Recorded video is given by Al-Matawi Hussein, who is a Master 2 student in Muhammad VI Polytechnic University, and he will introduce the solvent synthesis of lithium vanadium as high capacity and high capability anode for lithium-ion batteries.
Hello everybody, I'm Al-Matawi Hussein. I recently graduated with Master degree in Material Science and Engineering. Today I will talk about solvent synthesis of lithium vanadium oxide as a high capacity and high capability anode material for lithium-ion batteries. As you know, the electricity grid are so complex system which demand and supply must equal at any given moment, especially during the current context of renewable energy development. Energy storage system becomes strategic to help ensure the balance between electricity production and consumption and create a flexible and reliable grid system. Electrochemical storage by means of battery remain the most widely used because of its considerable advantage over other solutions, that of mobility, high energy density, and high efficiency. And here I'm talking about lithium-ion batteries. The electrochemical performance of lithium-ion batteries depend on the reversible redox reaction between the anode and the cathode side. In terms of the enhancement, the improvement of the anode material is significant compared with the cathode material, meeting the requirement of high energy density and high safety. However, the anode side are dominated by graphite, but still some challenge related to its lower theoretical capacity and flashing phenomena at low voltage. So, to overcome this limitation, the development of some alternative is required. Here, lithium vanadium oxide look as a promising class of anode material. In this study, the lithium vanadium oxide has been prepared in nanometric scale using Solger reaction, where the citric acid as a gelatin agent was injected into a solution containing methyl-cation. Here we obtain a gel precursor. We wash and dried at room temperature for several days to obtain threshold precursor, then heated at 550 degrees C for 3 hours to get the final product. Now, let's move to the structure characterization. The analysis by XRD showed that we have a well-crystallized sample with octahedral structure with the following set parameter and space group. The structure properties of the anode material were further examined by Raman spectroscopy. So these obtained band represent vanadium double and triple coordinated oxygen, which contribute to the vanadium lithiation structure. The same image showed that the material consists of aggregate of particles with size ranging from 200 nanometer to several micrometer. The smaller crystal size of lithium vanadium oxide can be explained by shorter heat treatment time during synthesis. We can also observe the isotropic character of the particle with minor structural stress. Evaluated as anode material for lithium-ion batteries, lithium vanadium oxide demonstrates an interesting electrochemical performance, as confirmed by galvanostatic charge discharge process and cyclic voltammetric test, which can deliver a capacity of 300 mAh per gram at current density of 25 mA per gram and exhibits excellent reversibility of lithiation-delithiation process with mainly two pairs of redox peak located at around 0.5 volt and 0.8 volt respectively, correspond to the oxidation-reduction reaction. These redox peaks are attributed to the reversible extraction of two lithium ion from the structure. More than that, the lithium vanadium oxide demonstrates a stable capacity after 100 cycles with a capacity retention of 100% and good rate capability with reversible lithiation-delithiation process compared to those reported in the literature, as well as graphite material at the same current of density of 500 mA per gram. As a conclusion, the lithium vanadium oxide anode material demonstrates a good electrochemical performance and presents a promising candidate anode material for lithium-ion batteries.
Okay, thank you. Let's move to the third presentation, which is given by Abdelhafid Al-Atifi from Faculty of Science, Sidi Mohammed bin Abdullah University, Fez. The title of the presentation is Charging Interface based on LDO, Regulator for Lithium-Ion Batteries Technologies.
Hello, my name is Abdelhafid El-Atafi. I'm a PhD student in Sidi Mohammed bin Abdullah University, and I'm here today to present our work of LDO regulator-based charger for a lithium-ion battery in 118 nanometer CMOS technology. The outline of this presentation is as follows. Introduction, LDO regulator-based charger for a lithium-ion battery, simulation and drawing of masks, and conclusion. The use of the battery has become very much in demand as they are essential in most electronic equipment, some of which are used daily. So finding the best and the most optimal techniques to charge a battery has become a new challenge. There are many advantages of these batteries like very high energy density, very low self-discharge. We have also some disadvantages like special charging required and the risk of explosion if all safety conditions are not met. For charging a battery, we have 3 steps to follow. First, the constant current trickle mode, second, the fast constant current mode, and the third, constant voltage mode. Trickle current constant mode, when the battery voltage is less than 2.9 volts. The internal resistance of the battery becomes greater, which forces to charge the battery in the trickle constant current mode. Fast constant mode, when the battery voltage is higher than 2.9, the process switches from the first mode to the second mode. The constant voltage mode, in this mode, a constant voltage is used for the battery when the battery voltage is higher than 4.2 volts. In our circuits, we use operational amplifier. The first stage of an operational amplifier is a differential amplifier. This is followed by another gain stage. Then we use a comparator. It's a circuit that compares an analog signal with another analog signal, and the output is a binary signal. We use also the bandgap multi-output voltage reference. The basic principle of a voltage reference circuit involves a weighted summation of a voltage by current proportional to the absolute temperature beta, and a voltage by current complementary to the absolute temperature theta, so that the resolution voltage by current will have a zero temperature coefficient. The LDO low dropout type linear regulators, which are voltage regulators that allow to obtain a regulated voltage V output very close to their supply voltage. The advantage of these voltage regulators is that there is no ripple on the output voltage and no disturbance due to the switching. Unlike other architectures that use microprocessors to control the different charging modes, the architecture we proposed is a purely analog supports following the 3 charging modes of lithium-ion batteries: trickle current, fast constant current, and constant voltage, using a current mirror to have a constant and controllable current switches to change between the different modes, and a comparator to control the switches. Here is the simulation of our circuits. Then we made a layout with an optimal surface of 0.25 millimeters square, which is divided in two parts, control and power parts. Finally, this is a comparison between our work and the other works to show you the optimization we did. Generally, we have a higher efficiency and a column with a smaller shape area. And thank you for your attention.
So the last presentation given by Zinab Qasmi, and she will present the DFT calculation on MN dot and the pristine sodium iron fluorophosphate for sodium batteries applications. Please go ahead.
Hello everyone, my name is El Qasmi Zinab. I am a PhD student at the International University of Rabat, working on the development of phosphate-based materials for high energy density batteries, supervised by Professor Bali Mohammed, and today I'm going to present a recent study on the MN dot and pristine fluorophosphate by DFT calculations. Our way of living has become dependent of all kinds of energy, limiting its sources that seemed inexhaustible. To alleviate these problems, the use of renewable, sustainable, and clean energy sources becomes urgent to address the worldwide shortage of resources and global warming concerns. Secondary batteries reveal to be one of the most feasible options due to their high energy efficiency, versatile power, and suitable energy characteristics to meet various functions. The development of batteries has been through several years, from the 1836 up to now, showing the richness of these energy sources. Batteries consist of three main components in which a mobile ion is reversibly shattered between a cathode and anode through the electrolyte. During discharging, the ions are transported from the anode through the electrolyte to the cathode, releasing electrons to have electricity in the external circuit. During the charge, a voltage is applied to reverse the ion's migration direction to the cathode. The dominant cathode material in lithium-ion batteries are lead oxides. Sodium extraction from lead oxides induces phase transition leading to structural instability over prolonged cycling. In comparison to lithium lead oxides, sodium lead oxides shows an overall lower capacity. This material can experience up to 9 phases transitions, indicated by step-like plateaus in the voltage profile, while lithium lead oxides exhibits a single plateaus at 4 volts. On the other hand, graphite is the most common lithium-ion battery anode. It does not exhibit appreciable capacity for sodium-ion batteries. Graphite's poor electro performances is attributed to its insufficient interlayer spacing, which is 0.34 nanometer. Theoretical calculations indicates a minimum interlayer spacing of 0.37 nanometer, essential for sodium intercalation. Hard carbon is the current preferred sodium-ion anode material for their high capacity, lower working potential, and good cycling stability. The introduction of electronegative fluorine ions into sodium-based phosphates creates a new class of host structure and compositions, namely fluorophosphate materials. The presence of high ionic fluorine in ion sublattice structure with strong bond covalency stabilize the metal coupled states to increase the redox voltage. As a start, the calculation of the gravimetric capacity for fluorophosphate materials reveals the high capacity of both Mn-based and iron-based materials when compared to the others. The combination of both manganese and iron would be a good strategy for improving the electrochemical performances. Iron-based fluorophosphate material exhibits an orthorhombic structure, and the lattice parameters are comparable with an experimental published crystallographic data. This material has a band gap energy of 2.19 electron volt. We should also mention that the sodium extraction, sodium on site 2 are extracted first compared to sodium on site 1 and exhibits for PAT A an activation energy of 0.43 electron volt. Here we have for each Mn dopant percentage the corresponding band gap energy, and it shows that the lower band gap energy is attributed to 50% Mn doped material. The activation energy of the same pad, such as the A pad, is 0.34 electron volt, meaning the stability of the sodium migration inside the monoclinic 50% Mn doped material. The same conclusion is that 50% Mn doped material seems to be a good option that probably allows improving the diffusion mechanisms. The average voltage quality factor, in addition to the previous results, are showing a marked enhancement of the electrochemical and electronic properties of the 50% Mn doped material. And thank you for your attention.
So that was the last presentation. So I ask all the panelists to join the discussion, students and professors. So you can raise your hand. We have several questions to the PhD students. Professor Rojo, please go ahead.
Okay, thank you. First of all, very interesting talk. First of all, I would like to thank this presentation. It's very interesting and in 5 minutes you can say a lot of things, no? But it's I am very surprised by the topic and the work developed here. You know, in 5 minutes it's difficult to say. I think I have some, I don't know, questions. For example, for the first speaker, it's working in the NASICON, sodium, zirconium, nickel. Yeah, I want to ask, in the preparation, if they have impurity like zirconium oxide. What is the amount of zirconium oxide?
So Marwa, can you turn your microphone, please? Marwa Tayuri.
Yeah, sure. Could you hear me?
Yes.
Yeah. Thank you, Mr. Rojo, for your question. I think the impurity of zirconium oxide is about less than 100%.
Okay. And what is what electrolyte have you used in the electrochemistry measurements?
Sorry, I didn't.
Electrolyte.
The electrolyte is 1 molar in PF6 in EC/DC.
Okay. Yeah. And what about the C rates? You have worked at a low C rates, no? C over 10 or?
Yes, we tried different C rates starting from 25 milliampere hour per program density, current density, 25 milliampere per gram, and then 15 milliampere per gram until 500 milliampere per gram. And it shows kind of stability at the high rate at 500 milliampere current density.
Okay, excellent. Okay, thank you. A very interesting talk. Okay, thanks.
Thank you very much. Thank you very much, sir.
I have another question for the full presentations. Is DFT calculations, and it's also very interesting study. This is a very interesting materials like that is important to move in the fluorophosphate. It's important to move from vanadium to another cations, for example, not toxic and not expensive. This is a brilliant idea to move to iron fluorophosphate, and also with doping in manganese, with manganese, because manganese and iron are not expensive, are cheap, but environmentally friendly. It's a very good idea. That is not the preparation of the sample are not the in the preparation is not like vanadium phosphate, but you are preparing also, I suppose, also in hydrothermal synthesis, and you can control this one. And this is a very good idea. But my question is, we are trying to make a substitution of iron 3 plus for vanadium 3 plus. In the iron 3 plus, we have in a high spin, we have a D5, no Jahn-Teller effect. But if you are moving with manganese 3 plus, this is Jahn-Teller effect. Yeah, I can see that in the electron voltage measurement, the theoretical data, they have for the iron 3.74, I think, electron volts, and in the case of manganese 3.8. My question is possible to have all a solid state systems with all range of substitution? My opinion is the iron who control the structure, but with a high amount of manganese, the manganese make a perturbation in the structure for the Jahn-Teller and moving that. My question is, how is the maximum amount of manganese that we can introduce in the iron phase? Is possible to, perhaps it's a lot of things at the same time.
Thank you, Professor Rofo. Yes, please, Zineb, transmit your micro. And
yeah, I thought it was a question about how can we define the amount of manganese. This is it, if I heard. Yes. Yeah, okay. So as a start, we know that these materials have like a lake of electronic conductivity. Besides, they have like high ionic conductivity. So as a start, we choose to investigate the electronic conductivity, so we can have like an idea about the amounts of manganese we can choose.
Yeah.
And from the band gap and band structure, we saw that 50%. I mean the
yeah.
And we started from there.
And the energy allows to study all range of composition. It is a solid solution in this case, so there is some amount of manganese in which the energy is not enough to maintain the iron structure.
I'm sorry, I didn't hear well the question.
Yeah, I mean, it's just in your calculation, in the DFT calculation, you have, I suppose you have the stream, the manganese and the iron, okay? In the electron volts is different on all of them. Can you control, can you say something about a comment about the effect of manganese substitution in the iron substitution, in the iron phase?
Yeah, I'm sorry. The main thing we used is the voltage, because manganese has higher voltage than the pristine. So this addition like improve the voltage, the average voltage of these materials, so we can have like high energy density then.
Okay. Okay. Thank you. A very, very interesting work. Thank you.
Yes, sir. Thank
you, Professor Rofo. So yeah, I encourage all the panelists to ask and give recommendation to the PhD students. So I have one question here from Lubna Htidou. So the question is for Abdelhafid. In your opinion, what is the optimal charging protocol for fast charging applications? So please, Abdelhafid, turn on your microphone. Yes, so maybe Hafid is not with us, or some technical issues. So I would like to ask Zineb Kasmi, did you try to combine some experimental work to your DFT calculations, especially the Mn dot for sodium iron fluorophosphate?
Yes, of course. Yes, we are working now on the experimental part, which is elaboration, characterization, and also the electrochemical tests, but they are not complete yet. And maybe next year I'm going to show you these results.
Okay, excellent.
Okay, so let's move to Mohammed Shakir, please.
Yes, thank you for these nice presentations. The question is for Mademoiselle Miss Marwa about Nasicon nickel-based Nasicon phosphates. The first question: what is the theoretical capacity of your material? How much of milliamps per gram you expect?
Yeah, the theoretical capacity is 106 milliamp per hour.
For one sodium, right?
Yeah.
And it's strange for me. I cannot see the peaks oxidation reduction of nickel in your CV for diameter cyclic curve. Did you have explanation for this?
The oxidation peaks of nickel.
Yes, because then in your materials you oxidize the nickel, and yeah, the oxidation reduction reaction is it's nickel, right? Nickel 2 to nickel 3 or more.
Yes, but also there's the oxidation reduction of zirconium.
The active materials, the active element here is zirconium?
I think, yeah.
I don't think so.
Yeah, I agree with this. I'm agreeing with you, Mohammed Shakir. So I think is nickel, because we have the same. So Professor Good enough published 2 years ago this phase with Mn zirconium phosphate, and they show the peaks of Mn. So the nickel is still. So we are still working on that, and we don't know why exactly especially is inactive as a cathode material but active as anode. So what she did, Marwa, she made this electrode as negative electrode, but not cathode, because cathode is still inactive at this moment. So we are working on that to discover why it doesn't work actually. It's work for Mn, and also we work with the cobalts. We presented last year here in IRSEC, but nickel is mysterious. It doesn't work.
Yeah, that's why I'm asking, because the question behind is, even if you, okay, but the response is no. If you tell me that this nickel, because nickel it should be higher than 2.5, okay, you have a kind of small peak around 2.2, but nickel should be higher, around 3 point something. Okay, assuming that. Yeah.
But the cathode of Mr. Goodenough is the material of Mr. Goodenough is a cathode material, and in our case it's a anode. So for that I expected that this peaks is for the zirconium, not for the nickel.
What is the reaction? You reduce the zirconium? Did you check? Yeah, if yes, did you check, for example, after?
No, we didn't check, but I think we have to do some further analysis like the XPS to know exactly what is the oxidation reduction couple.
Okay, you know, sometimes you can just introduce the elements lithium or cadmium in the structure without oxidizing anything or reducing anything. You know, the Nasicon you have, I don't, okay, in E3, all the sites are occupied, right? Yes.
Yes.
I don't remember the structure. I work on this phase a long time ago, but yeah, I think you have to check. You have to be sure that to explain what happened, because okay, I don't understand to be honest with you. More experiment. I think more experiments are needed here to explain what is happening.
Yes.
if you have a radio oxide reduction reaction, or just you put and extract extra sodium in your structure, or maybe just electrolyte, I don't know. But what is strange is your material is working well in the cycling.
Yeah.
Okay.
Yes. Yeah. Professor Go, he raised his hand. So I was wondering, because Dr. Mati is not with us, and the question is like from the second speaker, Hussein. So he presented the lithium vanadium oxide. So is this material can be used in state of LTO with LFP or NFC as presented by Microvast in the first speaker? Please, Dr. Go ahead. Just turn on your microphone, please.
Is that my turn to ask questions?
Yes, please.
Okay. All right. So this question is also about the sol-gel synthesis of the vanadium oxide anode. So when I look at these, right, these, what are the advantages, right, for that? Because you have graphite, which is very stable, right, and you have other potential materials which have higher capacity, and now you introduce a material with higher capacity, but then there's also higher potential. So when you couple with cathode, you lose some of the voltages. So what are the advantages that you can extract from this material? If you really have a successful the vanadium oxide anode.
Yeah, so Hussein, turn on your microphone. Can you answer to Professor Go? Can you comment on the voltage, average potential voltage for lithium vanadium oxide, or the capacity also, and compare it to graphite?
Or maybe the read performance, right? What are the advantages that you can actually see through these materials?
Yeah, it is safe. I think even at high rate capabilities, so we cannot see some dendrite formation on the anode parts. So this is why it can be potentially used instead of LTO. Yeah. Hussein, you are with us. I don't know if Hussein is here, so he can answer to the question.
So that's okay. So the other question I have is regarding to the first talk, which is from Mara, about these sodium-ion batteries. And I think we have a lot of discussion, with Professor TO2 and also Dr. Amin also mentioned that is when you look at the sodium-ion batteries, right? One of the advantages is, you can really use manganese and not using nickel or cobalt or these kind of materials. So maybe that's a direction, when you think about sodium-ion, is think about the transition metals, which is more abundant, right? I mean, shy away from the nickel and also the cobalt and kind of things that are actually competing with lithium ion. So that's just asking, is that possible that in this kind of structure you can use manganese, kind of replacing nickel to do this kind of to create structures?
Yeah. So any questions for audiences? Maybe I have some questions about which is better as binder, CMC or PVDF for materials containing structures water. Thank you. This is from Asma Cafe. So she asking which is better, CMC or PVDF binder?
Oh, you ask me?
Yeah, she asked. She didn't address.
Sure, yeah.
Yeah. So, please go ahead for the answer.
So I would say it's really depending on applications, right? If you look at cathode, right, it's almost exclusively people using PVDF. It's just because, especially when you look at high nickel, which is and high cobalt, and these kind of electrode systems, it tend to pretty reactive to water system, right? If you use CMC, SBR is an aqueous-based system, which is good for the environment, but it's not good for the cathode material. So you end up with electrode. It doesn't really last. I mean, once you make electrode, it has a lot of side reactions, right? But when you look into anode, for anode application currently is all graphite. So the preferred system is CSBR versus PVDF. But then if you look into hard carbon and some different carbon material where you have a lot more free volume, I would say, and they tend to trap water, CMC become a problem because water-based binders start to trap a lot of moisture inside. It's hard to dry out, so you end up with a battery system that have a lot of initial loss at the beginning, and then also you compromise lifetime. So I think it's really in terms of manufacture, you really have to balance the environmental concerns and cost versus life, and in the end, I think graphite, I would say in general, same CSBR is a very good choice, right? People, there's more and more, application moving toward that direction. I think for consumer electronics, almost 100% is same CSBR, and power batteries, and there's more and more using that right now, just because people using graphite, they want to have a lot of high capacity, then you can. And for cathode, people still stay in PVDF because one is the stability in making slurries. The other one is really because of the stability at higher voltage, because that's another concern, right? If you push to 4.5 volt or even 4.3 volt, and the SBR start to create a problem, for the cathode. So for a variety of reasons, I think cathode, they perform, PVDF, and anode, more and more move towards same SBR. But for silicon, it's still I would say the verdict hasn't been out yet, just because, if we only use 5% of silicons, it seems all kind of binder can do the same job. But if we move to 80% silicons, I'm not quite sure if aqueous is the solution first, because you take silicon particle, you mix with water, they produce hydrogen. So, but I don't really say you cannot use water to make slurries, but that's one of the concerns, right? And then you have all the expansion, contraction issues. So there's a lot of concern, I would say, for high loading, silicons, it's open field. So.
Yes, thank you, Professor. So now I think we are behind the time, 15 minutes. So if no question for audience and also from the panelists, please, Professor Gao, go ahead and close this session.
Oh, I'm really, I think that's a great section, and there's so many discussions, and I really hope that, for us, we really enjoy. We all thanks for the committee's invitation, and for all the audience. I'm also one of the audience, right? It's really a very nice the talks. We learn a lot from both from the panel speakers and also from the student speakers. Excellent student speakers, really see the breadth and also the depth of the works. Very nice. So really like to thank you for the organizers for these, and thank you for all the audience, and really hope we have a good meeting moving forward. So let's close today's section, and let's give a one big applause to everybody in this section. Okay.
Yes, thank you. Thank you very much, and see you tomorrow in the same place and in the same time for the second day for this battery workshop. So 2 presentations will be given by Dr. Mohamed Shakir from UNO and Professor Stefano Passarini from Germany. So see you all tomorrow.
Okay, thank you.
See you
Thank you very much.
Thank you. Bye.